so on. So graphs represent objects and their relationships through nodes and edges. So rather than thinking of the world or the entities or the system that we are trying to model as a set of disconnected, separate entities, it is all about modeling the patterns and relationships between them. And what this allows us to do is to capture relations, and which leads to better and more accurate models, because borrowing of information and signal happens through the network. Such graphs appear as most valuable data in many different domains, from healthcare to IT industry to commerce and retail, manufacturing, finance and insurance, as well as transportation. So today, at this workshop, we are showing research advancements in graph machine learning. We are showing exciting progress in the PyG ecosystem and partnerships, as well as showcasing industrial applications. We will show how these technologies propel advancements of artificial intelligence and machine learning, and applications of AI to the next wave of science and industry. We are also going to announce new tools and partnerships that power these tools and applications. So thank you all for being here, for attending. Thank you, researchers, developers, and partners who join us to make this event amazing. So welcome to the Stanford Graph Learning Workshop. So deep learning for graphs, I want to quickly introduce it. The basic idea is that we are given an abstract graph between a set of nodes, and we have a set of edges, relationships between them. And the idea is that if we want to make a prediction at a given node in the network, we are going to define a neural network structure that captures the network structure, the graph structure around that given node. So for a node A here on this picture, here's an example of the neural network that is going to perform the computation to make a prediction for that given node. And what this means is that this network defines a computation graph that has two main operations. It has a message passing function that is learned, and it has an aggregation function that can be learned. And this means that when we are making a prediction for a given node, we are not only using the information at that node, but also the neighboring information. So graph neural networks are a way to generalize and apply deep learning to graph data. And it can learn patterns and relations on a giant scale and train accurate predictive models. There are two views on GNNs. One view is that graph neural network learns to combine features from the node itself as well as its neighbors and neighbors of neighbors in an optimal way to generate more accurate predictions. But it also learns the structure of patterns and relationships around that target graph. So the graph neural network captures both the structure as well as the feature information, the node information around the target node. This is very important because GNNs adapt to the shape of the data around the point of interest. And this is very different than other, let's say, deep learning models that assume a fixed input structure and a fixed, let's say, window. Here, every node can have a different neural network structure because the network neighborhood around it is different. So the model adapts to the data. So in this respect, graph neural networks are amazingly general framework that allows us to connect or glue together various kinds of models and various kinds of data modalities. For example, GNNs, they subsume CNNs and transformers, and they are just a special case of a general graph neural network framework. So this framework is so general that there are many different applications in many different domains. Everything from drug discovery to recommender systems, customer 360 journey analysis, fake news detection, fraud detection, as well as supply chain optimization. This is actually one of the hottest subfields of machine learning right now. Here I'm showing the popularity of different keywords of papers submitted to last year's ICLR, so International Conference on Representation Learning. And I'm also very excited that in December this year, we are organizing the first Learning on Graphs conference that will be in December. What I want to do next is I want to showcase some applications and talk about some tools. So one example where it is very important to have good graph structure and be able to work with dynamic graphs is in financial networks, which describe financial entities and their relations. And there are many tasks that you would want to run over this type of data, from fraud detection, anti-money laundering, to anomaly detection, credit scoring, and so on. So you can define a lot of different tasks over this dynamic dynamic network, from node-level tasks where you want to detect, let's say, bad actors, to subgraph-level tasks where you want to identify, let's say, anti-money laundering subnetworks, or edge level where you want to predict fraudulent transactions, anomalous transactions, and so on. We have been actually working with a central bank of a small European country to develop tools to be able to make active predictions about how this financial network of financial transactions is evolving over time. So the central bank was able to process dynamic graphs of tens of millions of transactions and make accurate predictions about what financial transactions are going to occur in this country next. The tools we developed led to between 40 and 70% improvement in accuracy over previous state-of-the-art. And more importantly, these tools are robust to the changes of transaction pattern over time. So we developed a tool for dynamic graph analysis called Roland that allows for a very easy creation of dynamic graph neural networks from any static GNN architecture. And it provides a scalable and adaptive strategy for training and high accuracy models. We have built Roland on top of PyG Graph Gym, which allows us to efficiently explore the GNN design space and find the architecture that performs well. PyG is the GNN library, an open source GNN library that we've been developed that provides state-of-the-art graph representation learning. It comes as a set of models, operators, an entire storage and graph manipulation framework, and sits on top of the PyTorch and uses it as an engine. So this year, we released PyTorch 2.1, where we developed PyGlib, which is a low-level GNN engine that scales and accelerates PyG. And it allows our partners to contribute scalable code that improves the performance of PyG. We also improved the design of GNNs and versatility of our framework by allowing developing principled aggregations. And we have also released many different modeling milestones, like scalable link prediction, 1,000+ layer deep GNNs, GNNs for heterophily graphs, and so on. Actually, PyG is the most widely used GNN graph learning representation framework. It implements over 80 different GNN architectures, 200 plus benchmark data sets. It has a very nice extendable interface, so it's easy to develop new architectures. And it also has sparsity-aware, high-performance CUDA kernels. The project has over 15,000 stars on GitHub and almost 3,000 forks. So if you are excited to use it, you can just type this command, and it will be installed. PyG is heavily used in research community, but also in industry. And it powers many different products and applications across a wide range of industries. Everything from Airbus using it to do anomaly and outlier detection, AstraZeneca using it to build knowledge graph for drug repurposing, Spotify, we are going to hear today about using it for their recommender system, fraud detection, all the way to fluid simulations at Saudi Aramco. Furthermore, we have also released a set of graph machine learning case studies and use cases that are freely available online and were actually created by Stanford students as part of the class that I teach. So it's a set of informative blog posts with code examples about how graph machine learning can be applied to many different domains. We have also released videos, training materials that teach you about graph neural networks. So basically, the Stanford course CS224W, Machine Learning with Graphs, is freely available on YouTube. And over 700,000 people have watched the videos so far. And perhaps the most importantly, PyG is supported by a huge community. Over 1,600 different research papers have been published using PyG. We have over 100,000 monthly downloads of the library, a community of 300 external contributors and developers, as well as a Slack community of over 3,000 members. And if you are excited about PyG, want to contribute or get involved, you can send us email, you can download the code, you can reach us through the Slack channel. One of the important aspects of graph machine learning is scaling it up, especially because the real-world applications really reach, the graphs in them reach sizes of billions of nodes and edges. And now, with PyG, we can learn deep learning models at giant scale that train predictive models for a graph in an accurate way. So one important announcement we have is that we have developed new abstractions that separate out the representation of the graph wireframe from the node feature information. Usually, those are stored together, but that is highly inefficient. So in PyG, we have developed new abstractions and implementations of them that allow for scaling up of graph learning by storing separately the graph wireframe, the graph structure, as well as the node feature information. So what is new in PyG is that now we have a concept of a graph store, and we have a concept of a feature store. And as a consequence of this, I'm also excited to announce two important partnerships in the PyG community. First is a partnership with NVIDIA, where NVIDIA joins us to accelerate PyG on GPUs. So we are working together on GPU-accelerated neighborhood sampling via QGraph integration, as well as GPU-accelerated heterogeneous GNN execution, which is very important. And also, NVIDIA's graph as a service engine can act as a graph store in the PyG framework, as I was showing earlier. Another exciting partnership that we have is with Intel, where Intel joins us to accelerate PyG on the CPU side. Here, we are working on accelerated inference of GNNs on the CPU, as well as accelerated neighborhood sampling techniques that give us about 20x speed up. In order to be able to accurately track the progress in terms of machine learning on graphs, we are also releasing what we call Open Graph Benchmark, which is a set of benchmark data sets that are used by the community. We have released the first version of OGB in 2020, and we have released the second version of OGB, the OGB Large Scale Challenge, last year at KDD, with over 500 different teams participating in different graph machine learning tasks. And that led to a huge leap forward in terms of modeling performance and understanding the performance of graph neural networks on various kinds of predictive tasks, on various types of graphs, from knowledge graphs to information networks, social networks, molecule classification, and so on. So this year, we are announcing OGB Large Scale Challenge 2, which we are running at this year's NeurIPS conference that will be in a couple of months, where we are releasing new data sets, even larger data sets with even more information, so that even bigger GNNs can be trained and the performance can be further improved. So if you are interested about this, go to ogb.stanford.edu. And last, I want to talk about knowledge graphs. Knowledge graphs are a way to capture and structure human knowledge in a machine understandable form. So knowledge graphs store facts in a form of a triple of a head relation tail. And we can have different types of heads and tails and different types of relations. There are many examples of these types of knowledge graphs, everything from common sense to world knowledge to also domain-specific knowledge graphs for various industries, for drug discovery, biomedicine, and so on. And what we've been working on and been very excited about is how do we answer complex predictions, complex multi-hop predictions over these types of knowledge graphs, where we are basically given a predictive query that we would like to find entities that answer it on the knowledge graph. And if the knowledge graph is fully complete, which it never is, then this would correspond to basically traversing the relationships in the knowledge graph. But we have developed a way to answer this type of queries directly in the embedding space. So knowledge graph can be highly incomplete, but the answers are still accurate. So an example that I'm showing here is we may want to predict drugs that might target proteins that are associated with a pair of diseases, D1 and D2, right? The goal is to find a set of drugs that have this type of relationship with a given set of diseases through the proteins they target. We have, in collaboration with Google, we have scaled up this type of reasoning engine or prediction engine over incomplete knowledge graphs to massive knowledge graphs. We are able to process a full freebase knowledge graph with 86 million entities and over 300 million edges or relations on a single machine. The framework is called SMORE, and it provides a scalable multi-hop knowledge graph reasoning. We have worked hard on the innovations on the algorithmic side as well as the system design side so that the performance of our system scales linearly with the number of GPUs you have and can run on a single or multiple machines. And what it allows us is to learn node embeddings in such a way that we can answer these complex predictive queries. And last, I want to mention the synthesis of knowledge graphs and large-scale language models. Knowledge graph can help us train much more effective large language models. And we have been exploiting both the relational structure between different documents as well as the knowledge captured by the knowledge graph about the entities mentioned in these documents. And we can get massive improvements and state-of-the-art results for many different question answering and other kind of NLP tasks, especially in domain-specific areas where there is a lot of prior knowledge that can be scattered across many, many documents. So knowledge graphs allow us to connect these documents together and provide additional supervision and additional kind of mesoscale supervision to the masked language models. So to conclude, today we announced new advances. We will announce new advances in research, new tools and platforms, as well as exciting partnerships and updates to the PyG ecosystem. We have a really exciting program for you with talks from the biggest minds in science and industry. The workshop program is as follows. We are going to start the morning session about the updates around PyG, and then the session before lunch, the main topic is scalability and performance of graph machine learning systems. In the afternoon, we are going to talk about exciting applications across many different domains, from drug discovery, fake news detection, recommender systems, and so on. So this event is live streamed on YouTube. We have about over 5,000 people who registered and are following the event, as well as a healthy crowd here in person. In terms of questions and answers, we are doing this through the PyG Slack, which you can join at this URL. And then you can join the Slack channel workshop 2022. And we are going to have the discussion and any kind of follow-ups in that channel. So with that, thank you very much. Great. So next, I'm excited to introduce Matthias Fey, who is a founder of PyTorch Geometric, or PyG, which is really the first and the most popular graph learning framework for deep learning on graphs. Matthias obtained his PhD from University of Dortmund and is now a founding engineer at Kumo AI. And Matthias is going to present all the exciting work that has been happening and is happening in the PyG ecosystem in the past year, as well as the plans for the future. Go ahead, Matthias.
Yeah, thank you very much, Yuri. Thanks for the invitation. It's really a pleasure to be here and to speak to that great audience here, both in person and online. I'm seeing that we have many people registered online. It's just great to see the interest in graph machine learning, but also in PyG. So thank you very much for that. My name is Matthias Fey. I will be presenting PyG. That means that what did we achieve in the past and what are the future roadmaps we're trying to integrate in the near future. So to start with that, as we learned earlier about graph neural networks, they can process graph structured input and are useful for many different applications. I just wanted to point out a different view about how we can see graph neural networks here, in the sense that they perform like a neural message passing scheme. So the actual computation that a graph neural network performs is depending on the input. And that means that it's like completely different from how we previously defined neural network, in which the computation graph was always fixed, considering like CNNs or transformers. So here we have like data-dependent computation graph, and that actually means that graph neural networks provide a way to generalize all these different architectures into like a unified computational framework. And so for me, it's actually like a new paradigm of how we think about and how we define neural networks, and that makes it so exciting to me. So just to give you an example, going from CNNs to GNNs is really trivial in the sense that we are no longer restricted to fixed neighborhood sizes or discrete kernels, but instead like we can operate and aggregate information from a varying number of neighborhoods or neighbors, and we can do that by making use of continuous kernels instead of discrete ones. We can also easily go from transformers to GNNs in the sense that transformers can be seen as message passing on a fully connected graph and then exchanging or computing these messages using attention. So graph neural networks are super general and super flexible, but that also makes them challenging to implement and unify into a single computational library. And so one of these challenges is, for example, that graphs are typically sparse and irregular. And so questions arise of how we can effectively parallelize this irregular data of potentially varying size. There's also a heterogeneity of the underlying data. So, for example, nodes can have numerical features, categorical ones. They can even describe images or text, and potentially even over different types of data in the sense of a heterogeneous graph. They are also inherently dynamic, and what I mean by that is that it's actually hard to find a scenario in which a graph will not change over time. And so a graph neural network naturally needs to incorporate that temporal information. There also exist various different requests on scalability. So for example, a computational framework of graph neural networks should work seamlessly both for sparse and dense graphs. And then there are also different representations or data sets of graphs. So we can have data sets that contain many small graphs in the sense of molecular learning. But there are also scenarios in which we only want to learn on a single giant graph. And so we need to encapsulate that into a single unified library. And then graph neural networks can, of course, be applied to a set of diverse domains and tasks in the sense that we are interested in both in node-level predictions, link-level predictions, and graph-level predictions. And we usually train them in a supervised fashion. But we also may be interested in tasks such as clustering or pre-training and self-supervision. And unifying them all is challenging. Our solution to that is called PyG, or previously known as PyTorch Geometric, which is a PyTorch library to unify all these concepts into a single library to enable deep learning on graph-structured data. It aims to provide or simplify implementing and working with graph neural networks, and that means that it provides necessary tools to create your own graph neural networks or plug these different components together to write them on your own. But it also bundles state-of-the-art GNN architectures and training procedures so that you can readily use them and do not need any experience with GNNs or how to write them and just plug them into your data. We are constantly encouraged to achieve high GPU throughput on sparse data of varying size. And I'm happy to announce today that we've made good progress on that one. And PyG is both suited, or we aim to be suited for both academia and industry in the sense that it should be flexible so that research is not limited by its scope and new research methods can be developed within. But it also should be comprehensive and easy to use so that industry can directly make use of these recent advancements and directly use them for their products and tasks. PyG is designed on 4 major design principles or components. And the first one are the graph-based neural network building blocks. That is like the heart of PyG. So we provide predefined message passing layers, graph-based normalization layers, pooling layers, and readout layers. And these all are defined based on unified interfaces to easily write your own. Also, PyG provides in-memory graph storage, data sets, and loaders in the sense that it easily supports both homogeneous graphs and heterogeneous graphs. And we provide access to over 200 plus benchmark data sets to easily get you going to train your own GNN. And for loaders, loader typically means here that we are using like some kind of mini batch technique to process both either many small or single giant graphs and to easily plug them into the GPU and into our training procedure. And we are happy to announce that we have now support for over 10 different sampling techniques introduced in research, and you can readily use them within PyG. Next, PyG provides graph transformations and augmentations. So you can manipulate your graph on the fly by dropping nodes or dropping edges to improve regularization. But you can also use more advanced techniques such as graph diffusion or missing feature value imputation. Importantly, PyG is not only limited to graph structured data, but can also process like mesh data or point cloud data by providing the necessary tools to transform this data into graph structured data and use GNNs on top of that. Over the last year, we also worked heavily on improving examples and tutorials, and we see PyG now as a central place to get practically started with graph neural networks. So we now provide videos, collabs, blog posts, and many, many other tools that get you directly started and learn about GNN in a practical way, whatever you prefer. And as Yuri mentioned earlier, we released the Stanford GraphML tutorials, which is like an application-driven way to get to know PyG. So you can directly search for your given application, and you correspondingly find a PyG example that implements that in practice. Importantly, I see PyG as like a highly modular tool so that you can easily swap out different components and test it and benchmark it. So it all starts with like defining the underlying data. And so we have access to many different data sets, and you can use them out of the box. It will get downloaded and processed, and you can even transform them to the given requirements that you have. After that, you usually input that data into a loader, and that loader is responsible for creating mini batches out of that. So either for single giant or many small graphs. And with that, we now provide support for node-wise sampling, subgraph-wise sampling, or graph-wise batching, and many, many others. After that, we are ready to implement our GNN module. So that module is a regular PyTorch model, but you can now just swap out the different GNN layers as you go. So here you would just instantiate these GNN layers, and then in the forward pass, you define the computation graph of your neural network. And you are really flexible in how to do that. Importantly, you're not limiting to always write your own GNN, but you can also make use of some predefined sets of models to directly get started using GNNs, and these models are derived from research and are well proven to be successful for a variety of applications. After that, the remaining part remains regular PyTorch. So you just iterate over your data that is provided by the mini batch loader. You move the data to the GPU. You compute the forward pass of the model. You input the predictions and the ground truths to the loss function, and then you use backpropagation and gradient descent to update the model parameters. So here we have access to the variety of loss functions and training routines that are provided by PyTorch, so we can easily make use of classification, regression on all kinds of different levels, such as node level, link level, and graph level predictions. But of course, you can get really fancy here and integrate techniques such as pre-training and self-supervision as well. Importantly, this scheme here stays the same across many, many different tasks. So it always involves defining the data, defining the loader, defining the GNN, and then defining how we actually combine these together and train them. With that, I'm happy to announce the progress we made over the last year and what we have in the pipeline for the end of the year. So just to give a quick timeline of how PyG evolved over the years, it was open sourced in November 2017 as part of my first research paper. And it took us 1.5 years to craft a proper paper release out of that with a title Fast Graph Representation Learning with PyTorch Geometric. And that paper introduced a lot of popularity and made PyG quite successful and familiar to a lot of people, which is great to see. After that, we tried to improve PyG. So we had some collaboration with the Open Graph Benchmark team, which provides a set of data sets of large scale size to improve graph machine learning. And here this collaboration ensured that we can easily use these data sets within PyG, but we also benchmarked them and ensured that PyG is well able to scale to all these different kinds of data. Last year at the Stanford Graph Learning Workshop, we introduced our Stanford University collaboration and also introduced PyG 2.0, which was like a really big release we were working on for 1 year. And with the main feature that got introduced here was heterogeneous GNN support, and we saw a lot of excitement over the last year, and people are using it with passion, I would say. So over the last year, we now acquired more partnerships in the form of accelerating and maintaining PyG for long and many more years. So we founded our own startup called Kumo AI, which is now also contributing to the PyG open source system. And we managed to maintain partnerships in the form of NVIDIA and Intel, which helps us to accelerate PyG both on CPU and GPU levels. Last month, we released PyG 2.1, which is also a big release and that introduced many improved GNN models and stuff like that, such as principles aggregation, scalable link prediction support, temporal assemblers, and many more features. We now aim to release PyG much more frequently, and we are aiming for quarterly releases. So the next release, PyG 2.2, will be released in November, and we are aiming here to improve accelerations and improve scalability within. With that, I'm having 3 big announcements to make today. One is a major architecture change in the form of a new GNN engine, which we call PyGlib. And PyGlib is actually an effort across many different partners. And it's great to see all these collaborations come together in this great project. And then we're talking about new optimizations. We have improved our GNN model design by making aggregations a first-class citizen in PyG. And we're constantly working on improving scalability, and we show that today with our pluggable graph backend support to seamlessly scale PyG beyond single node and in-memory datasets. So let's take first a look at PyGlib. So previously, PyG, or PyTorch was designed to use PyTorch, and then we added our own extensions to it called TorchScatter and TorchSparse, which provide the necessary tools for scattered aggregations or sparse matrix features. So the PyTorch team is now heavily investigating integrating TorchScatter and TorchSparse into PyTorch core, which makes these libraries somewhat redundant. And so our solution to that is that we're now introducing a new library called PyGlib, which is solely designed for optimizing all the graph-specific routines that we need in PyG. PyGlib is fully open sourced on GitHub, and it's actually a joint effort of both Kumo, NVIDIA, and Intel. In fact, it accelerates graph sampling routines, so it implements all the different kinds of mini-batch loading techniques that we need in PyG. It also accelerates heterogeneous GNNs. And it will accelerate, we haven't integrated that, but it's planned to release that in November, sparse aggregations. And just by installing PyGlib, you will see major speedups with like no line of code change, which is really exciting to see. So just to give you a sense of what I mean, so in PyG 2.0, we integrated heterogeneous graphs and GNN support to PyG. So that means that we have functionality for storing heterogeneous graphs in an in-memory storage. We added graph samplers and GNN layers to it that naturally can work on heterogeneous graphs. And the main feature we introduced was our toHetero model function, which is like a function that transforms a homogeneous GNNs and makes it applicable to heterogeneous graphs. And so you can think of it of a principled way to bring the recent advancements of GNN designed or researched to heterogeneous graphs right away. And that hetero function works as follows. So for each edge type in our heterogeneous graph, we duplicate the message passing modules, and then we're applying the GNN layer of the original homogeneous graph for each edge type sequentially. After that, we aggregate all the output embeddings that point to the same destination node type into a single node embedding that we use for the next layer. So that function here is super powerful and super flexible, but it also lacks parallelism, since due to the sequential computation its sequential computation of computing all these message parallels, message passing steps sequentially over each edge type. And so we now found a better way to do that, and we integrated that into PyGlib. And PyGlib now supports parallel type-dependent transformation via NVIDIA Cutlass integration. And that means that we can easily transform all the different features of different types using different transformations, but it happens all in parallel. And so that scheme is super flexible since it allows us to implement most of the heterogeneous GNNs with it. And it's super efficient, especially on sparse edge types with only a minor number of edges. And it scales well to a large number of different node types, which is not the case for our 2-hetero function. And so just by looking at the figure on the right, we see major speedups by just installing pyglib, and it scales naturally well to a large number of node types. More of that will be introduced in our Accelerating PyG with NVIDIA talk. Next, I also want to showcase how we accelerated graph samplers in PyG. So what we did was we used the initial implementation of neighbor sampling in PyG and improved it heavily by adding a variety of techniques to it. What we did was pre-allocation of random numbers so that random number generation is no longer a bottleneck. And we improved the mapping from global source indices to local ones, which is necessary to create the desired subgraphs for the mini-batch routines. And we do that via 2 ways. First, we integrated a faster hash map implementation, and for nodes that only and for node types that only contain a small number of nodes, we used vector-based mapping instead, which improved the performance quite a bit. And so just by looking at the figure on the right, we now obtain 10 to 15 times the speedups of the original implementation. And more of that will be introduced in the Accelerating PyG with Intel CPU talk later in the day. So that concludes pyglib. It is fully open source, and we release it we release it officially in our PyG 2.2 release, where it's coming in November. But we also provide nightly wheels, and you can just try it out, and it already works as expected. Next, I also want to talk about the optimizations we have integrated into PyG. One of them is the improved GNN design that now uses principled aggregations as first-class citizen. To motivate that, we see that the choice of neighborhood aggregation is actually a central topic in GraphML research. And what I mean by that is that we see research regarding what aggregations we actually want to use and how we can improve performance. So we see that different aggregations yield different expressivity, and they are actually different capabilities and what they can actually aggregate. So for example, we want to use some aggregation if we want to learn about structural properties, but we want to use mean or max aggregation if we are more interested in the local view or surrounding of the features. We see applications of combining multiple aggregators together and scale them appropriately according to node degree, and that can actually boost performance as well. And we see applications of learnable aggregations in the sense that we can, for example, learn the temperature value of a softmax aggregation that can seamlessly blend between min, max, or mean aggregation. Importantly, the choice of aggregation can have like a drastic effect on model performance, and so it's always good to try out different aggregators to achieve the best result for a given task. That motivates the usage or the introduction of aggregations as a first-class principle in PyG. And so aggregations now move from a hidden concept within the message passing class to a central concept and module or sub-package within PyG. So all these aggregations are now actually a module, and you can use them within message passing or also as global readout layers. Importantly, we added most of the aggregations that actually were used in research over the years. So we provide simple aggregations such as mean, sum, and max, but we also provide more advanced ones such as median aggregations, and these all naturally can operate on sparse input data. Then we integrated learnable aggregations, as previously mentioned, like softmax aggregation or power mean aggregation. And then we also have support for more, how I call them, more exotic ones, such as LSTM aggregation, which takes in the sequence of neighborhoods and processes them using an LSTM, or some form of sort aggregation, which sorts the neighborhoods according to their features. Importantly, all these aggregations are fully customizable, and you can combine them and use them within message passing or use for global pooling. And so the interface stays the same, but we can make them applicable to all these different steps in our GNN pipeline. Importantly, we can also combine them. That means that just by simply adding them as a list, we actually apply them together and concatenate the results to improve the performance here. Also, aggregations will pick up the best format to accelerate computations, and there is further optimization possible, for example, via fusion, in the sense that we can minimize the I/O from global memory by just performing the aggregations in parallel. But that is still like a to be done. I also want to quickly highlight the different flavors of how we can actually implement aggregations in PyG. So PyG first started in its first release with this well-known gather and scatter approach. And that gather and scatter approach maps the source and destination node features into edge level space. And that means that we actually materialize this big edge level tensor. We can then, in parallel, compute the messages on these edge level representations and scatter them back or aggregate them back to the destination nodes using atomic operations. And so that scheme here is super flexible, and it actually allows us to implement any GNN proposed in research. It's also super fast for sparse graphs, but there will be bottlenecks once you go to more denser graphs, because like this, there will be a memory bottleneck by materializing this edge tensor representation. As a result, we also integrated sparse matrix multiplication support into PyG. And so most, or not most, but some of the GNN instantiations can actually be expressed using matrix multiplication. That means that we no longer need this edge level tensor here, and the memory complexity stays with the number of nodes. But it's also not applicable to any GNN instantiation. And so we use this sparse matrix multiplication whenever there exists a GNN operator that can make use of that. With PyG 2.1, we also integrated the, how I call it, degree bucketing approach, which pets the neighborhoods of graphs to equal size by filling them with 0, and then you can actually make use of dense aggregations to perform the final neighborhood aggregation. Importantly, that will lead to memory efficiencies, because you actually need to pad the neighborhoods with dummy nodes, and it will actually potentially to a sequential iteration whenever you want to bin the degrees into different groups. But importantly, it actually allows us to apply any dense aggregation here, for example, LSTM aggregation or sort aggregation. With PyG 2.2, we thought of a fourth way to implement aggregation, and that is how I call it, like an individual kernel. And that means that GNN instantiations that have been proven to be successful deserve their own fast implementation. And that means that, for example, for graph attention, we can write our own CUDA kernel or own CPU implementation to make it as memory efficient and as fast as it can be. But as a downside, this implementation will not scale to any GNN layer, and so it's only applicable to individual ones. And we will release that as part of PyG 2.2. Furthermore, I want to talk about improved scalability and pluggable graph backend support. And I'm happy to announce, I'm sorry for taking it so long, that PyG now heavily simplifies the implementation of scalable link prediction tasks. So on the left, you see the original implementation of a link prediction model in PyG. And that means that we're taking a data set, and we split the data set or the edges there into edges that are used for message passing, which we call edge index, and edges that are then used for supervision, which we call edge label index. And then we have a model that encodes the node features in our graph using a GNN. And then we have a decoder that tries to predict the existence of an edge in our supervision edges. And that scheme only worked in full batch mode, so it's not scalable at all. With PyG 2.1, we introduced the linked neighbor loader. And so only minor changes are required to actually auto-scale your link prediction model to large data sets. So as you see on the right, on the left, you only introduce this new linked neighbor loader, and then the training procedure will just move to the for loop, and that will scale better to large graphs. Internally, this sampler will sample subgraphs from both endpoints and then fuses them together into the desired mini-batch output. Furthermore, I'm excited to announce that we are working on out-of-memory and distributed backend support. And so previously, PyG was limited to single-node in-memory data sets. With PyG 2.2, we are aiming to change that in the sense that we now provide support for feature store and graph store abstractions to plug in actually any backend you can think of. So first of all, we are disentangling feature fetching from graph sampling routines, which allows us to even think about having these different components be run on different machines. And we can also think about moving the entire feature fetching and graph sampling routines to different machines so that we can split them in machines that are responsible for sampling and machines that are responsible for computing or running the GNN. The interfaces then just work by, for example, the feature store interface is then just responsible for fetching the features of the nodes that we actually sampled, and the graph store implementation then takes care of either sample from nodes for a node prediction task or sampling from edges from a link prediction task. And just by implementing these different interfaces, you can think about, for example, the usage of out-of-memory backends, for example, using memory mapped I/O or by connecting to graph databases. And I'm excited, and I really will enjoy this talk that introduces that in more detail later. Additional highlights I quickly want to go over are automatic mixed precision support, which boosts the performance of GNNs even further. We additionally introduced temporal graph samplers in the sense that neighborhood sampling now ensures that temporal constraints are fulfilled in the sense that we do not want to sample neighbors that are actually part of the future. We improved heavily on our explainability methods by seamlessly integrating into the Captum library, which means that you can now easily explain GNN model predictions across any GNN model, any data set, and any task out of the box. And lastly, we introduced new model milestones in the sense of training really deep GNNs with more than thousands of layers, GNNs on heterophily graphs, and many more, and you are invited to check out the release notes to stay up to date. With that, I conclude my talk. So PyG bundles the state-of-the-art in graph representation learning, and it's exciting to see that this project moves from a single-person project into a collaboration that is now maintained by different partners around the globe. And so we have collaborations with Stanford, TU Dortmund University, Kumo, NVIDIA, and Intel, and all are working on making this project actually better. So if you haven't tried it out yet, please feel free to do so and give feedback as much as possible. You can always reach out on Slack or on GitHub to improve it, and it's always invited to send out pull requests to improve it on your own. So thanks for the attention.
Great. So thank you, Matthias. Next, we have Ivailo Bacevano. He's a community manager for the PyG community, and he's going to talk about what we are going to do and what our plans are to make the community even more vibrant, and how we are going to scale up the contributions and the PyG project in the future.
Thank you. Hey everyone, so my name is Ivailo. I'm the product manager for PyG. So my job is to make sure that the PyG community can work together effectively to build new products, and so that everyone can take advantage of what's out there. The goal for the community is to create an environment that's both highly collaborative and highly transparent so that everyone can see what everyone else is working on. The goal of my talk is to make sure that people are aware of what's out there and what's coming so that that can happen. So I'm excited to share some of those things with you today. You've heard a lot of things, a lot of new exciting updates, and you're going to continue to hear a lot of new exciting updates. But what we want to do is make sure that you guys are all involved in the building. So just kind of taking a look back at the PyG community, just looking at the GitHub metrics alone, you can see it's an extremely widely used community. PyG has been predominantly showing up in new research, and anytime data can be represented as a graph, PyG has been a great tool for the job. You can see people are actively contributing and building new features. By design, as you've heard, it's an extremely flexible framework so that people can build for any specific use case they might have. So I left a quote here by the Airbus team as they were building for a number of different applications because I think it does a good job of capturing its use. So I'll read it right now. GNNs provide a natural extension to consider our network's topology, and heterogeneous learning allows me to model complex and dynamic systems. I chose PyG for my application because of its ease of use, community, and features. So just wanted to quickly touch on some of the very common use cases we've seen PyG in production today. And this is both across leading research and in industry. From a financial transactions perspective, it's very easy to build a graph to represent financial entities and model their interactions. A lot of use cases come in the form of risk and fraud detection using anomaly and outlier detection, validating transactions, and also validating smart contracts on existing blockchain. From a security perspective, it's commonly used to identify compromised systems and network intrusion, along with any risk of fraud. Personalization and recommendation, so anytime you want to recommend content, advertisements, music, audio, and then predicting the next best purchase for someone. Knowing your customer, you'll hear more about this today as well, but understanding customer loyalty and retention, predicting churn and the lifetime value of your customers. In manufacturing, anomaly detection can also be in the form of predictive maintenance. And biology is another big one too. Being able to build knowledge graphs to model cellular and molecular systems so that you can understand what drugs will solve what problems, what the treatments are, and what side effects might exist. These are just some of the many logos that use and trust PyG today. So as you can see, there's a pretty established and growing ecosystem. So here are just some of the many examples. There's many more that aren't listed here. But they all fall under one of several categories. One category is building better performance and scale in whatever networks you may build. So making it run on many machines, making it run on different kinds of machines, making it run quicker. Another is having specific models and algorithms for handling very specific and niche tasks. And then others provide support for new raw data types and structures so that you can pull more use cases into graph learning. So just to list off a few examples, PyTorch Geometric Temporal is the most popular framework built on top of PyG for learning spatiotemporal signals. So that's more specifically building graph networks that work across both space and time. So you can think of demand forecasting, supply chain optimization, weather forecasting, anything that involves complex movements through space and time. Dig, or dive into graphs, is an algorithmic toolbox. So it provides things like graph generation, self-supervised learning on graphs, explainability, 3D deep learning. PyGod is PyG for outlier detection. So that's an algorithmic toolbox for detecting any kind of outliers or anomalies. So everything from security networks, social network abuse prediction, predictive maintenance, and risk and fraud. Quiver is useful for scaling PyG across many CPUs and GPUs to provide high performance and scalability. And Graphene produces geometric representations of proteins and RNA signals to make it easy to interpret. So how can you plug into the PyG community today? The first starting point we always direct people is our Slack channel. That we want to make our core collaboration hub. Our core team has already been there and helping answer questions, but we're going to be doing a lot of things with the Slack channel to make it much more adhesive to finding the right thing you want to work on, finding the right way to ask your question and get your questions answered. So we want to use it as a Q&A forum, and we also want to make sure that you guys are using it as a means for seeing what other people are working on and meeting other people. So we encourage people to introduce themselves there, to showcase the work that they're doing. We're going to have dedicated channels for each feature and each major roadmap, so that way people can collaborate on a per feature or roadmap or application basis. We're going to also have monthly town halls, the first one coming up on October 12th. So what this is it's going to be a monthly showcase to basically give you a rundown of what's the latest functionality, what's the latest successful use cases that have incorporated graphs, and video tutorials of new functionality. So it's an opportunity to see live demos of what people are working on, and also a spotlight session for any new contributors. So if there are things you're working on that you would like to present, please reach out to us directly. We've listed out a few examples of things you'll see soon, but things like leading manufacturing company detecting security threats and preventing risk, biotech company using drug discovery, and message passing, building your own feature and graph store implementations. Similarly, we'll have a newsletter. It'll showcase pretty similar stuff, primarily tutorials and guides for using new features. You can subscribe. You'll get an announcement in the PyG Slack channel. And as always, you can reach out to us if you want to contribute. The other thing we're doing is community-led sprints. So these are engineering organized sprints led by the PyG team as a means for getting everyone involved on specific features. So how they're going to work, we'll have a kickoff meeting where we'll do the overview for the feature, provide an opportunity to ask Q&A, kick off a 2-week sprint, and then at the end, we'll have a delivery meeting for demo, Q&A, and potentially kicking off the next sprint. So the first one happens October 10th. Announcement will be in the Slack channel. A couple other things that are out there that we encourage folks to use. So Open Graph Benchmark is a great way to benchmark your performance when you want to build something new for a given application. So there's a leaderboard for industry benchmarks and data sets. The data loader handles the download and pre-process, and it handles the standardization for evaluators. That way you can see how effective your new model or new approach is. We'll also be releasing data challenges on the Slack channel for specific problems. GraphRamX, similar concept, but applied to explainability. So we have a framework built around evaluation and evaluating evaluation. So the core PyG team, along with some folks from research, have built a framework to give you a comprehensive set of tools to help you with evaluation. The goal is to create a systematic approach for evaluating and the central library for you to use different methods. So you can evaluate with a comprehensive set of metrics and then submit your own evaluation metric and see how it compares to a leaderboard. And finally, there's what we have a public roadmap in GitHub. So it's a public roadmap which we'll use for tracking new features that we release. So you can see the status of new features and when they'll be released. But in addition, we can track features that we want community support on. So there's a column for looking for community support. So we encourage you guys to check those out. We have a few of them in there today, including some leading integrations with some of the leading frameworks. And then finally, we have a feature request column where you can submit functionality suggestions that you feel are missing from PyG. So we also encourage people to look at the existing issues for things that they can contribute on. And so just to name a few top themes on areas that we want to work on. Scalability, so being able to have new feature and graph store abstractions and new backends so that you can scale out your graph. Performance, we'll have a public roadmap which includes some of our collaboration with Intel and NVIDIA, which will showcase a lot of the operations that are sped up. Deployment, making it super easy to get up and running in PyG. New algorithms, models, integrations, and then explainability, so new ways of providing explainable results in a common interface. And yeah, that's everything so far. Thank you, and definitely reach out if you want to get involved, and stay tuned on Slack for any new announcements. Thank you.
don't think it's picking it up. Oh, there we go. It's picking it up. Is that working?
Okay.
Yeah, it's not.
Okay, so thank you, Ivailo. We continue the program with a talk by Manan Shah, who's a founding engineer at Kumo AI. And he will talk about some lessons learned as well as new interfaces that have been pushed to the PyG to scale it up to the large-scale data. Manan, the floor is yours.
Cool. So today we're going to be spending a little bit of time discussing the new feature store and graph store abstractions that Matthias mentioned a bit earlier, and in particular how you might use these abstractions to scale PyG up to very massive data sets and massive graphs. So this is a talk by Dong and myself. Dong is also an engineer at Kumo AI, and both of us will be discussing how we, at Kumo, where we think a lot about how to scale up large-scale graphs and to work on graph neural networks on massive large-scale data warehouses, and how we leverage a lot of the PyG infrastructure that we're building and pushing back into PyG to enable a lot of this effort. So the talk will have two major parts, the first of which will discuss the abstractions that were introduced before and how to kind of integrate your own custom feature store and graph stores to scale up PyG. And the second part will discuss how at Kumo, we have leveraged a lot of interesting techniques to kind of get the scale working with high enough throughput for training to be quite reasonable. So maybe to start off with the brief architectural blueprint of how graph learning works, graph neural networks operate on a very simple data model. They support a graph with nodes and edges and features, which are tensors for the elements in the graph. Message passing in graph neural networks operates with a relatively straightforward gather-scatter paradigm between node space and edge space, where features from node space are propagated to edge space, aggregated, and written back to node space in each message passing step. Full batch training is maybe the most simple way to think about graph neural network training, where you take the entire graph, the features for that graph, and transfer that to the GPU to perform forward-backward, update weights, and repeat this process multiple times for some number of iterations. However, for a graph of any reasonable size or complexity or feature size, it's quite difficult to do this because GPU VRAM is quite constrained compared to CPU DRAM. So it can be quite challenging to transfer the entire graph over to the GPU to do forward-backward. So the natural extension to support some sort of scalable graph learning is to use sampled subgraphs and do forward-backward passes on sampled subgraphs instead of the entire graph. What this actually means in practice is that you would take a graph, sample subgraphs starting from some root nodes that you are trying to sample from, take the subgraphs in some sort of a mini batch, and then run forward-backward on the sampled subgraphs instead of the entire full graph. While this adds stochasticity to the overall model training process, it does indeed reduce GPU memory requirements of the overall training pipeline and does get us somewhere in the realm of scalability. So at right, you can see a figure where we first have our graph and features that are stored together in CPU DRAM, and then we have sampled subgraphs that are processed by any sort of graph learning framework, in particular PyG, that are stored in GPU VRAM and then have forward-backward passes conducted on them. However, oftentimes, this is not simply enough. While training on sampled subgraphs is great, it can be quite challenging to live within the restriction that the entire graph and all of its features must fit within CPU DRAM. In particular, there are a few situations in which this can be quite challenging. The first is that, as many of you may know, acquiring an instance that has a lot of CPU DRAM and attached GPUs can be very expensive. It's not very easy to get a huge instance with one GPU. In fact, many times you'll end up with multiple GPUs that you might not know how to use very effectively, and oftentimes this is very expensive of a process. Second, if you want to engage in some sort of data parallel training, this means that each of your compute nodes that are running the forward-backward passes must store the entire graph and all of the graph's features together. This can be a problem as well because you don't want to incur the latency of replicating the graph and all of the features among each compute node. And finally, and probably most importantly, beyond a certain graph or feature size, it's simply impossible to assume that that graph and all of its features will fit within the memory of a single machine. You might have a graph database storing your graphs, a key value store storing your features, and it can become quite challenging to have to copy all of that into CPU DRAM and work with the machine that has those kinds of requirements to conduct graph learning. So, scalability to large graphs and features often requires moving these data structures, in particular the graph and the feature store, out of core and only processing sampled subgraphs on the compute node. This reduces the memory requirements of your compute node to that of the mini batch that it's currently processing, which is in reality all that we should care about. The graph and its features should be able to be stored wherever, and all PyG or a compute engine needs to know is what it needs to process at its current moment. So you can imagine then that features are now stored in some sort of an abstract key value store with replication or partitioning as implementation details. And the graph information is stored in some sort of a graph store with, again, replication and partitioning being implementation details. And this is all good in the abstract, but it's important that any sort of graph learning framework defines a clean and easy-to-use interface on top of these abstractions to make it clear how to leverage these abstractions and how to use them downstream. So in the rest of this talk, we'll kind of discuss how PyG enables this and allows us to get to what we call independent scale-out, where PyG is no longer constrained to single-node in-memory datasets, but rather can support graph and feature stores behind any implementation that you might desire that are independently partitioned, replicated, and stored in some sort of optimized formats. So at right, you can kind of see the vision that we're looking for here, where we have a graph that is stored in a graph store that has nodes and edges, and basically the edge index that you use in PyG. And at right, you can see the feature store, which is very simply a key value store of node IDs to some sort of feature tensors that represent the features corresponding to that node. The sampled subgraphs are computed within PyG by sampling from the graph store and joining samples with features that are relevant from the feature store. So again, each training node now only requires enough memory to store the sample data that it cares about. At right, now you can see what these abstractions look like with PyG terminology. So the graph store stores edge index tensors. The feature stores any node and edge attributes that you might append to those nodes or edges. So for example, X, Y, or edge attributes, things like this. And the training instance that PyG deals with is the same object that you've always worked with, the data or header data object that PyG knows how to work with for forward-backward. This architecture that we propose is extensible, generalizable, and has a native PyG integration, and hopefully is very simple and straightforward to use with a variety of different graph databases and feature stores. So now we'll dive a bit more closely into the PyG particular part of this talk. How do we define these abstractions within PyG? How can users extend these abstractions to their own implementation? And how does it all work together under the hood for an effective architectural blueprint? There are 4 key abstractions here that enable the kind of effort that we are looking for: the feature store, the graph store, the graph sampler, and the data loader. The data loader is at the crux of this operation. It orchestrates feature fetching and sampled subgraph generation by querying different relevant stores. So you can see at the very bottom, at a high level, the data loader queries the graph store through the graph sampler for a graph sample given certain root nodes and sample parameters. The graph store is expected to respond with sampled nodes, which are then forwarded by the loader to the feature store to join it with relevant features for those nodes and produce mini batches that PyG cares about for forward-backward. So let's now dive a little bit more closely into what this actually means for each component of this architecture. The graph store stores the graph edge indices in a manner that is conducive to edge index efficient sampling. This is pretty crucial. Sampling can often be a pretty important bottleneck in forward-backward passes when working with large-scale graph neural networks. So it's important that this graph store supports very efficient graph sampling given its representation. Now, the representation that is actually used in the graph store, whether it's some sort of graph database like Neo4j, whether it's an in-memory graph store that just operates on CSR edge tensors, or something else entirely, is completely irrelevant to the actual abstraction and how PyG interacts with the graph store. All that we care about is that you support effective or efficient get and put and sample-specific operations to make sure that training throughput proceeds as expected. The graph sampler operates on top of a graph store to sample a subgraph from root nodes and related parameters. This means that it implements logic to sample from a graph store by calling sample-specific operations that the graph store might provide. In particular, PyG does not define a domain-specific language, or a DSL, for the graph sampling procedure. That is, we don't expect the graph store to abide by some vertex-centric or edge-centric paradigm just yet. Rather, all we expect is that the graph store and sampler are tightly coupled, so the sampler knows how to sample on the graph store, and the graph store provides whatever arbitrary operation that is required to enable this efficient sampling. The physical location, replication, partitioning, and other implementation details of the graph store are not worries of PyG and are implementation details that are left to the graph store implementer. For example, you can imagine a graph store that is implemented by pre-partitioning a graph, for example with Metis, a graph store that just stores sampled subgraphs themselves and doesn't even store the entire graph, just these sampled subgraphs that are leveraged by PyG, or something else entirely. And as long as the graph store provides us with these sample functions, the rest of PyG will work as intended. The feature store is the next major abstraction that is worth discussing, and its goal is to store features for the nodes and edges in a graph. Feature storage is often a primary storage bottleneck in graph learning applications, as storing a graph edge index in the general case is relatively cheap. For the storage of an edge index in a sparse graph, all you really have to store are the source and destination node IDs. But storing features can become arbitrarily complicated if you support large-scale feature tensors, for example, for any of the given nodes or edges. So a feature store also obviously requires basic CRUD operations, so create, read, update, and delete, just so users can interface with the feature store. But very crucially, it requires an efficient random access get operation. This is because in PyG's use of a feature store, we need to join the sampled subgraph with features from the feature store, which amounts to a random access query on the feature store. There are optimizations we can do here, and Dong will discuss those in the latter half of this talk. But the general idea is that the feature store should support fast enough get that feature fetch throughput is not a bottleneck for overall training throughput. Like the graph store, implementation details of the feature store, for example, if you use a general key value store, replication and partitioning here are very relevant as well, are abstracted from PyG behind the common interface that we develop and design. And finally, the most interesting component here is the PyG data loader, which is built upon a sampler, a graph store, and a feature store. It does three major things. It generates a batch of input nodes and requests sampled subgraphs from the sampler. The sampler responds with the sampled subgraphs that are rooted at each of the input nodes in that batch. It then collates all of the sampled nodes and requests associated node and edge features from the feature store that correspond to the nodes in the sampled subgraphs. Finally, it constructs PyG native data objects from these data and performs forward-backward computations and weight updates. All of this is invisible to the user. As long as the user defines the right interfaces and the interfaces are implemented correctly, the data loader handles all of this communication and computation perfectly, and it is PyG's job to handle the overlapping of communication and computation effectively to ensure that we can achieve maximum training throughput. Additionally, other details like multi-process data loading, prefetching at the data loader stage, and communication are all handled by PyG. End users only need to care about the data loader, and as long as feature stores and graph stores are defined properly, we should be good to go. So now let's talk about putting it all together into the PyG implementation. This is all features that will become visible in PyG 2.2, but if you pull PyG latest master, you can start working with these today, and you can give us any feedback. Any and all feedback is appreciated. The current interface looks very similar to the PyG data and header data objects that folks have already worked with. Here you can define, for example, my feature store is a custom imagined implementation of a feature store behind the feature store abstraction. Here we add paper features and author features to the feature store with simple syntactic sugar that we provide on PyG's side, which makes this type of setting, getting, or modifying of node features quite easy to use and quite simple for native Python users. Now internally, of course, there might be a lot of things going on behind the scenes that we obscure to the user. Put tensor might be an RPC call that stores data remotely. Put tensor might do nothing, and you might pre-insert all of your features into the feature store ahead of time. That's all fine. So long as we can define the abstractions properly, PyG will kind of overlay on top of that the syntactic sugar that makes it simple to integrate with PyG, and users don't have to know about any of these implementation details unless they care about performance. For the graph store, we have a very similar interface where my graph store, again, is an imagined implementation of the graph store interface. It supports two different kinds of edge indices. Here, in this case, we add the paper-to-author edge index and the paper-to-paper edge index in COO format, so it's 2 by n, where n is the number of edges in each of these edge indices. And we put the edge index with a very simple operation that just tells the graph store what is the format that you're receiving the edge index in, what is the edge type if the graph is heterogeneous, and what is the actual edge index. Again, storage format, partitioning, etc. are all implemented on the graph store side, and PyG provides this interface that allows for easy integration with custom graph stores. So adding edges is really just as simple as adding features, and we also provide syntactic sugar to make this simple as well. And finally, training brings everything together. The node loader is the abstraction here that manages sampling with a custom sampler, communication with the feature and graph store, and other implementation details. Here you can see where we've defined our feature and graph store, and also a sampler that operates on the graph store and has any sample-specific parameters. So here we've defined and imagined my graph sampler that uses some sort of neighbor sampling routine on top of the graph store. And we've told the graph sampler to sample 10 neighbors from the first hop and 20 from the second hop. We then define a node loader on the data, which is a tuple of a feature and graph store, a graph sampler, and any additional data loading parameters that might be useful. And then everything after that is just as if that loader was implemented in memory. The batches in the loader are batches that are computed in PyG, and the data are data or header data objects, depending on whether your graph is heterogeneous or homogeneous. And forward, backward, and everything else can be implemented ignoring all of the above code and assuming that it all has been done in memory. So as a final summary of what these abstractions provide and kind of where we're looking to go, PyG's remote backend abstractions make working with the distributed feature store and graph store no different from single node modeling. It's easy to store a graph and features out of core and to switch between in-memory and remote representations because the data and header data objects in PyG that are currently only in memory they also subclass the feature store and graph store abstractions. That means that you can use the same APIs with the feature and graph store as you can with a data or header data object. These abstractions also make a wide variety of extensions to PyG very simple and straightforward. If you want to, for example, integrate ahead of time sampling, where you pre-generate your sampled subgraphs, that's totally fine. Make that a graph store and just read from those pre-generated subgraphs as part of your graph store implementation. And if you want multi-node DDP without data replication, that works as well. You define your feature store and graph store and have your multiple nodes communicate with the feature and graph store instead of replicating your data amongst each node. And there are other axes of parallelism, basically any sorts of tensor parallelism on any dimension to avoid, if you wanted to avoid any sorts of data replication, we can support this natively with the feature store and graph store. However, it's important to note that performance here is absolutely critical. You'll need to monitor the throughputs of feature fetching, sampling, and forward-backward when looking for bottlenecks to make sure that you're not bottlenecked by graph sampling or by feature fetching when these things are remote. I'll now turn to Dong, where we'll discuss a lot of these interesting ways that at Kumo AI we've leveraged techniques that make feature fetching and sampling doable at large scale. So take it away.
Hello, everyone. Thanks, Manuel, for the awesome talk about the graph store and feature store interface. My name is Dong. I'm working on the machine learning platform at Kumo AI, and I'm going to talk about how we build a feature and graph store at scale and how we optimize it. So to handle to scale graph neural network models for large graph is challenging because real-world graphs and features cannot easily fit into memory. And also, people will try different graph sampling algorithms, which makes supporting very, very complex. And to optimize the graph store, we want to optimize its latency for the graph sampling. We also want to make it flexible to try different algorithms. Some people may try like breadth-first search. Some people may try random walk. And for the feature store, we want to support very high data volume and also high data throughput. To achieve this goal, we build a combination of in-memory graph store and on-disk RocksDB-based feature store as our feature store and graph store implementation. The in-memory graph store supports fast access to different nodes and also random lookup at neighbors. And the on-disk feature store gave us much higher data volume support and also very high data throughput. So to make the on-disk feature store high throughput is also a very complex task. Here I want to highlight a few optimizations we did to make it perform. So we store features in the protobuf format. For people who are familiar with TensorFlow examples, the features for a node can be viewed as a list of individual feature message, which contains a name and a value. It is not very storage friendly because we are duplicating feature names for every node. And also the data in memory is not well aligned. So we decided to separate a feature configuration file, and then we can store the actual feature format in a more compact form, where we store the feature with the same type in a very compact array. This gives us about 2x optimization for the storage and also a huge speed up for feature deserialization and feature conversion. We designed the graph store and the feature store as a service so that we can easily find machines that optimize for memory and storage as our data server to store the graph and the feature, and also machines with accelerators as our compute client who can handle training and inference. The server and the client communicate via protobuf and gRPC. So the client will receive the features in the protobuf format, which is optimized for the row-wise feature representation. And we want to convert it to the column-wise feature representation in order to do different kind of feature transformation, feature encoding for different column of features. Here we utilize Arrow to help us achieve the zero copy, in-memory zero copy design, and also help us to support different languages. We carefully handle RNA values to avoid unnecessary data copy. And all the server code and client code are written in C++ to achieve the best performance. And another thing about improving the feature store throughput is to improving the data locality so that we can access as many features as possible with one disk read operation. Here we use a very simple idea. We try to reorder features based on its neighbors. In this example, we try to group triangle nodes as close as possible if they share the same circle node neighbors. And then we try to group square node as close as possible if they share the same triangle neighbors. This simple optimization works very well for a lot of real-world applications. So this is the last part. I want to share some benchmark result. On the left side is the speed up we get for feature deserialization and feature conversion. With a more compact portal bar format, we are able to 3x speed up the feature deserialization and conversion. And on the right side is the throughput versus the normalized data size. The x-axis is the data size normalized by the single machine memory limit. As you can see, the blue line is our optimized version with data locality. It consistently performs twice as better compared with the basic approach. And we are able to fully utilize the GPU with on-disk feature storage. So that's it for this talk. Thank you for listening, and also thanks Core PyG team for the awesome interface.
Thank you, Dong. This concludes the first morning session. We are going to take a half-an-hour break. There is coffee and some food outside, I think. And we are going to continue at 11 a.m. Pacific time with the next series of talks around scaling things up, as well as recommender system applications and so on. So thank you. We have a half-an-hour break, start at 11 a.m. Pacific time. Hi, Nishi, right?
Yeah,
Yes,
nice to
okay,
meet
great.
you.
Super excited about your
Yeah.
talk. You are ready.
Yeah.
You
I
have
just
an
need a
amazing
plug.
power adapter.
Yeah,
You
yeah.
can kill a cow with this or something. Super.
Yeah, it's huge. This
This
is the
one
only
doesn't
way I
work?
can do. Oh, actually, yeah, that works perfect. Well, let me try it. Oh, I don't know. It is the Apple one, so I don't know. They might not like Windows. Oh, yeah, okay, perfect.
And you
I'll
can
make it
set the-
extendable, yeah.
Are you the first now?
Yeah, yeah, I'm
Okay,
up
so-
next, yeah.
Great. I'll introduce you briefly, and then you can go. You have the time, so it will be
Awesome.
And
Thank-
don't rush it. Okay.
Thank you.
I'd like, you know, like an address. I wish we had better.
That provides
We have something called like the AI. I didn't know that is like a standard to get a PhD, you know, like it's the kind of like whatever you want. Sometimes people go get a PhD. But I think it would be kind of like better if it was Yeah, I've seen some of the colors there and but it's still. I mean, yeah, maybe I'm the right guy. I do a lot of distribution and yeah, so.
I mean, you know,
I mean, you know, let's say maybe, yeah, I mean, usually the money that come on the screen, you know,
You're on the PyTorch.
Yeah, PyTorch team.
team.
Yeah.
Okay, I'll say that. How are we on time? There is still 59, so it's okay.
1 minute.
Okay, so welcome back, everyone. I saw we had a good coffee break, a lot of lively discussions. Super awesome. So we are continuing now with the program. The first part of the next session will be about collaborations and scalability of PyG and new features. And then we are kind of going to transition into talking about applications and use cases of graph machine learning in various types of applications and domains. So to kick off this before lunch session, I'm excited to welcome Rishi Puri, who's on the PyTorch team at NVIDIA. And he's going to discuss NVIDIA's efforts and contributions into PyG to both allow us to scale it up, as well as improve efficiency of the execution. So thank you, Rishi.
Thank you very much for that introduction. So this presentation will go over the GPU accelerations coming to PyG as part of an ongoing collaboration between PyG and NVIDIA using the CUDA libraries Cutlass, cuGraph, and cuGraph Ops. First, we will go over NVIDIA's GNN API. After this, we will talk about how PyGlib provides low-level optimizations to accelerate PyG workflows with NVIDIA CUDA libraries. Working with GNNs comes with a unique set of challenges. First, GNN model training requires advanced systems knowledge in order to load large data sets, manage memory for graph structure data, and train in a distributed manner. Additionally, script-based GNN workflows are not flexible enough. Swapping data sets or models, even for similar tasks, requires a lot more effort than for computer vision or natural language processing. Torch Vision and Torch Text have enabled such flexibility in computer vision and NLP, which does not currently exist for GNNs. It also takes a tremendous amount of time to pre-process large data sets on CPU alone. Lastly, it takes significant additional effort in order to deploy a trained system. NVIDIA provides a flexible, easy-to-use, general API that allows for building end-to-end workflows, addressing the previously mentioned challenges. Automatic, accelerated system management reduces the need for systems knowledge. Our flexible API allows for switching between tasks, models, and data types with a few lines of code change. Rapid's GPU-optimized pre-processing cuts down pre-processing time for super large data sets from hours to minutes. The API also allows for deployment at the push of a button. This API was described in detail during the recent GTC Fall conference hosted by NVIDIA. PyGlib is a low-level library exposing optimized operations for use in PyG. cuGraphs provides GPU-accelerated, neighbor sampling-based data loading for large graphs. Many real-world applications require graphs that exceed the memory capacity of a single GPU. This requires subgraphs to be sampled via neighbor sampling as part of the training loop. Currently, the sampling is done entirely by the CPU, leaving room for acceleration with a GPU implementation. Cutlass grouped GEMM enables GPU-accelerated heterogeneous GNNs with a segment matmul used for a typed matrix multiply. Heterogeneous GNNs utilize layers with a linear weight for each node or edge type, iterating over them. Type matrix multiply allows us to parallelize over these types, addressing this bottleneck due to iterative computation. Additionally, cuGraph Ops integration for accelerated sparse aggregations is coming soon. Much of the computation for GNNs relies on sparse aggregations, which will have ample room for optimization. All of the mentioned optimizations are to be integrated into PyG to provide speedups with no lines of code change needed by a user. The Rapids cuGraph PyG ecosystem will support multi-node, multi-GPU using cuGraph or cuGraph service. Additionally, it will support segmented training and sampling across multiple GPUs. There will be support for massive scale, homogeneous, and heterogeneous graphs. cuGraph and cuGraph service will provide graph stores with no code change needed. This will all integrate with cuML and cuDF for faster pre-processing, training, and inference. The diagram shows a general pipeline in the NVIDIA PyG ecosystem. One option is to use cuGraph to directly manage node and edge data with cuGraph and cuDF. The other is to use cuGraph service. This provides additional flexibility with data stores and compute segmentation. Additionally, cuGraph service provides easy training and inference across multiple clients. Both options support using multiple GPUs for both homogeneous and heterogeneous graphs. Both of these options will rely on cuGraph's core algorithms. In either case, the graph and feature stores from either option integrate into PyG for effortless use with GNNs accelerated by Cutlass and cuGraph ops. Currently, the initial PyG wrappers have been merged into the latest cuGraph branch, 22.10. These wrappers can support both single and multi-GPU sampling. The current goal is to integrate accelerated GPU loading into native PyG. Part of this entails creating fast converters from sampled cuGraph data into native PyG heterodata objects. Along with these efforts, there is ongoing work on ensuring that cuGraph can scale to support massive heterogeneous graphs of over 1 billion edges. Additionally, cuGraph ops is in the process of integrating accelerated sparse aggregations into PyG. Additional effort is going into enabling easy multi-node, multi-GPU training. In this preliminary benchmark, we use cuGraph to accelerate sampling for 2-hop neighbor loading in the Microsoft Academic Graph dataset. In the left graph, we can see that CPU is much slower than the cuGraph's GPU implementation. In order to be able to see how GPU scales, we also graph the GPU time alone on the right graph, seen there. We will now discuss how Cutlass can be used to accelerate heterogeneous GNNs. When designing a heterogeneous GNN, one may want to apply a linear transformation separately to each node type. This is implemented in PyG as the heterolinear layer. The naive implementation essentially iterates over each node type and performs a matrix multiplication. This is inefficient as there is no parallelism over node types. We can remedy this inefficiency with Cutlass by parallelizing over these node types. We do this by using the Cutlass grouped GEMM kernel. By grouping together the node features of each node type in a single tensor, Cutlass allows us to apply separate matmuls to each segment of the total node feature tensor. This method remains highly efficient even with a large number of node types. In this benchmark, we use PyG's fake hetero dataset, which generates synthetic heterogeneous data. We do this to be able to scale the number of node types while holding the other parameters of graph generation constant. We graph the combined average time to compute the forward and backward pass of a heterolinear layer on the synthetic data. Our graphs show the clear benefit to parallelization. In the left graph, we see how CPUs are drastically slower than any GPU implementation. Since the CPU implementation is so much slower, we use the graph on the right to show the same numbers, specifically comparing the vanilla for-looped GPU matmul implementation to the PyGlib Cutlass implementation. In the zoomed view, we can see how PyGlib is so much faster than the vanilla GPU implementation, scaling far better. One of the most commonly used heterogeneous GNNs is the RGCN. In the naive implementation, we simply iterate over each edge type, filter the relevant edges, and multiply the aggregated result with the corresponding weight matrix. Finally, these intermediate outputs are summed up. This implementation is very flexible and can be used with any homogeneous GNN using the two-hetero function previously mentioned. It can even be used with a combination of different homogeneous GNN operators. However, this implementation scales poorly with the number of edge types due to its iterative nature. For our Cutlass-based RGCN, we use PyG's generic gather-scatter scheme to lift node features into a uniform edge-level space. We then compute the messages in parallel, and finally scatter-reduce back into a single node feature matrix. Using the same Cutlass-grouped GEMM as for heterolinear, but grouping by edge types this time, we can compute the messages per edge type in parallel. Because the gather-scatter scheme is generally supported by PyG, this implementation is flexible enough to support any heterogeneous GNN operator. This method is very efficient and scales well for heterogeneous graphs, even with sparse edge types or a large number of node or edge types. One key aspect of this efficiency is that for any given node type, computation is not wasted on nodes that are not related to said edge type. In this benchmark, we use the fake hetero dataset again, except this time we scale the number of edge types while holding the other parameters of graph generation constant. Again, we graph the combined average time to compute the forward and backward pass of an RGCN on the synthetic data. The graphs show the clear benefit to parallelization. In the left graph, we see how CPUs are drastically slower than any GPU implementation. Again, the zoomed view on the right showcases the speedup of PyGlib over the vanilla GPU implementation. In summary, NVIDIA provides an API for effortless GPU-accelerated GNN training and deployment. You can check out the NVIDIA GNN product page with the provided link. The API will be open sourced on GitHub towards the end of Q4. NVIDIA is also releasing an optimized PyG container that is performance-tuned and tested for NVIDIA GPUs, which is coming Q4. PyGlib uses cuGraph and Cutlass to enable further acceleration. Initial Cutlass integration is available in PyG 2.1 with additional accelerations coming soon. Thank you. That concludes this talk.
Sorry, go ahead. Thank you, Rishi. We are today running fast, which is very unusual for these types of events. So you can take time to go longer if you like, but don't. But I think nobody will mind if you start lunch sooner, so that's okay as well. So this is great. So thank you for the first interesting talk. Now we are Ke Ding is going to talk about the work that we are doing with Intel to improve the performance of PyG and GNN workloads on the CPU side. So this will also be, I think, very exciting talk with very interesting insights about how CPUs can really help with graph workloads. So okay, thank you.
Yeah, thank you, Yuri. And so we just heard like a great update from Rishi from NVIDIA's side, and now let's switch gear to talk about accelerating PyG with Intel CPU platforms. And my name is Kerr, and I'm a principal engineer at Intel Software and Advanced Technology Group, and working on AI and analytics. So this is my outline today. So I will first talk about Intel AI software stack in general, as well as zoom in the version for PyG at Intel platform. And the second part, I will talk about PyG optimization for Intel CPU, which is the most important part. And I will cover two major things. One is the message parsing, and the other is the mini-batch sampling. I will start with providing an analysis and then come up with the detailed optimizations, how we do that. And I will conclude my part with what's next, right? So some of the important features to be expected on the Intel side. Yeah, so talking about Intel, so people will say, oh, it's a CPU company, right? So Intel produce CPUs and for the client and for the IoT and for the data center. But in terms of AI and ML space, actually, we are doing much more than that, right? We have Xeon for the cloud and the data center, and we have cores, right? Core pipeline for our workstation, and we have XE graph, and for the data center GPUs, right? So for both training and inference, and we have VPU, Movidius VPU, and we have accelerator, and we also have Habana, right? So which you can see it is truly kind of an XPU story, right? So Intel's vision in this space is we want to provide a unified AI software stack, and mainly to support two things. One important thing is to deliver the performance, which means we want to optimize the performance of each of the underlying XPU hardwares, right? And the second thing is we want to deliver the productivity, right? So oftentimes performance is not enough, right? So how to make the software stack easy of use and make the bar lower enough so that everybody, like citizen data scientists, can use those things, right? Which is very, very important for us. So with that, so we can already do lots of things like data analytics at scale. So like modern, right? It's just a distributed version of pandas. And so we have optimized the framework and the middlewares, right? So like 1DN already becomes default for both TensorFlow and PyTorch. And we also have domain frameworks like in the GNN space, we support both PyG and the DGL, right? And so we also have the best machine learning platforms on Intel platforms. On the right side, so Intel also develop lots of tools, right, to optimize and deploy model easily, right? So we have SIGOPT for the hyperparameter optimization, so it is a hosted service. And we have OpenVINO, so you can write once and deploy anywhere, right? And we have a neural compressor, so that does quantization, pooling sparsity, and distillation. So those layers are very foundational, very fundamental, but it is not enough, right? So we are developing more features into the top of the stack. And so for example, many domain libraries like NLP, we are co-working with Hugging Face very closely, recommendation system, transfer learning, and we're also providing workflows, right? Workflows and the containers, and so that those things can be deployed in any of the cloud CSP environment as well as on-prem environment, right? So in summary, so Intel's AI software stack is kind of a multi-level, multi-tier kind of solution, right? Data plus AI kind of solution, and it is open, so meaning like it's all like we either contribute into open source project directly, or like the project Intel develop is open source, right? We welcome any contribution into those projects, and so with performance and with productivity in mind. Okay, now let's take a deeper view on the PyG on Intel platform. PyG is a super successful open source project, and so in the GNN space, it has those SOTA models and also many operators, right, to build up those models and the storage, so like data loader and many different samplers. To support this PyG infrastructure, so the first thing is PyTorch, right? So PyG being a PyTorch native kind of project, so it leverages lots of things from PyTorch directly, like optimizers, like lots of common performance primitives. And also there are these three libraries, so torch, scatter, sparse, and the cluster. Matthias already mentioned about that, so those are the like GN domain-specific performance libraries developed so for PyG, and now they are migrating into the new PyG-lib. Matthias already discussed about that. So on Intel platform, so supporting those things, the underlying thing is first thing is the 1DN to get the optimized performance for the dense computing, and then the 1CCL, right? So the same thing, but it's for the collective communication part, which is used in the distributed training space. And so we are co-working with PyG and co-working with Kuma very closely. And so our philosophy is open source first, right? And upstream first, right? And we want to contribute everything into PyTorch, into PyG. And we cover both inference and training, and we want to optimize those performance critical primitives into low-level libraries such as 1DN. Okay, so the first thing I want to talk about is the message passing, right? So it's critical, very important in the GNN space. So it's kind of a generalized term of the convolution. So in the graph space, right, which is like a convolution is very commonly used in the computer vision space. So it's actually very simple. So 3 steps: gather, apply, and scatter, right? So take this as example. So there are 4 nodes here, 1, 2, 3, right? If we want to do the message passing on node 4, the first step is we want to gather all the node features, right? So from 1 to 3, and then second step is apply. You want to apply a user-defined function, right? And the third step is the scatter. So you can do like min, max, or like sum, right? So such kind of thing. And so that's that. And so many of the commonly used GNN topologies, they all follow such kind of thing, right? So it's very important to understand the performance implications. So what are the bottlenecks, right? And how to optimize it. So with that, we did the profiling on the Intel CPU platform. So there are 2 cases. So the first case is edge indexes with a CO format, right? We benchmarked with the Sage model with a Reddit data set. So it shows the scatter reduce, right? So occupies almost half of the entire time. And so the case 2 is the edge index is in the CSR format. And so from here, so we also benchmarked, provided from a GCN network with OGBM product data set. So here it shows SPMM reduce is almost occupy everything. 90% of the CPU time is occupied by this one. So if you are in an optimization space, so this result actually is pretty good, which means you only need to focus on those top few functions, right, to do optimization. And instead of on the other side, if they are spread around, so it is very hard for you, and you need to spend lots of effort to optimize everything. So now let's take a further look on how to optimize it. So the scatter add is the first thing. So scatter add actually is pretty straightforward, right? So it's nothing but add all the values from the tensor source into self, right? And at the index specified in the middle index tensor, right? So in this simple example, so you add like source 1 plus source 2 plus source 6, right? And add them together and into self 1, right? And so here, like M refers to number of node, right? N refers to number of edges, and the K refers to number of features. And so these are kind of tall and skinny tensors, right? So because, for example, Reddit dataset, it's not very big, but take it as an example. So M means like 135K node, and N means like 447K edges, and then K is the feature dimension, it's like 256. So they are tall and skinny. And so clearly it's memory bandwidth bounded kind of functions. So another thing I also want to point out is, so there's possible write conflict, right? Since multiple threads, so they may attempt to write the same address, so simultaneously. So how to optimize it on Intel CPU platform? So actually it's also quite straightforward. So 2 things, one is parallelization, the other is vectorization, right? And so the way we do it is parallelize it on the outer dimension, right? So either M or N, and do the vectorization on the inner dimension, in the K dimension. And we also solve the write conflict through the index sourcing, like here in this case is radix sort. So with this optimization, and so we measure the performance on the Sage model on the Reddit dataset. So the scatter add time, so we have 5.9x speed up. So in the function level only, contribute from the end-to-end perspective, it is like a 1.7x speed up from the entire training, entire inference side. And so this algorithm actually is equivalent to like convert the CL format to the CSR format and do the sorting and then do the SPMM reduce operations. So now I will introduce the SPMM reduce. So again, so SPMM reduce is like the hot spot when the edge index is stored in the CSR format. So the API definition is very similar to like the SPMM in the PyTorch side, except that there's additional reduction type, right? Min and max. And so it's very similar like the scatter reduce case. It's memory bounded, and it's again tall and skinny sensors. Right? And one thing is so the number of non-zeros so refers to the number of edges, right? So in this end side. So the way we do the optimization is also similar. We do the parallelization, we do the vectorization. So we do, the first step here shows the vectorization along the inner dimension. So we got 1.9x speed up. And the second step is we do the unrolling. And along the inner dimension, we got 2.2x speed up. And then we do the blocking, and it is row-wise blocking to reduce the write memory access. And it is 2.6x. And finally, we do the balanced thread partitioning, right? And in total, we got function level for 4.7x, and from the entire inference level, 4.3x speed up. So one thing was mentioned is regarding the last thing, right? So balanced thread partitioning. We cannot assume like each node has the same number of connections, right? So that's why we want to parallelize it on the number of non-zero like edges instead of like those nodes. Because if it is node, then it's different workers, so we have unbalanced payload. Okay, now let's talk about the sampling, right? So here it says a larger graph requires no sampling and graph partitioning. So I believe this is everybody understands this in this workshop. So literally means on the right side, so you have many neighbors, but you only select a subset of your neighbors, right, to aggregate the features, right? So it's kind of the dropout layers we commonly use in the computer vision or other models. So it improves two things. One is the performance, of course, because you don't sample everything. And the second is oftentimes it improves the generalization of the model. And the PyG so implemented like many commonly used samplers in the PyG loader, right? Such as neighbor loader, like those random node sampler. And so the concept of the PyG loader is a combination of PyTorch's data loader and with a specific sampler, right, which handles the data sampling as well as the transformation. So from here, the profiling result, right, is on the graph stage with the MAG data set. In this particular example here, so it occupies 71% of all the CPU time. And how to optimize it, right? So in the PyTorch from the user level API, so there's a number worker kind of concept. So user can set it to a larger number, so which means you can have multiple workers or multiple process to do the data load while others processing other things. But the thing here is even though those things are parallelized, but inside of each worker, it is still does the sequential sampling, which is not optimal at all. So take an example, right? So here is like a train data loader, right? So here it is number of workers equals to 4, and then the transformation is the convert batch thing, right? This single line of code occupies almost half of the total time. So we need to optimize it. So the way we do it is, first is to make sure sampling and the transformation so they can be properly parallelized. And the second thing is we want to assign certain CPU cores, right? Do the CPU affinity and to do the data loader, right? So you need to balance like the data loader versus the trainer, and different models, so you may have different settings for that. And those two bullets are common for all the samplers, but the third one, so I put here is it is model specific. Sometimes you need to fuse several ops together, like in this case is in the converted batch, so you need to write a native C++ kernel. And so you need to do it one by one. Okay, yeah, so that's my last page. So what's next? So the first thing is co-work with PyG, co-work with Kuma to fully optimize PyG on both inference and training for Intel platforms. We start with CPU, but we will cover Intel GPU as well as one of the next steps. And the second thing is we want to support large-scale distributed GN training for the top use cases. For example, recommendation system, for example, like fraud detection in the fintech, as well as some of like the drug discovery in the health and life science domains. And we are collaborating with our partners, and we are collaborating with our customers on those use cases. And the third thing is the unified graph platform. Right? We strongly believe in that, and want a unified platform to support query, analytics, and GN together. Right? And we also want to provide workflows, end-to-end workflows on top of that, so that it is, again, echo to what I said initially, to two things. One is the performance. We want to deliver the performance as well as the productivity, right? So to deliver easy of use workflows, right? As well as the unified platforms to reduce the journey from data to insight. Okay, so that's all for my part. Thank you.
Thank you so much. Actually, given that we are running ahead of schedule, we can also open the floor for some questions. So if anyone has any question, please raise your hand either for Ke or for prior speakers. Maybe we can spend the time now as this kind of finishes the first part, which is the focus on scalability and performance of the graph machine learning. Would anyone like to ask anything, say anything? Yes, go ahead. There's a microphone.
Oh, hello everyone. I'm from Samba Nova System. I have a dumb question, maybe out of scope. So there is another popular library in the GN domains called DGL. So I'm wondering what's kind of benefit of PyG over the DGL, and is because there are some models written in both either the PyG and also DGL. So is there a way to unify them? Yeah, that's my question.
Yeah, thank you. That's a great question. I can say some things. Matthias, do you want to say anything? You know, I think it is great to have a diversity of approaches and to have alternatives. I would say that the two frameworks are kind of sister frameworks. PyG is perhaps focuses more on playing really well in the PyTorch ecosystem and being amazingly extensible, while the DGL is more kind of based on a kind of a C++ backend, which makes it somewhat harder to extend or to develop new architectures on. I would say, you know, both frameworks are getting a lot of traction and a lot of use, perhaps with a bit different communities. one being a bit more organic, another one being a bit more supported by a big corporation. But our goal in PyG is truly to democratize graph learning, make sure we have a common framework to which we all contribute so that it really serves everyone rather than being driven by one or a small number of interested parties. So that's really, I would say, our goal, and that's why also we are hosting events like this. We are making sure the community is strong, providing all the materials, and also as we discussed around community sprints and engagements and all these contributions. Really, the goal is to create a library that serves everyone's purpose, and in some sense is a community effort, grounds up community effort. So that's how we see it. Yeah, thank you for your question. Right, and we are committed to keep supporting PyG as a truly open source framework. We are committed to feedback from the community and extending it in directions that helps the community. We want the library to be multi-cloud, multi-platform, and well supported across all different, let's say, computing architectures paradigms. So that's very important. And then PyG as an ecosystem, right, is both meant to serve, let's say, high-end, PhD level data scientists and MLEs and researchers developing the latest and greatest architectures, as well as having packages in the ecosystem like the Graph Gym that simplify creation of graph models for, let's say, more application-focused users or users who don't want to do core GNN architecture research. So the goal is to really have a kind of a wide portfolio and different APIs for different users. So that's kind of our vision, how we are pushing things forward. And because we want to be, let's say, developer-friendly, it's very important that interfaces are extensible, are generalizable, and that others are able to plug in their tools and their code into the ecosystem. So for example, the abstractions we announced today around a graph store and a feature store means that you can bring in your graph store if you have it. You can bring in your graph database, you just implement the API, and it will work well with the rest of the ecosystem. Right? So these are things that are very important to us because, again, we want this to truly be a community effort that serves everyone for all the use cases that the community is interested in. So we very much welcome the involvement. Yes?
Thank you. Great presentation. And I have a question about the online inference side. And I think we talk a lot about the offline training optimizations. And will this optimization be applicable to online inference? And do we have any work for online inference side? Thank you.
I can maybe say, so just to clarify your question, I think you are more thinking from real-time model deployment for various kinds of near real-time or real-time use cases in terms of, let's say, recommendations, fraud. That's the nature of your question? Okay, great. Okay, do you want to answer?
Yeah, so the inference optimization I just mentioned is actually the generic stuff, right? It applies for both online and offline. It's a very low level, right? So yes, so it benefits both. Yeah.
Okay. Okay, thank you so much. This was a great discussion. Super cool questions. We are also going to open for more questions later. So we are continuing with the program, shifting gears a bit. So I'm really excited to have Andreas Damianu, who's joining us from UK, from Spotify. And he's going to tell us about how they built a recommender engine for query suggestions, as well as, I think, playlists suggestions on the Spotify homepage using graph learning and using PyG. So take it away.
Thank you. So we have had some excellent talks so far about scaling PyG and all the new advancements. And now we will switch gears a little bit and discuss about an application where it makes a very big difference having this scalability advances, because we really have massive graphs and really have latency constraints when we talk about recommendations. First things first, this is work done in collaboration with many amazing people, which I list here, thanks to all of them. And I appreciate not everyone is aware of what entails to have a recommendation task. So let me provide a little bit of context. When you interact with Spotify or some other recommendation platform engine, the experience is powered by machine learning, and in turn, the machine learning model is powered by data. Traditionally, you might think of this data as being stored in some independent, let's say, SQL tables, being all there on their own. Of course, in reality, everything is connected. And a graph is a data structure that is emphasizing these connections. And with learning on the graph, we can explicitly exploit the topology of the heterogeneous and connected data pieces. And this is actually amazing for recommender systems, because we can represent both the content and in the interaction network. And by interaction, I mean user-to-user interactions, co-listens, item-to-item interactions, and of course, user-to-item interactions. So to make it a bit more specific, let's think of the podcast graph. We could construct as follows. We could have users to be nodes. We could have podcasts to be nodes. And of course, we can extend with, let's say, social network if we have user-to-user, or with metadata, for example, Wikipedia-derived topics, or tags like who is a publisher of BBC Earth, and so on. Obviously, nodes can have features like user demographics. Edges can have features like times listened. And with graph learning, we can perform reasoning that exploits long-range correlations that are found in the graph. For example, the fact that the red user is connected through a long path to BBC Earth is something that the recommender system might want to use. Another graph that naturally arises in Spotify is when a user is typing a search query. So here the blue user is typing a couple of queries in what we call a session. We get the results from the retrieval engine, and these are also nodes, same as the queries that can also be thought of as nodes. And some of the results can be shared with other queries and so on. So we have a graph again. And obviously, one could think of a combined graph, because all of these things live inside our own platform. And we are talking about the same user who is typing queries with the user that is consuming podcasts and so on. So traditionally, companies develop solutions somehow independently for different surfaces or for different problems in different parts of the platform. But with graph learning, the cool thing is that we can bring together heterogeneous knowledge from different parts of the platform, and we can therefore create application-dependent and holistic representations of users and content. And these are nuanced representations because they exploit topology. They capture complex relationships and can, of course, be specialized according to the downstream task, for example, recommendations. So from now on, when I talk about a graph, I will mean a heterogeneous graph. And obviously, when we start putting a lot of things together, we have to make some graph design choices. There are tools like Grail that semi-automate some of the process, or of course, you will need to do some sort of handcrafted exploration as well, trying different sorts of graph and evaluating that offline or even online. And then a lot of questions arise. So here's some of the lessons that I want to share with you. Some simple type of choices. Should some nodes, like some things like the Wikipedia-derived topic, right? Should that be a node on its own right, or should it be a node feature of an existing node, like the podcast node? Should we focus more on the knowledge graph type of approach, where we want to put as many entities as possible and then embed it? That's an approach that has been taken in Rexis in the past quite a lot. Or should we emphasize more the consumption patterns, that is, the user-item interactions, item-item interactions, things like that? And how can we handle redundancies? The more things we start putting together in heterogeneous graphs, we start creating a lot of redundancies. For example, this triangle here, should it be a fully connected graph? Are some of these edges redundant? Should we do some pruning? All of these things need to be decided. And let me explain a little bit more specifically how can you use these graphs for recommendation. When you get a recommendation from Spotify for a podcast, you might get in what we call a shelf like this. And the system to reach the decision to show you this shelf goes through a few different stages. Firstly, there is the candidate generation stage, where all the possible podcasts are sourced with a different source algorithms, and they're blended together with a candidate generation step to be filtered to a couple of hundred. This is an important step because we want to blend different sources, for example, familiar and unfamiliar shows, popular, less popular shows, and the ranker downstream will decide which of those are better for personalization, but we want to have all of those at this step because we are optimizing for recall. Then the ranker will take all this filter set and further reduce it down to a dozen or so, and will, by optimizing for precision, basically what is the user more likely to click on will get a ranked list. And as I will explain, GNNs can be used for both. Firstly, for the candidate generation step, we can have a source that is GNN-driven. The hope to do, by doing so is to have the topological information into the sourcing of podcasts that can have more nuanced information and potentially combat things like popularity bias. So it's a high, let's say, it's a high quality source of podcast suggestions. To do that with GNNs is relatively straightforward. We have our graph that I showed you before, and then we train a GNN for link prediction. That's a independent of the application, unsupervised, let's say, task. And by doing that, then we can extract embeddings for users and for podcasts. That's going to be all in the same space, in the same embedding space. So then we can have a distance between the user embedding and the podcast embedding, which means that we can take the approximate nearest neighbor routine, and for a given user, find the top K nearest podcast and give that as a list. That's going to be the sourcing from the GNN. As I said, we can also use GNNs also in the ranking step. The ranker is typically a machine learning model. Could be a wide and deep network or some other machine learning model that I have listed here. There is many of those. And these models, they consume a lot of features, and they are trained on historical data. And embeddings provided by GNNs can serve as additional features that have rich topology. Exactly, the point is that we can improve ranking with this topological information. And an additional point is that the ranker provided with these GNN embeddings can handle better the GNN-sourced suggestions from the previous step that I mentioned before. So the ranker is setting a lot of features, as I said, which, by the way, we can also use as node features for the graph. The GNN is producing show and user vectors. And at this stage, we do apply the ranker for every given user and a given podcast. So we can throw the show and the user vectors as additional features. Or, for example, instead, if we don't want to have raw features, we can also have the cosine similarity for a given user and a given podcast as a feature for the ranker. Result-wise, we did find that using non-complex graph learning algorithms helped us improve important recommendation metrics, particularly for long-tail shows, for example, shows that might be a bit less popular or they are not recommended as often. A different use case is the related search query suggestions, which I'm explaining here. When you type a query in Spotify, for example, sleep, you're looking for like a podcast about sleep or sleep sounds, something like that. This goes through a system that has access to historical query logs. And in the end, it spits out some related searches that you could have done related to what you did already. It's going to look like this, a tab like this in the app. And you can see that the aim of that is to be able to help the user find more easily what they're looking for, or maybe help the user explore different searches that they could have done that might not be exactly the same, but they will hopefully be interested in that as well. So for example, sleep and rain are related in a sense because in our platform, people who type rain, often they are looking for calming, relaxing rain sounds because this helps them sleep or relax. Again, the GNN-based approach can be used here. We have experimented with and used it in the candidate generation step. and we have found that it has key advantages. Firstly, it can generalize well even for new queries that the system has never seen. For example, imagine that Taylor Swift has a new album, and this is a completely new query that we need to be able to handle. And that's because GNNs are reductive. The other thing is that we can suggest related queries that might not even exist in the logs. So this goes beyond a simple, let's say, co-occurrence model, which is like, this query has been typed in the same session with these other queries, so I will suggest these other queries. Here, in fact, we can suggest things that might not exist because we can have synthetic queries, or we can decide that we have topics as suggested queries, or genres of music. It's also robust to language ambiguity. If you were using, because these are text, right? You could use an NLP model, and if you were using only a language model, then things like Poker Podcast and Poker Face would be matched very closely in the embedding space language-wise. But in the embedding space of a GNN, these are far apart because they are living in completely different neighborhoods. And again, the way to achieve that is straightforward. We have a graph that is built on the session level and is enriched with metadata, like genres, topics. Here we also have the concept of clicked query. Is quite important because a clicked query is a query that resulted in a click. Not all queries have this property. For example, users sometimes they write a query and then they don't click on it, they reformulate, they drop the session and so on. So clicked query carries a lot of weight, let's say. And by the way, I want to make the point that it's a domain knowledge here that we can incorporate in our graph and in our results. So for example, we might want to put a higher weight for nodes associated with clicked queries. Then we train again GNN on link prediction, and we come up with an embedding space. In the embedding space, we have everything living in the same space, and the things that we extract embeddings for are things that we might be interested in showing as related searches. For example, we might want to say that, that a topic is something that the user could use as a search, right? So given a query, we find the nearest neighbors in the embedding space, and then maybe we have some logic to blend different nearest neighbors like queries, click queries, episodes, and so on. And this is what we suggest as a source of related queries. Here are some examples. When we have spam using water as an example query, we get a list of suggested queries. The color indicates the relevance as given by the distance to the nearest neighbor space. So we have things like soothing music with calm waves, sleep music, and so on. For good Disney songs, we have good Disney hits, and so on. And as you can see, and as we have also observed in production, with a graph-based search, we can have semantic information from sessions that goes beyond language. For example, sleep for 32 hertz contains none of the words that are included in the given query, but they live in a similar neighborhood in the GNN space, so we are able to suggest that. You can also see that we can suggest things that are not queries, so this is actually the name of a podcast, and so on. The similarity score that is here indicated by color is something also that the ranker can use downstream, so it's a useful information to know how related is a suggested related query. And we can see that from what I showed here, right, everything is embedded in the same space, not just the queries, like also the podcast episodes, tracks, all of these things are embedded in the same space. So this hints towards an extension where we can use GNNs to power the actual search retrieval algorithm. That would be the engine where you type a query and is doing the actual retrieval step to give you the relevant things that you think you are looking for. So I'm concluding by discussing some of the challenges and learnings that we have learned by using GNNs applied to recommender systems and to the tasks that I mentioned before. Firstly, it's important to capture both the collaborative filtering and the representation learning effect. And as I discussed before, that can be done by ensuring that we have a rich graph, but also having the collaborative filtering network, things like user-item interactions, item-item interactions, and so on. We found that it's often better to enhance the production system, like the ranker, for example, rather than replace it. So it's actually great that we can generate GNN embeddings and give them as features to an existing model, like the ranker. And that's because production rankers are typically super optimized, right? So don't want to replace them. We might not be ready immediately to replace all of that with a GNN and say, you know, the link prediction is what we use as a recommendation. It's important to use product-specific knowledge, and that can be done, for example, when we create the graph. And as you understand, graphs are massive, and talking about the number of edges, the number of nodes, right? We have like many users, many interactions. They are like really, really big graphs. And that's why I'm super excited about all the talks that I heard before. In the things that we have tried so far, we have actually used Ray for end-to-end train and inference that also has a distributed object store. We will be sure to check also the feature store and the graph store that has been discussed before. We're super excited about that. And also can integrate Ray with fast subgraph sampling as well. So again, everything stays nicely distributed data-wise. An important aspect to consider when we talk about recommendations is that graphs are dynamic. For example, we have new users, or we might have new consumption patterns, right? For example, you know, when the queen died, maybe when you type queen, you mean less about the band and you mean more about podcasts about the queen, things like that. These things have to be reflected when you generate embeddings and when you do recommendations. So it's a great thing that GNNs are inductive. We might use this capability to not retrain all the time, but still be able to embed new nodes without retraining everything. And also, we need to think about maintaining some sort of embedding consistency. Remember, these GNN embeddings are fed to downstream tasks, downstream models, and these models might be shocked if suddenly we serve embeddings, we give them embeddings that are completely different distribution-wise. A simple technique is to initialize embeddings at one point using the embeddings from a previous training step. Finally, I want to emphasize how important is, we have found at least, to be able to do rapid development iterations. We think that having the same code for production offline experimentation really speeds things up. And we have a PyG-based solution. It's really amazing how we can do this quick iteration, how we can have the PyG code used for trying different graphs, different extensions, so on, and then rolling it out when things are ready. And at the same time, having this customizable way of trying things, and when we're ready to roll out, we get out of the box a lot of scalability and other clever things happening under the hood. So that's all. I have also a list of references here. They're by no means exhaustive. You can browse them later on. Thanks again to all the people that have worked on that. That concludes the talk. Thanks.
Super, yes, we have time. Let's do a question or two. Go ahead.
I was wondering, how do you generate features, both podcasts or music as Spotify? I mean, is it a fixed amount that you squeeze everything in, or is it auto, or is it labeled by humans? How do you do that?
Right, so the question is how we generate features for the nodes, for example, right? So features exist anyway, and they're created by many pipelines because different machine learning models do use features, right? So the ranker is using features, the kind of generation models are using features, analytics teams are generating features for the analysis. So we kind of exploit what is already there, right? Because these things exist already. So maybe I'm not gonna go into too much detail about what things are used, but obviously you can imagine that there is features based on on descriptions of podcasts, for example, right? You can have implicit and explicit features, all these things. Things that exist already in the database, like user demographics, right? So all these things are used for the collaborative filtering anyway. Now, when we talk about graphs, we might want to have additional graph-specific features, right? But we have found that the features that already exist, right, and especially, even considering the links between user and items that we already have, that's already like a good boost in a couple of metrics that we have found so far.
Thank you. One more.
You have some questions from Slack. One of them was, how do you handle new users with a cold start problem?
Yeah, so the question is how we handle new users and cold start problem. It's a huge problem when it comes to recommendations, so there is papers and papers on that. When it comes to GNNs, right, it's convenient that we can use the inductive capabilities. So when you have a new user, we don't have to retrain the whole graph, right? If we do have features for this user, we can readily do inductive reasoning and then map in the same space already. And then there's also other clever things that one could do. For example, you might have a new user, but you might have other features for this user for maybe a different surface. Like if you have a new user for podcast, maybe you already have some data from music consumption and so on, right?
Sounds great. Let's finish here. Take the rest of the questions offline. Thank you so much. Great talk.
Thank you.
Great. So next, in the theme of applications of graph machine learning is Hema Raghavan. She's a co-founder at Kumo AI, and she'll show us how Kumo is using PyG. Thank you, Hema.
Thank you, Yuri, and it's a pleasure to be here. Today we'll be talking about how we're enabling enterprises to query the future using GNNs. That's a long title. But essentially at Kumo, we believe that we can radically transform how AI is done today. And in particular, we can make the ability to bring predictions to business use cases really fast. We believe that the interfaces can actually be as simple as SQL. And that's the tagline of Query the Future. Right now, Snowflake, Redshift, all of the databases have made it so easy to query the past. But we want to be able to make AI as easy as SQL. We believe for that to happen, GNNs are going to be the core technology to power it. And I hope that during the course of this talk, you'll see why. We're also very excited about PyG. Many of our developers actively contribute and maintain PyG. We think it's a developer-friendly ecosystem. It's also a very research-friendly ecosystem, which means we're just at the start of a revolution in GNNs. And I think by enabling a platform that actually allows so many contributions, we can actually innovate together as a community. So today, the ML lifecycle looks something like this. And by no means do we have to read all the content of this slide, but there are so many steps. And for those of you in production environments, you probably recognize the number of pain points you have to go through to get a model in production. There is the data cleaning, the labeling, the construction of a data set, that is the training data set prep, and then there is the post-model building, hyperparameter search, and productionization. The feature stores, the serving, so on and so forth. This means that either a company has to invest and build all of these tools, but it also means that a data scientist or an ML engineer actually has to, know so many of these tools and touch so many parts of the pipeline. Oftentimes, what this means is it can take several months to bring your first model into production. Today, fortunately, there's a startup ecosystem that serves many pieces of the pipeline, but that still doesn't cut down the time as much. So if you're a small and medium business starting out, you would buy many of these solutions, but it doesn't cut down the time significantly in getting that first model out. So what happens in a business that's not the top 5 companies with deep resources, right? There are more ML problems than ML engineers. So how do you pick a problem that's useful for your enterprise to work on, right? Let's say you're an e-commerce business and you know AI is going to be useful. You'll typically pick recommender systems or you'll pick personalization. And you go by gut instinct and some combination of what your predecessors did. But it could very well be that supply is your problem, that you actually don't have enough suppliers, and you better be predicting, supplier churn and actually giving, incentives for suppliers to come in, and you can do very well with a very simple ranking and recommendation model. And really, what happens is, because you don't know where to invest, it is very likely that enterprises leave, cash on the table. I think finding new high ROI problems for an enterprise is a bit like finding the right site to mine for gold. When you find the site, you exploit that site, you can extract as much as you want. So, all the AI engineers, data scientists, analysts, they want to work on that problem. But where do you invest next? What's the next problem to do? And that's, can we transform that? Can we actually bring down the time that you build that first model and see that, is this prediction going to be useful, right? So it's exactly like saying, what site should we mine for gold? The other revolution that actually inspired the team at Como was the representation learning revolution. So I did my PhD in text, and back in the day, writing a search pipeline was pretty onerous because you would do text pre-processing, there would be a part-of-speech tagging, there would be n different feature pipelines that let you capture the structure of the data. But that's gone today. So when you do text, you throw in text, right? Raw text. The same with images. You don't hand encode any of those features. And you can throw raw pixel data and you can get predictions. But then why is it the case that XGBoost and logistic regression and some of the more classical models are still the mainstay in enterprises today? And when we took a step back and started looking at what enterprise data looks like, it looks something like this. There are tables, there's a product table, there's an articles table in this case, there's some transactions table, and so on. The snapshot here is from an H&M data set. H&M is a store famous for clothing, and this is a Kaggle competition data set. It's very simple, it has 3 tables. But most enterprises have very deeply nested relational schemas, right? And if you start thinking about what a data scientist is doing in this warehouse, they're effectively trying to capture relationships between entities in these tables. But what happens inside or under the hood is they actually have to flatten the DP, which means you're writing a lot of join workflows, and then you're trying to capture all of those relationships in some kind of cross features and so on. And that's what leads to a good chunk of that complexity in that pipeline that we saw in an earlier slide. So really, the idea behind what Kumo is trying is that, hey, can we take this relational structure and find the right network topology that's right for your business problem, or you build your business graph automatically, right? Because once we can construct that, then we can, apply GNNs. And GNNs, as we saw in earlier talks, right? I think Matthias mentioned it, Yuri mentioned it. They capture structure beautifully. They subsume so many other classes of problems that you can solve anything from customer churn and LTV to recommenders to abuse and fraud. So if we can get this right, then we have a general purpose platform that solves many, many different classes of problems. So here's just an example of how we're trying to do this at Kumo. Again, very simple example, H&M data set. And the prediction problem is of predicting customer churn. And the blue node is essentially the label, which is basically a SQL-like or Excel macro-like expression on one column, which is the transactions table. And the brown and green nodes are the tables connected off of that. A richer structure would give you a much richer graph, effectively. And that top, the prediction can always be captured in a SQL-like expression, right? And this is going to be the gist of how we build our user interface on. So the idea behind Kumo is to bring the deep learning revolution to warehouses, but in a drastically simplified user interface. With that, the next thing we'll do is a demo by Sutinyan is our head of product. He's right there. Feel free to catch him at lunch. But we decided to skip technical issues that may happen with out here and actually show the demo on video. But it's all real time, so you'll see how snippy and fast it is on this data set.
Hey everyone, I'm going to show you how easy it is to use alpha version of Milk here. Go to raw data.
Okay, that audio was.
Everyone, I'll show you how easy it is to use alpha version of Kuma here to go from raw data to prediction production.
Do you know what's happening with the audio?
We're going to use the H&M data set, includes completely anonymized version on metadata for their customers, or they say.
No, the audio is bad. Tinyan, do you want me to drop my volume? Cut it down? Here? Oh, you think it's an echo effect?
Maybe you can try lower volume.
So I don't have volume control anymore. I've ceded volume control.
Why don't you play it on mute and talk over it?
Okay.
To go from raw data to predict it.
Actually, that's a good point. Maybe if I mute. That may solve it, right? No, that doesn't solve it. All right. Should I switch to laptop audio? Okay. We can, how many engineers does it take to solve? So, let's go. Oh. Now.
To go from raw data to predictions in production. Throughout this walkthrough, we're going to use the H&M public data set, which includes completely anonymized information on metadata for their customers, the articles they sell, as well as transactions for a fixed historical period of time. So obviously that's a common retail data model, but you can also bring a data model of your own choice representing your industry. Kumo would flexibly adapt to that as well. Now the first step is you create connectors. So let's create a new connector. We'll call it H&M. The data's, we stored it for the purposes of this demo in S3. So here's where it's located and done. You can start connecting tables now. To make this easier, we'll just do a walkthrough of one table, but we've already ingested the other tables as well. So let's ingest the articles table. It's a dimension table as opposed to a fact table. We want to ingest all of the columns, so let's leave all of them selected. We can take a look at the way that the pre-processing is done if we want, but let's just assume it's done correctly. And we'll choose which of these is the primary key, in this case, the article ID. So then the table is ingested. There we go. And also what we've done is we've calculated basic statistics on the first 10,000 rows to give you a sense of, is this the data that you really wanted to ingest? So for example, you can see that, most of the values are present. You can look at the distribution of the product names and the product codes, etc. Now, as a next step, we can start creating the graph because we've already ingested all of the tables. So let's call it our H&M graph. We can choose the tables that we want. In this case, we'll choose the customers, articles, and the transactions table. And now let's draw the linkages between those tables so that we can create a full graph. So the customer ID column links to the transactions table also through the customer ID column here. You save that linkage. You can also link the articles table, article ID column, to the transactions article ID column, just like that. Here we have a fully connected graph, which is ready for us to do predictive querying on. So we complete graph creation and we write predictive queries. Now, predictive queries are the heart of the Kumo platform. And the most common kind of problem that we see, let's just say we do a churn prediction problem. So a typical query for churn might look like this. I've copied it over to make things easier. Predict for every customer, filtering the customers to just the ones that have had a transaction in the last 60 days. That's what this -60 to 0 means. So they must have at least one transaction over the last 60 days. And predict for the next 30 days, are they going to have another transaction or not? Because what you want to detect is somebody who was active but became inactive, right? So let's train that query. We're going to start training now. And in order to save time, I'll show you what this looks like when it's complete. So you can see the query here. You can retrain it if you want when you have new data. And you can also review the evaluation metrics. And here we show common metrics on model quality to give you a sense of how well you can trust this query when it's used in production. And these are generated off of historic data, including, for example, the contribution of the different columns to the final prediction, as well as a bunch of other global statistics. When you are comfortable with the quality of this query, then you can start using it for batch predictions. So I want to predict, let's say if the probability of a customer having no transactions is higher than 0.5, then I'm going to mark it as churn, right? So that's what this means. I'll give it a table name, and I'll give it a location to output to, also in S3, and I want the predictions. So I'll run the batch prediction. And to show you what this looks like when it's done, here's what the output will be, and also the location where you can get the batch predictions. Now, finally, when the batch prediction output is generated, what you'll see is a table like this, where you have the entity that you're making predictions for. So in our case, the customer ID, you'll have a row for every customer ID that's active, that meets the filter that we set earlier. You'll have the timestamp of the prediction. You'll have the value that's predicted. In our case, it's whether churn is going to be true or not. And then you also have the probability of a false prediction and a probability of a true prediction. Now, this is what we generate if you're doing a binary classification problem or like a true-false prediction like what we defined earlier. But if we just predict a count or a sum or something like that, then instead of these three columns, you would see just a single number representing the predicted expected value, right? And you can do, there are a lot of things that you can do after this. So for example, maybe you want to reorder so that you can choose all of the most likely to churn customers and then reach out to them first. Or you might want to choose the ones that are most likely not to churn and do something about them as well. So there are many things that you can do after the batch prediction has been generated.
So with that, I hope it is apparent how we make it easy to actually use, to build a GNN to solve a business problem and actually shortcut that life cycle of building a machine learning prediction for your use case, right? And this can enable so many different functions, right? Like being able to use machine learning for sales, for marketing, like a lot of these underserved problems in any given enterprise. For this particular problem, we did compare, to a couple of baselines. One was a, simple marketing analyst kind of baseline that one of our engineers wore for a day. And the second one was an XGBoost-based baseline. For the LTV problem, LTV means how much is the user going to spend in, the next 90-day period. It's an error metric, so lower is better, and we do better. And likewise for, the churn problem, which was talked about, we, the AUPRC and AURC numbers also look pretty good. And in general, we're able to get to pretty a good accuracy on many different problem classes. So that said, to use Kumo, we still do expect data to come in raw tables in clean formats, but then most enterprises are doing that for analytics anyway. But after that, Kumo can actually give you a pretty end-to-end solution. And we don't expect training data to be created in one table. And that's a very important problem because a lot of machine learning engineers spend a lot of time doing correct training data set construction, right? So for any of you who build LTV and churn models, a lot of your workflows are actually getting that timestamp correct and then building a training data such that there is no data leakage from your held out sets to your training data sets. So none of that happened here. So, it was all behind. And actually, the GNN temporal sampling helped us there. So we constructed the graph. And smart temporal sampling can actually, prevent you from actually having to create a separate training data set, right? Through the rest of the, 5 minutes, I think I'm running over time. But I'll just breeze through some of the. I'm going to bleed over rock, if that's okay with you. Okay. I'm going to just go over technical problems that we're solving. And I hope that ignites some of the interest in the community of what we have to, work on together. The predictive query is one of the intelligent engines at Kumo. We, have a query planner and a query optimization interface. So, we made it look really simple, but behind that YAML, simple YAML config was, a query planner and an optimization that actually did a lot of the planning, right? Like the training data set construction and then how this would actually go to our ML infrastructure. Our ML infrastructure is PyG backed, and a lot of the intuitions that were presented in Dong and Manan's talk, apply there. Something else that's of great interest is, we've not done a lot in the GNN community for transfer learning, but actually we're finding that within an enterprise, there are so many similar problems that you can actually start thinking of transfer learning. Because we did churn, but churn and LTV, basically one is a classification problem, but the other one is actually a regression problem, which is saying, will the customer spend, and how much will they spend, right? So you can actually start using very similar network structures and leverage these for similar prediction problems. And that can actually accelerate productivity as well. So this is just saying that the objective function changes from a count greater than 0 to a total sum, right? And then you use a regression. Our infrastructure, so behind that UI, there's a REST API and an orchestration framework that talks to our data platform. Our data platform builds or materializes a graph. It's a highly optimized graph, and that goes to our ML infrastructure. We also enable explainability because a lot of our customers are actually in business organizations and they actually want to understand what led to the predictions. So at Kumo, we have actually thought of graph-based solutions to actually come down to table level and column level explainability. So, but that's a great technical problem where we also don't flatten the database again, right? Like if you had to do classic mutual information, you would be flattening the entire database. and have a massive workflow for that, and then coming to column level predictions, but we actually do that through graph algorithms. This is more for how a user might use Kumo, but we provide a secure cloud-first solution in which your data is isolated and your compute is in individual VMs. So, across enterprises, there is no mixing of data, right? So, and this is necessary to be an enterprise SaaS offering. We love open source, so we not only contribute to open source, but we also consume a lot of open source. So the Kumo control plane leverages a lot of technology out there. So in general, I hope what you got out of this talk was that, on top of a GNN, we're able to actually build up a platform that amplifies a data scientist to be able to do so many different prediction problems, right? And oftentimes, data scientists get one-off prediction problems that from their business owner that they don't have the time to invest in. And this would actually save you from that. Feel free to reach out to us over lunch, either for the product or for discussions on how we can collaborate on PyG. There's a few of us here in the audience. Thank you.
Yes, okay, thank you. Thank you so much. Thank you, Hema. In the interest of time, we'll skip the Q&A session. And next, we'll have a brief presentation by Joseph, who actually is leading the affiliates programs at Stanford, and he'll present a very exciting program we are having at Stanford to increase diversity.
Yeah,
thank you, Joseph.
Thank you, Ray. All right. Good afternoon, everyone. My name is Joseph. Many of you know me because you got emails from me to come to this meeting. The purpose of my team is to make it easy for you to invest in the research happening at Stanford. So over the lunch, we can talk about that. We also have a program that will allow companies to recruit Stanford computer science and electrical engineering students. So very exciting work there. Come talk to us about it. But for this brief talk, I want to talk about the diversity of master's and PhD students for your companies. We know that diversity is a problem at the undergraduate level, but when you go to the master's and the PhD level, it gets even worse, even harder. So what can you do about it? I want to talk about the LINKS program, which is one program you can participate in to help that. So what is the LINKS program? So we have students from historically black colleges and universities that come to Stanford for 8-week research experience. We had a cohort that came through this past summer. They finish their research experience, they go back to their home institutions and finish their degrees. These are rising seniors, so folks going into the senior year, last year, or juniors, typically third year. Many times they take the research project, they start here at Stanford and continue it at their home institution. The idea is that after they graduate, they will apply for graduate school, either master's or PhD. If they apply to the program here, we waive their application fee. So make it a little easier for them to come to here. And that increases the diversity of talent pool that you then can hire at a future date. So here's a picture of the smiling faces of the cohort that came through here. There are 6 students from a variety of HBCUs. And shown on your right, no, your left, my right, is Brianna Spencer, the Director of Diversity in Computer Science. So for this upcoming summer, we want to repeat and also to double number of students. We want to bring 6 students from HBCUs and 6 students from Hispanic serving institutions. And so students like Alina, shown in the middle, will get to work with Stanford CS faculty, like Jeanette Bogner, who does robotics. They are all mentored by PhD students and postdocs in their lab, like Andre that's shown here. They will also be mentored by someone from industry. So that's the ask and your company's role. And this is how you can participate. 1, a financial contribution. So it costs $13,000 for each student to come and do this whole experience, flights, lodging, food, etc. We're also asking for mentors. Would you be willing to mentor these students through the 8-week period? Tell them about the career in your company or your particular career path. And many times, if all goes well, you'll continue to mentor them for a few months afterwards. And also site visits. If your company is located in the Bay Area and you're willing to open your doors, we would love to bring the cohort students to your site and discuss what job and industry is like. The overall goal for this program is to connect students that historically do not have access to Silicon Valley, do not have access to a network here, to give them a taste of both what academia is like and what industry is like, to get to know people here and the work here, and get them excited so that they will apply for and go to graduate school. If you want more information, here are our emails. Feel free to take a picture of that. So Brianna Spencer is the director for diversity here at CS. That's my contact information. And again, over lunch break, we can talk about how to invest in research here at Stanford, how to recruit students at Stanford, of course, the diversity program, the LINKS program. So thank you for your attention.
Thank you, Joseph, for presenting this important initiative. So with this, we break for lunch. We meet again in 1 hour at 1:30 p.m. Pacific time. So a lunch break. The lunch is served outside. Thank you.
Thank you.
5G industry. Oh yeah, definitely. Yeah, we have to have something. That would be a good thing to have. Okay.
Okay.
Ja, daj. Malo še eno minuto, lahko še... Awesome, thank you, thank you. I can come back. Okay, that's okay. I'll come back to you. Yeah, it's still not.
Yeah, looks good.
Okay, Roka, lahko še enkrat. Okay, great. Thank you, Rok, for this nice dong or chime. Great. So we had a good lunch, and we are continuing with the program. In the afternoon, we are going to talk about different applications of graph machine learning. And to kick off the session, I'm super excited to be able to introduce Marinka Žitnik, who's an assistant professor at Harvard Medical School. She's also an investigator at the Broad Institute of Harvard and MIT, and also affiliated with Harvard Data Science. She's one of the pioneers in applying GNNs to biomedical and drug discovery type problems. And I'm, as I said, super excited to welcome her here, and thank you for flying all the way across to join us in person today.
Of course. Thank you so much, Yuri, for this kind introduction. Really excited to be here today. And I will talk today about graph AI and its role in enabling precision medicine. So when we are thinking about precision medicine, there are actually two big problems that are to be solved. And the first one relates to diagnosis, and the second one to treatments. And I'd like to, throughout the talk, give you highlights of how graph AI can not only is useful and helpful in advancing diagnosis and therapeutics, but actually crucially necessary to enable particular use cases in the context of precision medicine. And when we mention precision medicine, what we really mean is that we need techniques that would be able to take into consideration the increasing precision with which the state of an individual is described, including their genetic code, electronic health record, nutrition, environments, and be able to accurately and quickly diagnose that individual. And once the diagnosis is there, really the question is what kind of interventions, particularly chemical, genetic, or therapeutic interventions, can be introduced in order to treat the disease or improve the life of that individual. And the precision part here means that we want to move away from this kind of one-size-fits-all principle, where typically then diagnosis and treatments is done without consideration of the specific properties of individual, and do that such that it's really done at the individual patient level. And so I want to start with a vignette on how graph AI is particularly useful to enable diagnosis. And so the motivation for that part really is that there are over 7,000 distinct rare diseases in the US. And rare disease in the US is defined as a disease that affects around 200,000 patients in the US. And so the consequence of that is that patients that have those kind of diseases, they present themselves with a very different phenotypes and different symptoms to the clinicians. And because of that, most frontline clinicians have really no prior experience. They truly have never seen a patient like that before. And that is challenging because it contributes to delayed diagnosis and often requires a lot of visits to specialists and subspecialists. And it's known as diagnostic odyssey, where on average it would take the individual to spend 5 to 7 years before they get the actual diagnosis. And so this diagnostic delay is so pervasive that it can lead to problems for patients. The consequences are that because of it, patients might need to go to redundant testing, go to procedures that they would not necessarily want or to do, which is costly and detrimental to their health. There might be substantial delays in obtaining disease-appropriate treatment and diagnosis, and sometimes the delay is such that really there are some irreversible progression of the disease that happens. And so while we have seen over the last years tremendous progress that AI has enabled in diagnosing accurately patients, a critical gap that remains is that with the exception of very few diseases, we really don't have large enough annotated data sets on which one could train models to be able to distinguish between someone who has a disease and others who don't have a disease. For example, a prominent model that was concerned with diagnosing a diabetic retinopathy, which is disease of eye, which is currently the only autonomous AI approved by FDA to be used in clinic and also built by electronic health record, has relied on several hundreds of thousands of patient data that was used to train the model. So what we can do in situations where we don't have this large data set? So what we developed is a model called Shepherd. Shepherd is a few-shot AI learning method that can be implemented at various stages of clinical diagnostic workflow for the purpose of diagnosing rare disease patients. And so overall, Shepherd's GNNs works as follows. We first create a base model, which we obtain by training a self-supervised graph representation learning approach on a really large biomedical knowledge graph. And we do that with a purpose so that this serves as a base onto which we can overlay then individual patient-level information. So we then think of a patient as some sort of subgraph that is activated in that knowledge graph. And so what Shepherd does is then taking that individual patient information, it generates representations for that patient, the genes that have mutations in that patient, the symptoms and phenotypes that the patient has, and does that in such a way that it optimizes the resulting embedding space such that patients that are similar to each other will be represented by points that are nearby in the embedding space. And once we have this model, we are really interested in asking ourselves, can we transition it into real-world biomedical implementation? And so in this case, we teamed up with UDN, which is an undiagnosed diseases network. It's a network of 12 clinical sites in the US. And we wanted to really implement Shepherd and deploy it in these clinical workflows and see to what extent it can help accelerate the diagnosis. And so the setup for that was that we are very clever about trying to figure out how to be able to train the model on data from multiple sites. And so in doing that, we actually are generating a cohort of patients that are simulated on which the Shepherd is optimized. And then it's evaluated on 2 external patient cohorts across those 12 clinical sites in the US. And the results of that are the following. So we use Shepherd for 3 key tasks. And the first task relates to causal gene discovery, which is a task defined as given a patient, meaning patient and their set of mutations in their genome, and a set of phenotypes the patient has, can we produce a prioritized list of genes such that the gene at the top of the list is most likely to be causal gene for that patient phenotype? The goal of that is that if we can do that very accurately and quickly, then that gene would be the primary target for therapeutic intervention. And so the scatter plot shown at the top of this slide actually shows that for over 70% of patients, their causal gene is such that it's actually not neighboring gene to the phenotype nodes in the knowledge graph. And so that is significant because it essentially means that for those 70% of patients, we would not be able to diagnose them accurately without having a native graph-based approach. And so here on the right, I'm just showing an example of one specific patient and their patient card, and kind of the output then that Shepherd provides for that patient that then feeds directly into the discussion that clinicians have. The second task, in addition to causal gene discovery, it's a patient-like-me type of function. So patient-like-me functionality is the crucial task that kind of powers lots of variety of downstream tasks. And it's concerned with the fact that given a patient, what are other patients that look like this patient? And that similarity can be defined at genetic level, molecular level, phenotypic level. The reason why you would want to have like a really very good kind of similarity lookup like that is because then you can transfer information about positive experiences in terms of diagnosis and treatments from one patient to the other. And the third important task that Shepherd can do is concerned with really be able to characterize the kind of diseases that are presented in patients in unusual manner, when the patient might have multiple diseases at the same time, or they might have a genetic disorder that has not yet been classified in medical vocabulary. And so all these three facets of clinical diagnosis are enabled by essentially being able to query the underlying embedding space of the knowledge graph that is contextualized for the given patient level for different purposes. So the takeaway messages here that I'd like to make is that first, the use of graphs here is not only beneficial, but it is necessary. It really means that we had to have an ability to be able to find that there are multiple steps that need to be made in order to go from causal gene of a patient to their phenotypic presentation in the knowledge graph in order to make accurate diagnosis. And the way Shepherd can overcome limitations of the traditional approaches is by really infusing patient, clinical, and genomic data into the knowledge graph, and is doing that through a self-supervised pre-training using GNNs, by then, and importantly, by being able to generate a cohort of synthetic simulated patients that can help the model train well when the number of actual patients per disease is a very low number. And importantly, when implemented and tested across clinical sites in the US, it demonstrates the potential that these kind of methods have for shortening diagnostic odyssey for patients that have otherwise rare genetic diseases. Now let me change gears a bit. So once we have a model that can diagnose patients accurately and quickly, the next question becomes, well, once we have the diagnosis, what kind of interventions one should design to treat that patient? And so with that in mind, it is important to think about designing medicines that will be safe, effective, and that will be able to identify what patient would benefit the most from a given treatment and when the treatment should be given to the patient and in what dosage. And so these kind of questions are questions that we are thinking quite a bit about, and towards that end, we have founded an initiative that we call Therapeutics Data Commons that sits and serves as a meeting point between, on one end, biomedical scientists and biochemists who can identify meaningful tasks and data sets in the problem of discovering safe and effective therapeutics, and on the other hand, AI/ML scientists who design machine learning methods that can support the entire life cycle or all stages of drug discovery, going from early stage of drug discovery, where the main question is how to go from a large number of candidate chemical compounds and identify what are those that are most promising for further investigation, all the way to later stages of drug discovery process, where the question of safety and efficacy in real human patients is of primary concern. And all that is with the goal in mind that we want to facilitate both algorithmic innovation as well as practical advance in therapeutic science to be able to find out what are the algorithms that are most suitable for specific drug discovery applications and why would that work well. So the way we think of these problems is that most AI workflows in drug discovery consist of a sequence of steps. And so therapeutics data commons provides an ecosystem of data sets and benchmarks and loaders, lots of those, many of the functionality that popular ML benchmarks have that can support ML scientists when they are developing the models for specific drug discovery problems. And so that at the stage of model development, one can easily then interface with toolkits such as PyG or others in order to develop powerful models that perform well on leaderboards so that we can identify what are those that are can be transitioned into real-world implementation. So what does real-world implementation mean here in the context of drug discovery? I know fundamentally, I know that not many might be thinking about these problems on a daily basis, but the way we think of a disease and a drug is the following. So disease can be thought of as some form of perturbation of normal healthy state in the individual. And so to find an effective therapeutic, we want to find what kind of chemical could reverse that disease-associated perturbation. So in the network language, the way we think of it is that we have these vast biological networks of proteins in human cells and the way they interact with each other physically in the cell. And we know that part of that protein has been targeted by the disease. And so the question there is, what kind of drug could mitigate that alteration and perturbation that was disease associated? So in our case, when we have these kind of tasks and goals to identify what compounds can intervene against the disease, the way we approach these problems is often that we go through a broad range of human diseases, an entire range of already approved and available drugs. And we kind of parse through that data with the hope that we can tune our GNN models in such a way that they would be able to distinguish between compounds that are safe and effective for patients versus compounds that are not safe and effective, meaning they don't treat patient. And we do that across many, many diseases. Each disease is effectively a form of a pretext task in the pre-training scheme. And so we are doing that with the purpose so that the testing phase, even for diseases that has otherwise very few treatments, we're able to produce a priority list of what are chemical compounds that are most promising for that disease to maximize the yield of downstream experiments. So let me just show you one concrete result of doing that and partnering with experimentalists in our case. And so this was the work related to identifying, repurposing drugs that we can quickly repurpose for viruses, where our GNN models have prioritized chemical compounds, such that at the top of priority list were those that the model thought were most promising compounds in terms of most likely that would maximize the yield of downstream experiments. And so out of those 918 compounds, our collaborators from National Emerging Infectious Disease Laboratories tested their efficacy against a pathogen in human cells and also in cells of African monkey, who is a model organism for this disease. And so by screening these predicted compounds in human cells, we obtained near 62% success rate over which is in sharp contrast with around 0.8% hit rate that we would obtain by non-guided screening. So effectively what that means, if you take top 100 predictions made by the model, 62% of those that appear in the top 100 list are actually inhibited the growth of the virus versus only 0.8% one would get if you would do that without any guidance from AI model. So this is an order of magnitude improvement over non-guided screening. And importantly, we want to understand, is there something interesting about those drugs that the model predicted and that were also shown to inhibit viral growth? And so the results of that were that we found that 76 out of 77, those predicted drugs that reduced infection in the laboratory were such that they do not directly bind to those proteins that the virus, meaning the pathogen, attacks. And so why is that significant? That's significant because it means that those drugs, the way that they work is that they inherently rely on network-based action. So they bind to proteins in human cell that are not directly attacked by the disease, but through a cascading events of interactions, those initial protein targets actually have effect against the virus. And so this group of drugs is now referred to as network drugs. And it's another example of the kind of discovery that could not be possible by alternative strategies that don't use graphs. So it's not really only improvement in terms of performance, but it's able to find this kind of structures that other techniques were not able to do. So beyond a particular, beyond pathogens in virus, this kind of approach where we are trying to learn the mechanism of therapeutic action across the entire range of approved drugs is applicable also to various other settings, where we can think of overlaying large biological knowledge graphs with information about simulated diseases in the lab, which in that case would mean essentially taking groups of cells and perturbing those cells and see how those cells behave and trying to learn about that. That behavior. And the way we are approaching that is that when we are learning embeddings for genes in such a way that we can model effectively and understand where two genes will lead to similar kind of response in human cells, while we also want to preserve interpretable relationship between those genes and be able to really target the behavior of those genes in a very precise manner so that we know how they behave in a specific cell type versus some other cell type or different tissue context in that regard. And so the way these models are then used practically in biological discovery is that they can be thought of some form of AI-based catalogs. In our case, these are catalogs of chemical compounds. So when then a biochemist has a new compound that they're interested in, they can essentially take that compound as a query, and internally it's decomposed into a set of biological functions or pathways that are kind of a way to describe what that compound would do to a human body if it's used by a patient. And that set of pathways then are decomposed again into a gene-level behavior so that we know what genes would be altered if a patient then takes that particular compound. And so when we have this kind of catalog, it can be queried for numerous downstream tasks in drug discovery in terms of optimizing drugs, finding their therapeutic actions, and so on. And finally, what I would like to mention is that when we are designing these catalogs and AI catalogs and GNN models that are making predictions, we're increasingly paying attention on how to make sure that these models can transition into routine use. And for that, it's important to be thinking not only about how to optimize for accuracy of those predictions, but make sure that those outputs are trustworthy and reliable in that regard. So for that, we are essentially designing various visual interfaces that can provide different kinds of explanations to end users, and really evaluating the performance of those models through studies with biochemists, through studies with clinicians, when we ask them to what extent those outputs produced by models and associated explanations are really useful. And so here on this slide, I'm just showing an example where we teamed up with our collaborators from Mount Sinai in New York and evaluated the utility of GNN outputs when presented together with explanations versus no explanations at all in an effort to be able to really decide when are predictions useful to them and if they would use those predictions to inform downstream experiments. So with that, thank you so much for your attention. I'm very happy to have a team of students who are outstanding and amazing and collaborators to work with. All papers, code data sets are on our lab website as well as at TD Commons AI. Thank you.
Awesome. Thank you, Marinka. We perhaps have time for one question, and the next speaker can set up. Okay, no question. Thank you. Thank you.
Okay, thanks. Sorry, guys, this is always the worst time.
We cannot help you. You're using Windows.
I'm using Linux, but I appreciate the thought.
Okay.
Let's try this. Oh man, this is bad.
Can you flip? Oh yeah, it's what's that, KDE or something?
Yeah, it's GNOME, yeah.
I'll do a long introduction.
Yeah,
then.
do it. Yeah, just
okay,
sorry,
great.
yeah.
So I'm really excited to be able to welcome Brian Perozzi. He's a research scientist at Google and one of the pioneers of graph embedding work. He co-authored the DeepWalk paper that basically took the word to vec and generalized it to graphs. Today, so he's been kind of working at Google on graph learning ever since, and today I'm really excited to hear about some successes, solutions about applying graph neural networks at Google. Thank you, Brian.
Thanks, Yuri. That was the appropriate length introduction. All right, guys. I guess I'll time myself. I'm a research scientist at Google. I work on the graph mining team, and graphs at Google are bigger than you might think. Since PageRank, we've been very excited in them, and we're still very excited in them. The graphs that we're dealing with are typically very large, so we're talking things with billions of nodes, or more, and that's the kind of scalability that we're interested in. And the team's mission is to work at this intersection of algorithmic ideas for scalability and machine learning, and then some other intersection of actually providing value to the company. So we have a lot of applications, hundreds across pretty much every Google product you've heard of. Some of them are highlighted here on the right. I'm specifically the head of the GNN team, and so our team, sub-team's mission is to make it easy to use graph structured data inside neural networks. And so we do research in this area, obviously. That's what I'm going to talk about primarily today. We do have a library that's not PyTorch geometric to express these models. We also kind of build the infra for training and development internally, and we do a lot of model consultations. So we try to take the ideas that we see in academia, that we develop ourselves, and apply the best of breed to solve Google's problems. So what challenges for GNNs are there? That's a great question. I'm going to talk about a couple today that we've encountered. It's kind of be like a story kind of through time of different challenges, where I focus a little less on the first one, so I mean heterogeneity and scale, and then some of our more recent work on what's the right graph to use for your graph model, and how to benchmark these systems and how to generalize to unseen data. And I crammed a lot of content in here, so I hope I go at the right speed. So I think the first challenge, right, when you work with real data sets, they're a lot more complicated than academic ones, right? So when we first started working in this area 5 or 6 years ago at this point, we noticed that the real graphs we were working with, in addition to just being bigger, they weren't homophilous. And most of you know what homophily is, but if you don't, it's kind of the probability that an edge between two nodes mean that they exhibit the same, you can think of it the same label, perhaps. So it's it's kind of that the edges indicate correlation with the downstream task that you care about. So one of our efforts in this area, many years ago at this point, was to allow multi-scale information to the model. So instead of kind of just doing a model over your immediate neighbors, look at more than your immediate neighbors. And so there's sort of nice reasons to do this. You can learn a model that kind of can figure out things like edges if you were to apply it to a vision network. So this is the paper on that if you're interested. But this is, it's still a problem, and it's really exciting to see more work since this paper in people actually caring about models for heterogeneous data, because that's what all our problems are. Another challenge, kind of the second of the big quick ones, is that if you want to run these models on really, really big data sets, you're going to notice that your training gets slower and slower as you go on. I'm sure Matthias knows a lot about this. I see a smile there, maybe. And so, right, like this is a big challenge with these systems because we want to have the graph that has a lot of information in it, but that makes our matrix multiplications get slower. And so we did a lot of work on sort of what I would call like the simple GNN style approaches now, like linearizing the diffusion processes. To basically, you can think of it as create a new graph that captures the random walk in expectation, like where the messages would be sent if you did a lot of iterations. And so this kind of idea about using the diffusion information in the graph and kind of pulling it separate from the model is something else that we worked on a lot in the earlier days. And you know, this is, I think, it's a transformative idea too. Like a lot of people are working in this area now. So to talk about like some stuff more in depth, so challenge one is like, what's the right graph for our data? And so this is going to be mostly about this paper called Grail and some of its extensions. And thank you to the Spotify guy, Andreas, for actually mentioning this work. Thank you. The idea here is when we have a graph learning system, we assume we have like a partially labeled set of nodes for node classification, for example, and we have edges that indicate some kind of similarity. And in a perfect world, basically you could solve this with a clustering algorithm or a toddler. You could say just go and color in the nodes that don't have the right color. But sometimes, and you get something like this, right, where the colors are correctly sort of spread. But in the real world, you have a lot of different choices of similarity. And you can choose these kinds of similarity to be things like, you can think of them as feature embeddings. So some kinds of similarity might come from like content itself. In the case of something like YouTube, you can imagine some kind of like video similarity or some kind of like audio similarity as two kind of competing types of similarity you might use. And the reality is like if we have a heterogeneous graph, we have many different kinds of relationships to choose, and it's not obvious which one gives us the best graph inductive bias to run our models on, because we want the graph that tells our algorithm how to work. So you could do a bad choice of these edges. You could choose to choose this one type of similarity, and that won't do a good job of connecting them. Or you could try another choice where the recall isn't as good, it doesn't connect as much stuff, but it's very high precision, right? And this would be a better choice for a real-world application, even though it doesn't necessarily connect everything. And so we call this the graph design problem. So given like a multimodal feature space that indicates several different kinds of similarities, like so they each have a distance metric between them, and a partial labeling, can we learn an algorithm that's going to give us the right graph, the one that has the ideal relationship? So there's all the edges possible between nodes that have the same label, and then no edges that cross-labeled nodes. Our solution for this is called Grail. So it's kind of half a systems and half a model. So the system part of it uses LSH and bucketing to do kind of efficient distribute computation of the similarity thing. So we don't do all pairs comparison. You have to share some things in common. You have to be close in some parts of the metric space for us to consider running the model on you. And then once we have this model, once we have these pairs that are set up in these little points, we can use them for training a model or for doing inference on the model. What does the model look like? We've tried many, many different kinds of models. This is a popular one. So the inputs are kind of both, let's see if this works. It's kind of both the distances that are in the model, so like different kinds of similarity in the spaces, and then maybe like an embedding layer over here too. And so this kind of model can be applied to the training data, and basically then you've run it over all the candidates that you found through LSH collisions, and that'll give you the graph that is right for you. What does it really look like? So running this on an experiment for YouTube, for a trust and safety application, we can see things like nodes that are labeled abusive connected by nodes that aren't labeled as abusive. So it could be the case that these are an interesting kind of graph structure exposed through the model. We did run an experiment on this YouTube thing to see how much lift we were getting from doing the graph part of the algorithm, from doing Grail. And what we found is that Grail and label propagation was able to increase the recall of the system by almost 100%. So 89% of all this stuff came basically from adding graphs onto the already robust content classifiers and heuristics that they were using. And we can investigate properties of the graph too, maybe not as interesting here. A couple more example clusters about things to think about. So we can find dense abusive clusters, sparse non-abusive clusters. So the structure of the graph that comes out of this is actually really interesting in terms of the phenomenon you can see. What models do we use for this, for like our GNNs? In terms of like the GNN models we have, I've wrote a taxonomy of these things to try and understand them a long time ago. If you're interested, please check it out. But the thing that we find is kind of best is coming up with a separate model for each data set. So it's really the power of GNNs, that like the bespoke architecture that you can make for each data. So like in practice, people will say, hey, what convolution is the best? And I say, well, none of them are the best. We like to kind of build a special one for each data source. And that's because we kind of build everything around message passing. I guess that's kind of a small plug for our message passing inspired framework that we use for our production applications. When we rebuilt it for TF2, we also made it open source. So if you're interested, you can read more in the paper or check out the GitHub. All right, so challenge 2. Another challenge I have working in industry is that the way that academics evaluate these models is just absolutely atrocious. If you've tried GNN experimentation, you've run thousands of experiments on Quora, Sightseer, and PubMed to get that extra half percentage point of accuracy. I think that's a waste of time. And I know this is the Open Graph Benchmark house, so I'll try to be gentle. But the Open Graph Benchmark, which is great, I love it. But it's only 7, right? Sorry guys, it's only 7 data points, right? So like if you look at a bigger data set of all the graphs that exist, which still may not be representative, but if you look at a bigger data set that has thousands of graphs, you'll find that the Open Graph Benchmark graphs concentrate in an area that may not cover the space that well. So we have this distributed platform called GraphWorld, which tries to address this by simulating thousands of graphs with like all possible configurations, and to benchmark any number of GNN models on each data set. And then this kind of, after the distributed computation is done, you can aggregate the metrics to get insights. So for node classification, using a stochastic block model, there's all sorts of things you can vary. How much do nodes connect? How sparse is it? How what's the power law look like? What do the features look like? So you really trying to cover the entire space possible of the generator. What that gives us is these really cool pictures of the response surface of different models compared to each other. And I know this is the PyTorch geometric house, and so I say to you, friends, I built this for you. You can drop in any PyTorch geometric model and just sort of like benchmark it in this framework. Yes, I know, and it, this is the only time I've used PyTorch geometric, and it was easy, so good job. All right, so yeah, and so that's, this gives us kind of rankings of which areas of the graph, sorry I didn't explain that cool picture, but that gives us kind of rankings of which areas of the graph that different models perform well in. So this is edge homogeneity is like a homophily measure, so we see, GNN is typically run in these high homophily situations, and it works well because simple averaging works well. But there's different data sets and different kinds of areas where you see different other models perform better. So that's kind of the insights. If you're interested, read the paper more. It was at KDD this year. And in my last couple minutes, I want to talk about generalizing better with GNNs. So, the theme of today, I think, is that GNNs are powerful and that, you should all use them. I think I agree with that theme. But the problem with powerful models is powerful models can overfit. In particular, powerful models overfit when you give them bad training data. And when I say bad, I mean training data that's not sampled uniform at random, or training data that's just different from the test distribution, right? And so this can actually happen on a lot of cases where GNNs shine, like trust and safety applications. Your labels aren't distributed IID because they were found by some human who was going out there and like looking for bad stuff, and they found it, and then they recorded it as bad and threw it into your system to find more bad stuff. But this problem is you now have a biased sample, not a uniform sample. To convince you that distribution shifts are bad, here's a couple plots of standard data sets, standard academic data sets, where there's a distributional shift measure on the x-axis. And so what that's saying is the shift is getting bigger. As that number in the x-axis is getting bigger, the training data set is more biased. And as you increase the bias of the training data set, you see that the model's performance goes kind of bad. So some data sets are a little worse than others, but you can see this kind of general, hey, things get worse when your input data is shifted. And like I said, this occurs a lot in spam and abuse detections in the real world. And it's actually expensive to correct in the real world because of the label distribution. So when you have a really big data set and there's a very small thing, like a needle in the haystack you're trying to find, paying a human to find this like uniformly at random is very expensive. I guess another motivation is as your model gets more capacity, as it gets deeper, the domain shift gets worse. So if we want more powerful models, you're going to worry more about overfitting here, basically. So the strategy here is maybe a straightforward one, but what we're going to try and do is apply a regularization term to the latent representation, like the embedding that the model's creating, to balance out the bias. So basically, we're going to say, okay, the more that these two distributions look different, penalize the model. And there's a lot of different ways that you can do that, different regularization functions. You could use an adversarial model. You can use something based on the moments of the distribution. I think in practice, different data sets are going to have different kinds of regularizations that work best. We talk about one that worked well for the academic data sets because that's how you publish here. So just kind of keep that in mind. You may need to think about other regularizers. I think that's it, and I think I'm almost on time. Thanks for listening.
Thank you. Great talk. Lots of useful insights. We have time for one question, and then Srijan, you can come to set up. Anyone wants to ask a question? Okay. 1, 2, 3, gone. Thank you. Let's see whether you get a short or a long introduction. So I'm really excited. Maybe you get a long one. Okay, so great. Really excited to introduce Srijan Kumar. Srijan is an assistant professor at College of Computing at Georgia Tech. He spent 2 years at Stanford as a postdoc and has a PhD from Maryland. And he's been doing very interesting work in dynamic graphs, and especially when they are applied to fraud, web safety, fake news, detecting bad actors, and so on. So thank you, Srijan, for flying from Atlanta to present your work.
Thank you, Yuri. Fraudsters, bad actors, online misinformation, and hate speech present one of the biggest threats today to users, communities, and platforms online. User satisfaction, public health, democracy, and science and the entire society today are threatened by these issues. The problem is huge. Facebook estimates around 5% of its accounts, or around 145 million accounts, are fake. And it's estimated that Amazon has around 300 million fake reviews. At Georgia Tech, my students and I build AI, machine learning, and data science solutions to improve web safety and integrity for everyone. We innovate graph neural network, text mining, and behavior modeling techniques to develop multi-X detection systems, focusing on multi-platform, multimodal, and multilingual content. In the domains of web safety and integrity, while we are trying to catch bad actors, the bad actors are trying to fool and evade the detection systems. Therefore, we develop adversarial machine learning systems to identify the vulnerabilities of these detection systems from the get-go and patch them in advance to create the next generation of robust, trustworthy, and reliable detection systems. We attribute the role that technology, such as recommender systems, play in exacerbating cyber harms. And finally, we create data-driven solutions and tools to mitigate online harms and enhance platform integrity. My goal in the next 18 minutes is to explain 2 dynamic graph neural network methods that we have developed for detection and 2 adversarial learning methods that we have developed for fortification to create robust and reliable methods. Let's start with detection. Imagine that a user makes a post on your platform. You know this user's all historical posts and interactions, and you know all other users' interactions as well, including views, likes, shares, essentially everything that they have done on the platform. The crucial question for you at that very moment is whether the user is fraudulent or not. This is the basic question that every web safety and integrity system has at its heart. Temporal interaction networks are an incredibly powerful and a very flexible way to represent time-evolving interactions between nodes in a network. Here, I'm taking an e-commerce example where we have a bipartite node of users and items. When a user node interacts with an item node, a directed edge is created, which has an associated timestamp and a feature vector representing the type of interaction, the amount amount paid for the purchase, or the review text that is written. As time progresses, more user nodes, more item nodes, and interaction edges are created. This is a simplistic version, and you can generalize this to a more sophisticated framework as well. Representation learning presents a streamlined approach to model temporal interactions and represent dynamic evolutions of users and items, where each user and item can be embedded in a Euclidean space, and their evolution can be modeled by a dynamic embedding trajectory in this space. These trajectories can be trained for downstream tasks, for recommendations, for fraud detection, for misinformation classification, and so on. Our model that converts this temporal interaction network to dynamic embedding trajectories is called Jody. And this model was developed during my postdoc with Yuri here at Stanford. Jody is a mutually recursive, recurrent neural network framework that learns to predict dynamic embedding trajectories of users and items from their interactions. It has two major components: the update component that updates the embeddings of nodes that interact with each other, and a project component that learns to forecast these embeddings into the future to make futuristic predictions. Jody trains two RNNs in its update component, one for users that's shared by all the users, and another for items that's shared by all the items. We just create two user and item RNNs for scalability purposes. The user RNN uses the item embedding, the timestamp, and the feature vectors as input to update the user embedding from UT minus to UT. And similarly, the item RNN updates the user embedding, updates the item embedding by taking the user embedding as input. As interactions happen, the embeddings of both users and items are updated as information flows in. Now, here's the interesting part. Not only is Jody able to update embeddings, it's able to forecast where the embeddings are going by considering how the embedding trajectories have evolved in the past and how they will evolve in the future. Here we leverage insights from Kalman filters. Jody trains a projection operator that learns to accurately predict future embedding trajectories from any time point. Intuitively, the embedding of the user will change very little when time has evolved, when only a slight time has passed, and the embedding can change a lot when a lot of time has elapsed. To model this, Jody trains a temporal attention vector to forecast these embeddings. And the entire model, the update component, the projection component, these are trained simultaneously to accurately predict future interactions, along with a supervised loss to predict anomalies. To apply Jody in the web safety and integrity domain, we curated two new data sets from Reddit and Wikipedia, which have hundreds of thousands of interactions and ground truth of malicious users. Jody outperformed existing models by over 12%, and all the code and data are available at the GitHub link. A year later, Facebook released the TIES model, which has a very similar idea of using the dynamics of user and item embeddings for platform integrity tasks, such as ad payment fraud, fake account detection, and misinformation content detection. I'm super excited about this because this shows the potential that dynamic embedding models have at platform scales that have millions and billions of interactions and millions of users. Next, I will briefly describe another model, a very new one, that my students and I have created to model the dynamics in signed networks. For those of you who are familiar, signed networks are networks that have edges that can be positive or negative, indicating conflicting relationships. Positive relations can indicate trust, liking, supporting, and agreement, while negative relations can indicate the opposite: distrust, dislike, disagreement, and so on. Using directed networks, using unsigned network models on signed network models does not work because they have completely different properties, which I'll talk about shortly. But signed networks broadly are very applicable and incredibly useful in predicting veracity of posts, toxicity in conversations, conflict in online communities, and modeling online polarization. Essentially, think about all the trolling that you have seen online and all the arguments and disagreements that you have seen online. All of those have to be modeled as signed networks, specifically with negative interactions. As I was saying, modeling signed networks is completely different from modeling unsigned networks because it has to model both dynamics and signs simultaneously. There are three major challenges. First, the model has to follow balance theory. Balance theory dictates that edges in networks, in signed networks specifically, tend to form to create balanced triads, essentially triads that have an even number of negative edges. Edges form to follow the rules that friend of a friend is a friend, and enemy of an enemy is also a friend. We are still looking at dynamic graphs, so there are two dynamics-related challenges. First, since the graph is dynamic, we still need the model to be temporally aware. And unlike Jody, we would like the model to prevent staleness, which essentially means that even if a node does not have a direct interaction, its embedding should be updated. Importantly, existing methods either model the dynamics or the sign, but not both together. The prediction task, an important one at that signed dynamic networks need to deal with, is the following. Given a sequence of signed dynamic graph snapshots, can you predict the signs and weights of future graph snapshots which are also signed? To achieve this, we create Semba, which does a novel balanced aggregation. Here, instead of each node having one embedding, Semba creates a model where each node has two signed memories, one for positive and one for negative. When two nodes interact with a positive edge, memories of the same polarity influence and update each other, while if two nodes interact via a negative edge, memories of opposite polarities influence each other. To do this, Semba has 4 major steps. It builds on the TGN model, which was recently released. When a new edge is created between two nodes, signed messages are passed between the nodes following balance theory. That's step 1. In step 2, each node aggregates all the different messages during a particular time period that it will receive from all of its neighbors through new incident edges. In the third step, the node memories are aggregated and updated, which are then used to update the node embeddings themselves. Semba is trained to predict future links and anomalies in the graph. We use Semba on multiple data sets, and on average, Semba performs 4% better in predicting links and link signs, and it has, importantly, a 50% reduction in negative link prediction. So recall that I said that existing models are able to very accurately model positive links, but not negative links. So when applied, they make over-prediction of positive links and under-prediction of negative links. Semba overcomes that and has a very, very low false positive rate for negative links. So far, I have explained 2 dynamic graph neural network models, one for signed and one for unsigned. Next, let's turn our attention to robustness of graph neural network models in 2 different contexts. First, bad actor detection, and the second is recommendation systems. Investigating the robustness of systems is especially crucial for web safety and integrity tasks for 2 reasons. First, bad actors actively seek to fool detection systems that are designed to catch them. And it's important to be proactive and identify these vulnerabilities as early as possible without deploying these systems to later find out that they are not robust at all. And second, bad actors seek to manipulate recommender systems to push their agenda, their content, to everyone or to specific targeted groups. Both of these scenarios are obviously undesirable. Therefore, we develop adversarial machine learning techniques where we find the vulnerabilities that these models have with a goal to patch them in advance so that these models become trustworthy, reliable, and robust against adversarial manipulation when they're deployed. Let us first look at the case of bad actor detection and the robustness of dynamic GNN models like Jody and Ties. The key question that we need to ask here is, are detection models robust against adversarial manipulation? And if not, what's the worst case scenario? What's the worst case in terms of adversaries manipulating the system and the harm that they can deliver to the system? In this work, led by my PhD student Bing He and published last year at KDD, we designed a new adversarial attack model to conduct a targeted attack on these detection systems. PetGen is a personalized text generation model that generates attack post nodes along with its content to maximally reduce the prediction performance of a detection model. The post content can be considered as the features of a post node, and that is the most important thing that we are creating over here. Let me draw your attention to some of the crucial findings that we have. First, we find that both graph and sequence-based models that are designed to detect bad actors can be easily manipulated. In the plot, if you look at it, without any attack, the model gets a performance of around 0.7. While even very, very simple attacks, which are very simply just copying posts that the same user or previous or other users have written, they drop the F1 score. And as more sophisticated models are created, like PetGen, they can lead to a drop of as high as 15%, which is remarkable. On average, when you look at the failure rate of these models, we find that Ties, the model that's deployed at Facebook, has a failure rate of 26%, which is incredibly high for a production-level model. Next, we turn our attention to robustness of GNN-based recommender systems to minimal, insignificant perturbations in the training data. Well, consider how recommender systems are trained. They take historical clicks of all the users with all the items and use that to train a recommendation model that is used to then generate recommendations in real time during test. We wish to investigate whether imperceptible, minimal, and insignificant perturbations in the training data can lead to drastic changes in recommendation lists. Obviously, the goal here still is to create recommendation models that are stable, trustworthy, and reliable. In our upcoming paper at CIKM, led by my PhD student Sejun Oh, we asked two research questions. First, how stable are recommendations to minimal imperceptible perturbations? And second, is the impact uniform across all user groups? To measure the changes, we define sensitivity of recommendation systems as to how much the recommendations will change if perturbations are present in the training data. Through extensive experimentation, we show that both graph and non-graph-based recommendation systems, all of which are state-of-the-art, are very, and surprisingly super high, have very high sensitivity to even minimal random perturbation. Even one data point change, so which means changing one click in the training data among millions of data points, changes the recommendations of all the users. Perturbations in many cases can alter the top 10 recommendations by as high as 80%. Looking at the plot, what you see is that a stable model will have a rank biased overlap, which is a metric that we used to measure the stability of recommendation systems. That would be 1 if the recommendation system was completely stable. However, what we see is that even minor imperceptible changes lead to a very high drop in recommendation performance in terms of the stability. This is of ultra high concern because this highlights how fickle these recommendation systems are, even though they are state-of-the-art and many of them are being used in production. We create a new algorithm called Casper, which stands for Cascading Perturbations, that leverages interdependencies between interactions to identify the perturbations that should be introduced to lead to maximal changes in the data. Next, we compare the impact that these perturbations have on different user groups. Notably, we find that the instability has a disproportionate impact on users for which the model has super low accuracy compared to users with high MRR. Essentially, what this is telling us is that The recommendation systems for models, for users who they're not even able to predict very accurately, they're also very fickle and very unstable for them compared to users in the high MRR group for which the recommendations are even more stable. This highlights a fairness issue of recommendation systems that needs to be addressed. To overcome some of these vulnerabilities, we have created a novel adversarial fine-tuning model called two-part, or two-phase adversarial training, which is under review right now. And that leads to improvement in the stability of recommendation systems without sacrificing performance. In fact, in some cases, it even improves the performance. Allow me to wrap up now. In the past 20 minutes, I've described 2 dynamic graph neural network models for detection and 2 instances of adversarial robustness in classification and recommendation tasks. I'd like to thank my students for their hard work that made me come here and give this presentation, and the sponsors for supporting our work. I'd also like to thank the organizers for inviting me, and I look forward to continuing this discussion over the course of the workshop. Thank you.
Really great. Thank you so much. Again, time for a question, and I'll invite Luna to start setting up.
Thanks for the presentation. So you show example of showing like stability of the GNN networks where you remove perturb one training data set. I'm just curious about what if we just retrain the model, like how much overlap you will see?
That is after retraining. So we see that's exactly. Thank you. So when we retrain the model, the MRR and recall and other metrics do not change a lot. But what we see is that the recommendations are drastically changing. So it can change as high as 80% in many cases. So that's the main critical issue that we have here.
Sorry, I just want to clarify. So the question is, if you don't remove the training data, you just retrain the model, so how much overlap you will see?
This is after controlling for all that. So this is if you retrain the model, it will give exactly the same recommendations. They are controlling for all the biases of initialization and other things that are there.
Okay, thank you.
Great. So for the next talk, I'm really excited to present Luna Dong. She's a head scientist at Meta AR VR Reality Labs, where she works on knowledge graphs. And before then, she was a principal research scientist at Amazon working on their product knowledge graph. So this will be super cool talk. Thank you so much.
Hi there, this is Luna from Meta, and it is my great pleasure to come here to tell you about our work to build an AR/VR assistant and what is the role of graph learning to enable this assistant. Okay, so we are all busy and everyone deserves an assistant, and I wonder when you think about a virtual smart assistant, what would you think about? So it could be an assistant that responds to your commands. For example, you could say, hey, Siri, set a timer to 7 p.m. And then it will sort of interact with the app and do the timer for you, set the timer for you. It could be an assistant that controls your devices. You could say, hey, Alexa, turn off bedroom lights. And then your lights is off. And this is actually my #1 use case for Alexa. My #2 is playing music. It could also provide you information. For example, you can say, hey, Google, when does summer end? And it can tell you, hey, that is this particular day a few days ago. So at Meta, we are also building an assistant with a goal to empower connection to people and experiences in your life. So for Facebook Portal, as an example, you could say, hey, Portal, and then you can do hands-free call. And you can get other information such as weather, music, timers, alarms, so on and so forth. You can see your photos, for example. And for the Oculus Quest, VR glasses, and you can use this assistant to do hands-free sort of meeting up with the friends, asking who is online, Or you can find the game, open Beat Saber to jump straight into the game without really clicking all of the buttons in your glasses. And recently, this is last year, we shipped this ribbon glasses. And basically, with these smart glasses, you can take pictures, you can make calls, you can sort of listen to music, hands-free. You can just talk to it, hey, Facebook, take a picture, and then it will take the picture for you. So what is an ideal? Okay, this is already talking. So what is an ideal virtual intelligent assistant? And it should be an agent that knows you and the world. That's how it could best serve you. It can receive your requests or predict your needs. And receiving your requests is to serve you in a reactive way. And predict your needs is to serve you in a proactive way. And it can provide you the right services at the right time. All of this should be with your permission. Okay, so what are the technologies to support such assistant functionalities? And we have been talking about 3 examples, and they belong to 2 categories. It's either task-driven, where you interact with the apps or with the devices, or it is information-driven, where it gets the information from the knowledge graphs or from the web to answer your questions. And intelligent assistant is essentially a conversation system. And here, let's use an example of turn off lights, turn on lights to show how it works. So basically, the user request voice is first turned into text with this ASR, automatic speech recognizer component, and that translates voice to text, turn on lights. And then NLU component understand this text to figure out what is your intent and what is the device. And here the intent is to turn on the device, and the device is lights number 1. And this is to assume you have only one light, sort of a smart light to be controlled. And after that, the dialog state tracker will track the current status. So the action type is turn on the device is this particular one, and the current status of this device is off. And then the dialog policy will send this to real devices to turn on the device, and then reset the status accordingly, update the status accordingly. So after that, everything is done, and it will return the success status, and NLG will generate a confirmation, for example, lights turn on, and then TTS will translate this text to speech, and that is the voice confirmation you are getting. And this is one round sort of conversation. You get the confirmation. There could be 2 rounds conversation where you answer some clarification questions. For example, which lights do you want to turn on? It could be multi-turn conversation where you have some follow-up requests, such as dim the lights. You can even ask questions. How many people does it take to change its bulb? And expect some humor from the assistant. Okay, so that's for the current generation. And what are the challenges and initial solutions for next generation AR/VR assistant? And to answer this question, first let's see what is different for an AR/VR assistant. And first, this is glass. And so you see through your glasses. Your glasses not only hear what you are saying, but also see what you are seeing. And because it is glasses, you can wear it everywhere, so it is very different from just something that you put on your kitchen counter. And because you can wear it everywhere, so you can wear it for a long time, and so it knows you better. And finally, you wear it everywhere, you wear it for a long time, so you do not necessarily have the connection all the time. And with all of this, this means the assistant need to evolve. And first, because you can see through the glasses, and instead of just asking, hey, how tall is Empire State Building, now you could look at some building and ask, what's the name of this building? How tall is it? So it is not voice only anymore, it is multimodal. And because you wear it everywhere, so it knows the context, it knows where you are. And instead of asking, hey, show me my shopping list, when you are walking in the street, it might send you a reminder saying, hey, you should remember to buy the apples and the bananas at the grocery store near the corner. And because apples and the bananas are on your shopping list. And because you wear it for a long time and knows you so well, and you could, instead of just asking what's the weather today, it can tell you at the time when you wake up and put on your glasses, hey, today is sunny, 70 degrees. Would you like to play your favorite morning music? And actually what you just heard from my glasses is to inform me what is the battery level. And finally, we do not necessarily have connection, and we do want to have a very small latency. I don't know if you have timed yourself, if you use Alexa, just by asking the weather, it will take 1 second to give you the answer. And also we want the privacy. So instead of sending all of the data requests to the server side, to the cloud, we might want to do on-device learning. Okay, to enable all of this, and basically, we need to evolve the assistant. For understanding part, to make it multimodal, we need to have the computer vision component. We want to do multimodal understanding, and we generate output not only in text and voice, but possibly also images. This is the augmented reality. To be context aware, we need to collect context information. For example, what is the time, where you are you sitting or standing or jogging or walking or biking? And are you talking to someone? Are you in some particular event, such as a workshop? And then with the context, we can do context-aware understanding and also context-aware planning. And finally, with all of this context, we can trigger proactive services. Okay, so at this moment, you might be thinking, hey, how is this related to graph learning? And here I want to mention two things. One is proactive trigger. This is basically recommending some services for you. And also this KG web-related information-driven services. It can answer your questions. It can give you some recommendations. So let's look at this assistant recommendation. So on the one side, we could have all of the reactive recommendations, and those are through conversations, so conversational recommendation. On the other side, it can be completely proactive, and based on your context, your past behaviors, routines, it will recommend some services. And let's see what the graphs could do. First, we could have public knowledge graph that we use to power this conversational recommendation. And here the challenge is the knowledge graph is huge, and how can we leverage the vast volume of knowledge without sacrificing the latency? And to give you an example, let's say you would like to recommend some books like Catcher in the Rye. Maybe you are looking at this book, and so the assistant can see that through your glasses. And then assistant will look at this graph and said, okay, do you want to have books by the same author or have the same genre? And let's say you said, okay, I would like to have the same genre. So assistant will tell you this is a subgenre. And meanwhile, do you want first-person or third-person narrative? And then once you answer that question, assistant will tell you, hey, the Scarlet Letter is a good book for read, and it is a novel by this author. So as you look at this, what is important is which path you want to follow to identify those nodes for recommendation or for information. And what we did is we took thousands of conversations, and we annotate the entities in the knowledge graphs. And using that, we trained a path generation model. And given the initial knowledge graph node embedding, using just the knowledge graph embedding, and also the utterance, the dialogue context, we can predict what are the best walking paths on the knowledge graph to return you some node as recommendation. And according to different paths, we then re-rank all of the neighborhood nodes. And to make it really fast, we will prune those unattended paths to reduce the search space. And you are more than welcome to check out the paper there. And the next thing is, this is so far just using the public knowledge graph. And what about the personal knowledge graph? Knowing more of the user's reading history, the user's preferences, the user's routines. And here, the challenge is how can we leverage those personal information without sacrificing the privacy? And to do this, we enrich the graph from just the public information by adding the personal information. We call it personal knowledge graph, but it's actually a behavior graph. And then when we do the recommendation, we can look at what the users used to do. When the user is asking for a good place to eat, we will say, hey, you used to eat at downtown Phoenix. Do you want to still find a restaurant over there? And once the user conform, we would ask, hey, you like American food. Do you want American food or some different cuisine? Et cetera, et cetera. And the nice thing here is the content in the graph is not that important. It is, again, really the path that is important. So we only use the structure of this figure, this graphs, and learn the embeddings of those graphs, and use that together with the embeddings of the past dialogues, and then predict what is the next dialogue action, what are the nodes we want to recommend, which basically means what is the next value that we will retrieve and recommend to the users. Okay, so in addition to all of this, I also want to very, very briefly mention federated learning, which is also very important for preserving the privacy. Normally, we push the data to model, but federated learning allows us to push the models to data. And we can train the model at the server, for example, the meta model, and then push those models to each single user, and the user will use their embedding to fine-tune their recommendation models. Okay, with all of this, what I want to say about the future of graph learning for AR/VR assistance is this actually gives us an opportunity to put together 3 different kinds of graphs: knowledge graph, social graph, and also behavior graph. And if there is any other graph, well, there could be other graphs that people are interested in, for example, graph for bio, but so far we don't need to know your gene to recommend you some books yet. And so how to get all of these graphs together to get your history, your current context, your surrounding world, and how can do that, use the graph to enable multimodal contextual AI, proactive recommendations and conversations. And all of this needs to oftentimes happen at runtime, so the latency needs to be low. It sometimes need to be on device, and so you have very limited memory, etc. And we want to preserve the privacy. That's why it is so hard, and I need to be honest with you that graph mining is not in these classes yet. And there are still a lot of research to do. So with all of this being said, I have to admit to you that now my everyday worries are not yet those fancy features. It's much more of the device, the physics of the device. What is the memory? What is the battery? What is the thermal? I don't want the glass to recommend a book to me and then melt on my face. So for those of you who know me before, I used to work a lot on knowledge graphs in the past 20 years. My dream is there are trucks of data sending to me, and I can use them to enrich the knowledge graphs. But now, since I'm working on a slightly different domain area, I have a new dream. Now, my dream is that everyone has a big nose, and you can wear a computer, and we don't have all of the limitations for battery, memory, etc. So with this, several takeaways. We talked about what is a good intelligent assistant. We talked about it is essentially a conversational system, either task-driven or information-driven. And we need graph learning. There are a lot of exciting problems to make it even smarter and stronger. With that, I would like to take take questions if we have time. I'm looking at this and.
Thank you.
Yes.
Great talk. Thank you so much.
Do we still have time?
We can take a question.
Yeah.
Yes.
Would you do inference and learning on the device, or how are you envisioning that interaction?
Yeah, great question. So the question is whether we do inference, we do on-device learning, basically. Yes, we do that. And all of the speech understanding, natural language understanding, and also the sort of natural language generation, etc. This currently is on-device. So it is a lot of, sometimes we really need to struggle for tens or hundreds of bytes of code.
Okay. Thank you so much. Great talk. Thank you for the overview and the vision. Super cool. So our next speaker is Michi Yasunaga. He's a senior PhD student at Stanford in the computer science department, co-advised by me and Percy Liang. And he's really working on this exciting area of how do we endow large-scale language models with more relational knowledge and allow them to reason better. So go ahead, Michi.
Sure. Yeah, thanks, Yuri, for the introduction. And hi, everyone. I'm Michi, a PhD student working with Yuri and Percy Liang. And today I'm very excited to talk about our recent work on empowering language models with graph learning. So this is a joint work with my amazing colleagues listed here. So to start off, I want to give a brief introduction about what is NLP, natural language processing. So NLP is a research field in AI that tries to teach machines to communicate with human language, such as English. And this involves understanding natural language inputs, reasoning about it, and also generating coherent natural language outputs. And over the past few years, we have seen remarkable progress in those NLP systems, and now they power many products that we use every day, such as machine translation, question answering, personal assistants, and special applications like legal and healthcare services. And many of those modern NLP systems are powered by large language models. So you may have heard of BERT, GPT-3, and so on, and they are basically very big neural network models that are pre-trained on massive amount of text. And the power of those language models is that you can take any text corpus, like Wikipedia, to pre-train, to perform self-supervised learning of this model without any human annotation. And the resulting language model can be adapted to various applications, such as question answering and so on that I mentioned earlier. And those language models are typically trained by taking a document from a text corpus, and then you perform some language modeling task over it. such as predicting the next words or predicting masked words from the original text. So here in this talk, I want to introduce how graphs can play a significant role in improving language model training. So we have a lot of graph data related to text, such as hyperlink graph that connects relevant documents, and knowledge graph that connect relevant entities. And our insight is that those graphs can provide connection between concepts that might be far or latent in the original text. So for instance, document links like hyperlinks can connect multi-hop knowledge that spans across documents. So for instance, we have a Wikipedia article about tidal basin in Washington, D.C., shown on the left. And we have the hyperlink document, National Cherry Blossom Festival on the right. And by combining those, we can actually get a new multi-hop knowledge, such as tidal basin has Japanese cherry trees, which was not mentioned in the original single document alone. So the idea is language model is very good at capturing the local context, but the document graph can provide additional global relations about entities. Similarly, knowledge graph can provide latent relations about entities but that might not be mentioned directly in the text. And this can help reason about the text using the background knowledge. So in this talk, I want to give the message that graphs can bring relevant documents and concepts closer together and help language model training. And I will introduce two concrete techniques to enable this. The first is LinkBird, which tries to use document links such as hyperlinks. And the second is Dragon, which further incorporates knowledge graphs to train language models. So let me dive into the first technique, LinkBird. So as I mentioned, documents have rich dependencies with each other, such as web pages, which has hyperlinks, and scientific papers have citation links. And those links are very important because they can bring together knowledge that spans across multiple documents. So here, our goal is to train a knowledgeable language model from a graph of documents. To this end, we propose this LinkBird technique, which consists of the following two steps. The first step is, given a document or given a graph of document, we will create link-aware language model inputs. So specifically, we will create input as a pair of two text segments, A and B, by using the following three sampling options. So first, we'll take some segment A from some document, let's say document 1. And then for segment B, we'll either take the contiguous segment from the same document, or we take subsegment from some other random document. Or we take a segment from a document that is hyperlinked from the original document to prepare segment B. And our input will be the concatenation of segment A and segment B. After we prepare this input, we will pre-train the language model using link-aware self-supervised tasks. So we'll consider two joint objectives. The first is masked language modeling, which masks some words from the original text and tries to recover them. The second is document relation prediction, which tries to classify the relation between segment A and segment B that we prepared. So this will be either contiguous or random or linked. And the idea is that by training the model using those two joint objectives, we can encourage the model to learn the multi-hop knowledge that was brought together by document links. So that was the LinkBird technique. And here I want to introduce some exciting results that we got from LinkBird. So here, we pre-train LinkBird in two domains. One is general domain, the other is biomedical domain. For the general domain, we use Wikipedia as the text corpus, which is same as previous BERT model, except that here we also use the hyperlinks between Wikipedia articles. And then we evaluate on various NLP and question answering benchmarks. For the biomedical domain, we use a PubMed as the text corpus, which is same as the previous work like PubMed BERT, except that here we use the citation links as an additional training signal. And we evaluate on various biomedical reasoning tasks. So here's the evaluation result. So we find that LinkBird makes consistent improvement over the baseline BERT models across all the tasks and domains we studied. And especially the gain is large for the biomedical domains, possibly because scientific papers have rich dependency with each other through citation links, and LinkBird is good at capturing such information. And our biomedical LinkBird, which we call BioLinkBird, actually sets a new state of the art on various biomedical NLP tasks, which is very exciting. I also want to share some exciting benefits of this LinkBird technique. So the first benefit is multi-hop reasoning. So within the question answering data set we studied, there are several tasks that require multi-hop reasoning, such as hopper QA and trivia QA. And we find that LinkBird is especially useful for those kind of tasks. So here's a kind of interesting example from the hopper QA dataset. So to answer this question, you need to look over those two supporting documents to arrive the answer. And here, you need two hop of reasoning. So you need to hop from these Rodin brothers to Henry Burks in the first document. And then you need to hop from the Burks group to Montreal in the second document, where Montreal is the correct answer. And we find that the baseline BERT typically predicts the entity that is close to the original question, such as Toronto, but our model can correctly predict the answer, Montreal, which is in the second document. So the insight or intuition is that because LinkBird has seen linked documents in the same context during the pre-training, this helps the model to reason with multiple documents in the downstream question answering applications. The second benefit is few shot or low resource question answering. So here we fine-tune the LinkBird or BERT on just 1% or 10% of training data. And here we find that LinkBird is especially effective on those low resource regime. So this suggests that LinkBird internalized more knowledge than BERT during the pre-training. So this supports our core idea that hyperlinks or document links can provide additional useful knowledge for language model training. We also have all our LinkBird and BioLinkBird models available on Hugging Face, and you can use it with just 5 lines of code. So you're more than welcome to check it out. So to summarize, LinkBird is a new technique to train a knowledgeable language model using document links, such as hyperlinks and citation links. And we show that it is especially effective for multi-hop reasoning and few-shot question answering and so on. Now I want to introduce the second technique, Dragon, which further incorporates a knowledge graph into language model training. So as I mentioned, language models are typically trained with text or additionally with document links, as I just mentioned. But knowledge graph provides complementary information to text. So text has broad coverage on knowledge and can capture rich context. On the other hand, knowledge graph can capture structured background knowledge by representing entity as nodes and relation as edges. So this can provide a latent relation about entities that might not be directly mentioned in the original text. So here, our goal is to train a language model jointly from text and knowledge graph so that we can fuse the strengths of the two modalities. So in order to achieve this, we propose this new technique called Dragon, which does a bidirectional pre-training of a language model from text and knowledge graph. And this consists of the following 3 steps. So the first step is, given a text corpus and some knowledge graph, we want to prepare an informative pair of a text segment and knowledge subgraph so that the text segment can contextualize the knowledge subgraph, and the knowledge subgraph can ground the text by structural knowledge. So to do this, we specifically sample a text segment from the text corpus, and then based on that, we retrieve some relevant knowledge subgraph from the knowledge graph by doing entity linking. And then this will give us a aligned pair of text and local knowledge graph as our input. And secondly, we will design a model that can capture the rich interaction between the input text and the input knowledge graph. Here, our idea is to use the GRID-CLM encoder from our previous work, which is basically a bidirectional architecture that combines transformer and graph neural network. And this can basically fuse the input tokens, text tokens, and knowledge graph nodes bidirectionally for multiple layers to produce a final representation for both modalities. And finally, we'll pre-train this model using 2 self-supervised reasoning tasks. The first task is masked language modeling, which masks some words from a text and try to recover them. The other is link prediction, which drops some edges from the original knowledge graph and tries to recover them. And the idea here is that by training the model using those 2 objectives, we can encourage the model to use both the text information and the knowledge graph information to reason about the missing words in the text and the missing links in the knowledge graph. So this will encourage the model to learn bidirectional information flow over the 2 modalities. So that was a Dragon technique, and now I'm excited to talk about the results of Dragon. So we also pre-trained this Dragon in 2 domains, general and biomedical domain. For the general domain, we use book corpus as a text data and concept name as a knowledge graph. And then we vary on various common sense reasoning tasks that require some common sense background knowledge. So here we have two types of baseline. The first baseline is language model, such as Roberta or the LinkBird I mentioned earlier. The second baseline is a language model that is fine-tuned with knowledge graph, but was not pre-trained with knowledge graph. So this will be something like a GRIS-LM. So the difference of Dragon is that in Dragon, we will pre-train a language model with knowledge graph besides doing fine-tuning. And similarly, for the biomedical domain, we use the PubMed as the text data and UMLS as the biomedical knowledge graph. So here's the performance result. We find that Dragon makes a consistent improvement over the two baseline I mentioned, over all the tasks and domains. So we can further decompose this and see the effect of using knowledge graph with respect to the baseline language model. And we can also see the effect of pre-training with respect to the baseline GRIS-LM model. And we can see that both of those components provide substantial improvement for the model performance. I also want to share exciting benefit of the Dragon model, which is improved performance for complex reasoning. So here, we identified several complex questions that require some reasoning, such as questions that contain negation or conjunction terms. So this will likely to involve some logical reasoning, and also questions that contain many prepositional phrases or many entities. So this will require more reasoning steps or reasoning constraints. And we find that Dragon is especially useful for this kind of question that require complex reasoning. So here's a kind of concrete example of such a kind of complex question answering example. And here we're also visualizing the model behavior through the model attention weights. So on the left, we have a question that contains conjunction and. And we can see that after several layers of the graph neural network propagation, the model shows stronger attention over entities that are related to this conjunction, such as schools and so on. And then this gives us a correct answer. On the right-hand side, we have a question that contains negation. And for this one, we notice that the model shows stronger attention over entities that are not negated in the question. So in this case, the entities such as beach and so on. So from those observations, we can kind of get the intuition that in our Dragon model, the knowledge graph is serving as a scaffold for performing structured and multi-step reasoning, which is a very exciting finding. So to summarize, Dragon is a new technique to pre-train a language model jointly on text and knowledge graph. And we talked about approaches such as deeply bidirectional model to fuse the two modalities, and self-supervised objective to learn the joint reasoning over text and knowledge graph at scale. And then we showed some exciting results, such as improved performance for multiple-step reasoning, and we hope that this will be useful for knowledge and reasoning-intensive applications. So to conclude this talk, the main message I wanted to convey is that graphs can play significant roles in improving language model training by bringing relevant document and concepts closer together. So we talked about LinkBird, which uses hyperlinks or document links to bring in multi-hop knowledge. And we then talked about Dragon, which further uses knowledge graph to do improved complex reasoning. So I think that there's a lot of exciting future research avenues in this direction. For example, how can we use graphs to better incorporate implicit relations about concepts? And how can we use graphs to perform more formal reasoning at scale beyond common sense reasoning? So we have all our papers and code and models available online through those links. And I want to thank all my collaborators and thank everyone here for your attention. And I'm happy to take any questions. Thanks.
Thank you. We have time for questions. Go ahead.
So a quick question is, have you tried to apply this to a business intelligence context? Can you repeat the corporation point of view, instead of standard analytics, but more of a dynamic discovery through a non-constrained?
Right, that's a very good question. So far, we use kind of the standard benchmarking NLP like question answering. But we think that knowledge graph is especially useful for many industry like business problems. And I think that would be a very interesting application in future work to do. Yeah, thanks for bringing this up.
Just a quick one. Does Dragon beat LinkBird?
Yes, that's a great question. So here we have a BioLinkBird as our baseline, and yes, Dragon, we implement Dragon on top of the LinkBird. So this one will have both document links and also knowledge graphs, and this one improves over the BioLinkBird.
Really cool, thank you.
Thanks.
Yeah, quick question. So is there a human baseline on such reasoning tasks?
Is there a human baseline?
Yes.
Repeat the question.
Yeah, so the question is, does this kind of benchmark data set have human level performance? And the answer is yes. For example, for the common sense reasoning data sets such as OpenBook QA, they have the reference point where they tested human performance. And I think the model is pretty getting close to the human level performance, but the human level performance is still higher. So there's a lot of interesting room of improvement.
Just wait for the mic.
Yeah, I posted this question on Slack as well. So I'm curious about LinkBird. How does it compare to Colbert, which has kind of similar idea, where Colbert like retrieves information from like a corpus?
Right. Yeah, that's a great question. So I think the main difference is that there are many kind of retrieval-augmented kind of retrieval-based language models, which use some retriever to retrieve relevant documents. But here we find that using hyperlinks actually provide more high-quality document pairs, because hyperlinks is something human annotate, and human think those two documents should be related to each other. So we find that using hyperlinks provides better performance. Yeah, but I think the retrieval-augmented language model is a very exciting research direction as well, and with, I think, kind of complementary direction.
Awesome. Thank you so much, Michi. Thank you. So we have a 20-minute coffee break, and we start again, I think, at 3:30. Thank you so much.
Thank you.
Great job. Very nice. Yeah.
switch now?
Okay, okay, perfect. Okay. Okay, awesome.
also digital twins. So the challenge with this is that you can't, like, I love this stuff, but the reality of what I see in working customers, which is 500 million employees, is that their information architecture landscape is enormous. They have many, many, many systems, mostly on RDBs. So my challenge is I can't take, if I go to a retail customer that has 100 million SKUs and variations of products and create a node for each one. Graph, maybe Tiger Graph, maybe some, very few can, they can't do that SKU. Yes, yes and no. So what I have to do is figure out what I call is, first of all, a dynamic extractor that has smart attributes. So I can extract things at different scales. And then for things that are important, I can grab instances. For things that are not important, then I have to build a real-time integration. So if the use case requires for me to pull out every asset that's going to find, yes, I can. Right? But this basically is kind of an expert so that you can understand. And I built this analytics reverse engineering data dictionary, data semantic layer. So this will make it basically a single person can actually navigate the entire complex. Now, the reality is a lot of people are using AI and ML for point optimizations. They're not solving the biggest problem, which is the left hand doesn't know what the right hand is doing in a large corporation. That's the problem I'm trying to solve. That if I have a problem with the plant, the manufacturing site, what is the impact? So impact analysis, right? That might closes what products are being made, which customers, which suppliers, what's in the supply chain. You know, that is the problem. Well, it's super high level, but it's depending on you also want to know the detail, right? Well, I created it. And so when I want to go in for instances, I've got to put a dynamic injection for what I need, and then I reload it on the fly. It's both. I have a tool that does 90% of the work. There's no way that you can make 100% turnkey enterprise anything. Yes. No, I deploy it for the enterprise, and then I sell it. So that's that kind of horizontal solution. But then I sell the license vertical solutions. If you do M&A, divestiture, I'm margin for that. If you want to do digital twins, I'm margin for that. But I also want to do the integration for other and as soon as I do that, then I'll probably sell it. Imagine there's a tool in the market that I can take somebody from SAP to Microsoft and a click of a button and say, this is oh, by the way, SAP will no longer have 25 million of recurring revenue, yearly recurring revenue licenses. I'm a Goliath and David and Goliath and the Dave. Yeah, this is the, and I've talked to a lot of consumers. It's very disruptive because their business model is time and materials. I can do what a team of consultants do in 3 months in 2 days. Me. With the tool I have. Exactly. Yeah. But this is really interesting because the way I see it is that because I have that backward depending on what the customer needs, I can go in and look at that and it says, you're going to optimize this. Fine, I'll go extract it dynamically, put it in the data. Then you can go run your because it's always, this stuff is changing, right? And the fact is that, yes, I have a person, but I don't have one for some custom, bespoke system that's a customer. That's just a lot of sweat. Okay? That's like, yeah, there are tools that can reverse engineer skills. Okay? But what about the semantics? I built the semantic model for a scheme, but for me to go before the system, that's why I want. This is why this is exactly is to add that semantic layer for systems that I don't have those trained models. But anyway, thanks for the invitation. Yeah, my pleasure.
Okay, good. You have 15 minutes or so.
15 minutes.
Or, no. You can do 20. Okay, you are talking about. Okay, super. Sounds great. People are getting a bit tired, but that's fine.
Okay, Matthias. Okay.
So, welcome back from the coffee break. Let's sit down and continue with the program. Okay. Okay, great. So welcome back from the coffee break. We have 2 more exciting talks, and then we have a very exciting panel from industry leaders about graph machine learning. So the next talk will be given by Weihua Hu, who's also a senior PhD student in my lab. He works on applied graph machine learning, and especially kind of problems motivated by the real world. And one of the impactful projects he's been working on is a suite of benchmark data sets, as limited as they may be, as we learned from Brian's talk, but still the best thing there is out there, to benchmark and measure progress around building better and better models. And you are going to see kind of evolutions of this project over the last 3 years and the impact it has had on the community. So thank you, Weihua.
Yeah, thank you, Yuri, and thank you for the kind invitation. So I'm Weihua, and today I'm going to talk about the Open Graph Benchmark Large-Scale Challenge. And this is a joint work with the amazing collaborators listed here. So the starting motivation of this project is that the realization that benchmarks are really important. Historically, this has been exemplified by the ImageNet and MS-COCO datasets in the field of computer vision, and SQUAD and the GLUE benchmark in the field of natural language processing. Specifically, these challenging and realistic benchmark datasets have driven a lot of methodological innovations. For example, on the ImageNet, a lot of models have been developed over time to achieve better performance on the ImageNet, as you see here. And inspired by this, in order to advance the research in machine learning with graphs, we think it is critical for our community to develop diverse, challenging, and realistic benchmark datasets for machine learning on graphs. To achieve this goal, in May 2020, we introduced Open Graph Benchmark, in short OGB, which is a collection of realistic and diverse benchmark datasets for machine learning on graphs. OGB is available under this webpage, ogb.stanford.edu. We have paper describing our datasets. We have a GitHub repository that offers the Python package to use the datasets. In total, OGB includes 15 datasets from diverse domains and tasks as listed here. We have the datasets for node property prediction, link property prediction, and graph property prediction. And we have datasets from natural science domain as well as social and the information science domain. And all these datasets are available through OGB Python package, which you can install easily via this pip install. And with this OGB Python package, you can download the dataset and split the data with a few lines of code. We even provide the evaluation script so that the different papers can use our script to compare in a unified manner. Finally, we have a public leaderboard available so that you can see what are the state-of-the-art methods on our webpage. Since our launch in May 2020, many methods have been developed on our datasets.
In total, there are over 450 leaderboard submissions, and the drastically accuracy improvement of many data sets has been made. Here I'm showing two examples, one on molecule data set, another on product classification data set. And as you see here, over time, the accuracy on these benchmark data sets have been improved drastically. To mention about the impact of OGB, as of today, there are more than 300,000 total dataset downloads, 350,000 total Python package download, 1.5 GitHub stars, and over 800 research papers use OGB to develop their graph machine learning models. Beyond this, we are actively expanding OGB. We actively look for external data set contributions, especially those that are complementary to the existing OGB data sets. And the recent contribution I want to highlight is data set called OGBL vessel data set provided by Potselt et al. And this is a very interesting, unique data set. It's a link prediction task over incomplete whole brain vessel graph of a mouse from a neuroscience domain. And like this, we actively look for graphs from diverse domains so that we can cover a different graph with different characteristics. Beyond diverse graph characteristics, we are actively pushing forward the large-scale graph machine learning. It's because large-scale graphs are really ubiquitous in industry with billions of nodes and edges. However, we know that these large graphs are hard to handle because training GNN on this large graph requires sophisticated mini-batch sampling methods. Also, if we want to learn some unique embedding on each node on this graph, the number of embedding parameters can be huge, which can be hard to learn. And on these large-scale graphs, we also have this machine learning system problem where we need to deal with expensive I/O for this large number of features, and we want to accelerate the training via distributed training. So there are all these challenges awaiting for us for large-scale graph ML. And in order to push the frontier of large-scale graph ML, we need a machine learning challenge on large-scale graph machine learning. To do this, for the ACM KDD Cup 2021, we provided a set of 3 challenging large-scale graph data sets. And this is available through our webpage. We have a paper describing our data sets, and we also have this GitHub repository for providing the data sets. So OGB, large-scale challenge, OGB LSC in short, has attracted huge attention from the community with over 500 team registrations across the globe, and 123 teams actually submitted the final test submission in our KDD Cup. And we have diversity also in terms of the institutions, in both the academic institutions and industrial institutions joined our competition. The unique characteristics of large-scale challenge data sets is that they are orders of magnitude larger than any existing graph data sets. For example, we provided 3 data sets, node level, link level, graph level. For node level, it's a graph with more than 200 million nodes with more than 1 billion edges. For link level classification, it's a graph with about 90 million nodes. And for graph level molecule data sets, we have graph data sets with about 4 million graphs. So it's really large graph. And each data set, as I'm going to explain now, is really practically relevant. So now I'm going to talk about each data set and the performance gain we observed during the KDD Cup. So the first task that we have, this node level task, it's called the MAG 240 million data set. It's a heterogeneous academic graph with different node types, papers, authors, and institutions. And papers cite each other, so there's a citation edge between the papers. Author writes the paper, so there's a write edge, and author is affiliated with some institution, so there's affiliated with edge. So this together gives us this heterogeneous academic graph. And the task here is to predict the subject areas of papers situated in this heterogeneous academic graph, which is essentially a node classification. And on this data set, with more than 200 million nodes, our best baseline achieved like about 70% accuracy, while winners achieve more than 75% accuracy. We observe a huge gain in this KDD, in last year's KDD Cup. In link level prediction, we provided this WikiKG 90 million dataset, which is a knowledge graph describing the facts about the real world. And the task is to impute missing triplets in the knowledge graph, because these knowledge graphs are known to be highly incomplete, and we want to use machine learning methods to impute the links. And the prediction task is basically given a head entity and the relation. Jeffrey Hinton, for example, is a head entity, and relation is the born-in. We want to predict the target entity here. For example, here should be UK. Okay, so and the performance improvement on this data set is, again, really large. Our best model is achieve around 85 mean reciprocal rank. The higher, the better, while the winners achieve nearly perfect MRR on this data set, which is quite impressive. And the final task is at the level of a graph. And the graphs that we have is a molecular graph, and the task is to predict an important quantum chemistry property called HOMO-LUMO gap of a given molecule. And this is a practically relevant machine learning task, because usually this is computed by expensive quantum calculation, which takes about a few hours per molecule, but we want to use machine learning to directly predict it. And this can be useful for a variety of material and drug discovery applications. And on this data set, we again see huge performance improvement. Here, the performance is measured by mean absolute error. The lower, the better. And we again see winners achieve significantly lower error compared to our best baseline. So what kind of methods have brought this huge performance gain during the KDD Cup? In fact, we observed many innovative methods have been developed on our large-scale graphs, and here are the summary. For example, we saw new mini-batch sampling techniques have been developed for heterogeneous graph. New label propagation methods are developed for using GNN. New knowledge graph embedding models have been developed. People start to use self-supervised learning to improve the performance of GNN. And one noticeable technique is that people start to really use the deeper and bigger and more expressive GNN to achieve a high performance on our large-scale data sets. And more details of this, the discussion is available in our OGB large-scale challenge paper on this archive link. So this was last year's KDD Cup. In order to further push the frontier of large-scale graph machine learning, we are organizing the second OGB large-scale challenge at NeurIPS 2022. And the web page is available here. And the winners and their solutions will be announced late November. So please check it out. This challenge basically uses the similar three large-scale data sets as the first OGB large-scale challenge at the KDD Cup. And this is because we want the community to help track the progress of this field every year. So every year, and this is similar to the annual ImageNet challenge, where we see, on the same data sets, like the performance improved every year. And however, for this challenge, we also update some data sets to make them more challenging and realistic, which I'm going to describe now. So the first updates that we make is that for link prediction task, we no longer prepare the candidates for the tail entity. So for the first challenge, for this task, we prepare the 1,000 candidates to let the machine learning rank among them for this tail entity. But for the second OGB challenge, we do not provide any tail node candidate. And this forces the machine learning model to find the correct answer, for example, in this case, UK, among all the 90 million node entities, which is much more challenging. than the original KDD copy, and it's more realistic. The second update that we make is that we start to provide the 3D molecular graph for training molecules. And this is motivated by this thing shown here. So the homo-lumo gap that we are interested in predicting is actually computed in 2 stages. We first have the 2D molecular graph, and we perform some expensive geometry optimization to arrive at 3 molecular graph, on top of which we compute homo-lumo gap. For the first challenge, we only provide the final product here, but for the second challenge, we also provide this 3D molecular graph so that the participants can potentially utilize this information to better improve the model performance. And 3D molecular graph is really emerging research topic in GNN, so we're excited to see how community use this additional information. Okay, so in conclusion, we presented OGB and OGB large-scale challenge to accelerate research in graph machine learning. OGB is actively expanding with external dataset contributions. So if you are interested in contributing, we have a forum on our ogb.stanford.edu website, so where you can see how to contribute the dataset. And furthermore, to push the frontier of large-scale graph machine learning, we are organizing the second OGB large-scale challenge at NeurIPS 2022. So that's all. Thank you.
Thank you. Any questions for Weihua?
So this might be a bit far-fetched, but I imagine most of the graphs in the data sets have some sort of computational representation, right? But have you looked into maybe also including data sets that have graphs that are based on images? So you have an image of a graph, but not necessarily the annotations of, the actual connectivity of the graph. Have you looked into that?
Right. That's a great question. We do not provide those data sets. And those data sets, like even point cloud, you can artificially construct a graph by connecting the nearby nodes. And we haven't provided those data sets. And we can, but one reason is that there can be different ways to model those. And if we try to start to provide the graph structure ourselves, that might limit the creativity.
Yeah.
But I think, but definitely graph approach can be promising for those domains.
Thanks.
Okay. Thank you for the questions. So if you have an exciting graph data set that you'd like to share with the community, Weihua is someone to talk to. So thank you again, Weihua.
Yeah, thank you.
Great. So the last talk of today is by Hongyu Ren, who's also a senior PhD student in my lab. He's working on knowledge graphs, and he's working in particular on these reasoning methods that allow you to ask complex predictive queries over these knowledge graphs. And some of these methods he's developing are finding its ways into assistants like Apple Siri and others.
Yeah, thank you so much for the introduction, Yuri. So my name is Hongyu Ren. I'm starting as a 5th-year PhD student at Stanford, advised by Yuri Leskovich. And I'm super excited today to talk about reasoning in knowledge graphs using embeddings. And this is joint work with several amazing colleagues. So we are interested in this type of knowledge graphs. And a knowledge graph is a heterogeneous data structure defined over a node set, an edge set, and a relation set. And each edge on the graph is in this triplet format that really captures a relation between a subject and an object. In the real world, knowledge graphs have been widely used to capture all the facts and knowledge about the world. So for example, we have Paris is a city, and Mona Lisa is created by Da Vinci, etc. And we can take all these facts together, these triplets together, and create such a large heterogeneous data structure. And prominent examples of knowledge graph include Wikidata and Freebase. Right? Often they may have tens of millions of nodes and hundreds of millions of edges. And they have really been the backbone of really critical industrial applications, ranging from like question answering systems to recommender systems, as you may have heard from the previous talks. So given a knowledge graph, there will be like millions of facts and different entities and relations, right? And with hyperprobability, it is incomplete. So it is very expensive, if not impossible at all, to enumerate all the existing facts. So one of the most important tasks on the knowledge graph is graph completion, also known as link prediction. So basically, given the existing edge set, we want to predict the missing facts or the missing edges. So for example, here, given this current graph, we want to infer whether James has visited the Louvre before. And the prominent solution in the space is based on embeddings. Right? So one solution is called TransE, and the idea is to embed all the nodes and relations to a Euclidean space, such that for all the existing edges on the graph, we will have the sum of the subject embedding plus the relation embedding equals the object embedding. And the key insight here is to model this relation traversal on the graph as a vector traversal in the embedding space. In such a way, we may infer these missing links by simply looking at the embeddings. And this is an active field with many methods developed. So in this talk, however, we really think about how to do multi-hop reasoning. And the goal is to answer acyclic conjunctive queries, which is a subset of first-order logic with existential quantification and conjunction. And one example I show here is that to answer questions like, where did all Canadian citizens with Turing Award graduate? And we can first convert such a natural language question to its logical formula as shown below. And we can also represent this query with a graph, right? And it's easy to see such queries have such a tree-structured query plan where the leaves represent the topic entities mentioned in the query, and this green unique root node that here being this green root node represents the answer. So we may execute this query plan on this knowledge graph. Right? First, we start with the node Turing Award and traverse by relation winner off to achieve all the Turing Award winners. And then we start with the node Canada, traverse by relation citizen off to achieve all the Canadian citizens. And then we take the intersection of the two sets and traverse again by the relation graduate from to achieve the answers of this query. And such a task really has a wide application in many downstream domains. Right? For example, I show here in biomedicine, we can ask such a query on a biomedical knowledge graph, which may further accelerate the process of drug discovery by suggesting the most promising missing facts. However, when we actually making the predictions on real-world knowledge graphs, as I introduced in the previous slides, real-world KGs are often incomplete, in the sense that there are many missing data and missing relations. Right? So for example, 93.8% of people from Freebase have no place of birth, and 78.5% have no nationality. And on Wikidata, 98.12% of movies recorded in 2020 have no information about the cast. So inspired by previous embedding-based methods, our general idea is that we can embed entities and relations in the shared embedding space. And we also want to reason in that embedding space, right? And by this, I really mean that we also want to embed the query in the same latent space. Then we can easily find the answers to this query by a simple nearest neighbor search, right? We can just check which entity is close to that query in the embedding space. And we may train such a model using contrastive learning objective, optimizing the distance between the query embedding and the entity embedding. And the resulting low-dimensional embedding should be more robust to such missing information and allows generalization. And the natural next question is how to embed the query. And our idea is to embed the query by following the query plan, since the query plan exactly corresponds to the reasoning process. In detail, we aim to traverse query plan from the leaves, these blue nodes, to the root, the green nodes. And later, I will show one example in the following slide. And here we propose our main model, Query2Box. And in Query2Box, each entity is represented as a single point in the Euclidean space. And each query is embedded as such a high-dimensional hyperrectangle with two sets of parameters. One set of parameters correspond to the center of this box, and the other high-dimensional vector corresponds to the offset of the box. And this is inspired by one previous work called probabilistic embedding of knowledge graphs with box lattice measures. So with such a box embedding, it is very natural to model a query as such a hyperrectangle. And this naturally has this property of a volume or size that naturally corresponds to the complexity of this query. And many logical operators, such as conjunction, can also be naturally calculated over the boxes. So here I show one example of query to box, which aims to embed the query as boxes. So given the question and its query graph, we can derive its query plan. And follow this query plan, we can embed the queries, essentially each node on the computation graph. Right, so we start with the anchor nodes, this blue node, Turing World and Canada, and we embed it as a point vector on this Euclidean space. And then first, by this relation winner of, we project the Turing World vector to such a red box that corresponds to the embedding of the Turing World winners. And then start with the point vector Canada, we traverse by relation citizen of, and to achieve this yellow box that corresponds to the Canadian citizens. And then we may take the intersection of the two boxes to achieve the embedding or this representation of Canadian Turing World winners. And then we traverse again by this relation projection graduate from to achieve this green box that represents the embedding of this query. And in order to find all the answers to this query, we simply embed all the nodes from the graph to the same space and check what are the nodes that are inside the box. So query to box shares the benefits of all these embedding-based methods. Right? Specifically, we can embed any query efficiently with this linear computation time with respect to the query size. And we can obtain these answers in a scalable manner simply by doing a k-nearest neighbor search. And also the method is very general because we can answer any query, even those we have never seen before, because all these logical operators, they are naturally trainable by design. And it is also very robust to noises. Basically, it's another natural property by using this type of embedding-based methods. Recently, we collaborate with Google Brain and introduced this first ever framework that scales up to such reasoning algorithms such as query to box to extremely large KGs with 86 million nodes and 338 million edges. And this framework adopts a distributed training paradigm with multiple workers and also a well-optimized pipeline that achieves the maximum throughput. And SMORE supports 6 different knowledge graph link prediction methods and also multi-hop reasoning algorithms. So when prior implementation runs out of GPU memory and also time limit on large KGs, SMORE achieves almost like graph size agnostic speed and GPU memory usage. So as shown on the slide, the freebase is 200 times larger than this freebase 400K. But the GPU memory is only like 1.2 times larger, and the speed is roughly the same. SMORE also enables almost linear multi-GPU speedup. And in summarization, how to develop such more expressive and better query reasoning method is an active research topic with many open questions. So there are multiple existing methods that develop different geometries or using different architectures, different GNNs to solve the problem. Here, query to box is only one example. So with SMORE, we have an extremely modularized implementation where implementing a new model only takes less than 100 lines of code. And so we welcome implementations from the community as well. And I'm also happy to talk about several downstream applications of such query embedding methods. So the first application is about answering natural language questions over massive KGs. So the setting is that instead of a structured logical formula as input, one has a natural language question that would like to ask and to find answers on this knowledge graph. So what we propose is called latent execution guided reasoning, where the goal is to really parse the question and achieve this query plan step by step while executing this query plan in the latent space simultaneously using query embeddings. So it is an iterative process of execution-guided synthesis, where we try to grow the query plan for one step based on the embeddings of the current query plan, and the latent query execution, where we execute this newly synthesized step in the embedding space. And this iterative process stops after we achieve a valid query plan, and at the same time, we may also obtain the embedding of this complex question, which we may further use to find the answers using nearest neighbor search. And we experiment or evaluated the method on several standard knowledge graph question answering benchmarks, including MetaQA and the web question. And we use really large KGs with up to 400,000 entities. And as shown on the slide, we improve over previous KG question answering baselines and achieve the best performance across multiple data sets. Another application of query embeddings is fact ranking. Right? So this task is that when querying a database, right, besides knowing the answers, users would also like to have a nice ranking of the answers returned by the database. So here we leverage query embeddings that rank each answer retrieved from the database, and we show in our user study that it correlates really well with the user expectation and user preference. And in conclusion, we propose this box embeddings for answering and modeling logical queries on massive and noisy incomplete knowledge graphs. And we also propose SMORE, the first scalable framework that scales up all these query embedding and reasoning methods to extremely large knowledge graphs. And I have also shown several applications of this query embedding methods towards the next generation neural query engine. And finally, I would like to acknowledge my collaborator and my advisor, and I've also attached a barcode with a link to the relevant papers. Thank you so much, and I'm happy to take questions.
Thank you. Wait, Hongyu, any questions?
A great talk. I'm curious about one thing. The embedding that you're talking about is mostly in the knowledge graph space, the translational transivariant embedding or the GNN. And the general question is, in the knowledge graph space when link prediction comes, have you seen the difference how GNN applies? How do you compare GNN versus transy kind of embeddings?
So that's a good question. So the question is how to combine this type of like shallow embedding like transE with like a modern architecture like graph neural networks. So I think the transE is, you can think of it as a encoder-decoder architecture. Right? So for transE, it really defines a distance function which can be viewed as a decoder, while you can use like different methods, like different GNN architecture or like shallow embeddings that can be viewed as the encoder of the full architecture. So these two can be naturally married together. Like by transE here, we will basically saying that for the encoder, we are using this shallow matrix lookup, and for the decoder, we use the transE type of like L1, L2 distance defined in transE. But actually in the encoder side, we can definitely use other GNN architectures as well.
If I may add on top, right, the main idea here is that you don't only embed the points, the nodes, but that you work with more complex embeddings. So for example, Hongyu presented where the idea is that you embed boxes, and then you learn how to move boxes in the embedding space. And there's also follow-up work where you can think that you embed every node as a distribution into the embedding space. Right, that again allow you kind of to move around in a controlled way. The same way as transE moves from one point to another, you are here learning how to move from one distribution over the entities to another distribution over the entities. Right, and now if you take an AND of two distribution, it's basically multiplying them, and you get the intersection, and so on and so forth. Anything else? Good. Then we'll move to the last point on the agenda today. So this is an industrial panel. So I invite all the participants to come on the stage. Good. Let's see, 1, 2. Yes. Thank you for coming.
Cool, how to sit on this one? Yes.
Great.
Nice to meet you. Thanks.
Awesome. So I would just introduce Nareen Chitar from JP Morgan Chase, who is going to moderate the panel, and then he's also going to introduce our distinguished panelists.
Okay, thank you. Can you guys hear me? Okay. Cool, so hello everyone. This is the last event of the day, and I think you had a very long day, but we're going to make it fun, a little bit like a reality talk show. Is this live streamed or like there's a 10-second delay or something?
There might be 5 seconds.
5-second delay, okay. So he has to react in 5 seconds if we say something inappropriate. Cool. So we have a very highly accomplished set of panelists here. So I'm going to read out their bios. Last night I tried to condense it a lot, but still it's so amazing that I was not able to go past one point. So Evan Feinberg, is that how I pronounce your name?
Close enough.
Okay, Evan. Evan, okay.
Yeah.
So Evan Feinberg is the founder and CEO of Genesis Therapeutics. He received a degree in physics from Yale and a biophysics PhD from Stanford, working in Vijay Pandey's lab. Is Vijay Pandey now at Andreessen?
He's joined between Stanford and Andreessen Horowitz.
Ah,
Yeah.
that's a good strategy. Like he goes to become a VC, you start a fund, you start a company, and he invests in you?
He did indeed.
Okay,
We
cool.
should all do what Vijay did.
Okay, that's great.
Thanks.
At Stanford, he invented PotentialNet and consulted on deep learning for big pharma, and has also worked as a software engineer for MoleculeNet, DeepChem open source projects. Very impressive. Karthik Subbian from Amazon. Karthik Subbian is a director and a senior principal scientist at Amazon. He leads a team to improve search quality and trust. That's very impressive. I have never, ever bought something from page 2. I always write a query and then buy from page 1. So
I hope you don't return it.
He leads a team to improve search quality and trust. He was a research scientist and lead at Facebook to explore information propagation and user modeling problems using the social network structure and its interactions. Again, very impressive. Neil is a lead research scientist and manager at Snap Research. He has 50+ publications at NeurIPS, KDD, AAAI, has been a chair at a number of these conferences. How old are you? Like, you seem right out of college. It's pretty impressive. He worked at Lawrence Livermore National Labs and has a PhD from CMU. And last but not the least, Junyao Lee is the head of machine learning for Apple Knowledge Platform. Previously, she was a distinguished research staff member and senior research manager at IBM Research. She has worked on scalable knowledge intelligence. Her work has contributed to 20 IBM products like Watson, Infosphere, and Cognos. Very impressive. Did you work on David Ferrucci's Jeopardy project by any chance?
We contribute to that.
That's great, very impressive. Cool, so I am going to jump to the questions now. So we have as you can see, we have a very highly accomplished panel today. And hopefully we'll have some time for audience questions. So first question. So everything about graphs is hot. You add the graph prefix to anything, it becomes hotter. GraphDB, graph neural networks. So can you share a few words about how you use graphs, DBs, learning in your work? And in some cases, people have said that they cannot share too much, or else, like, then she would have to kill us if she sees something. So maybe you can say some things about a canonical tech stack or something like that. So Evan, you want to start?
Sure. Can people hear me? Okay, great. First, I should just say it's a real honor to be back here on campus. I started my PhD here at Stanford almost exactly 9 years ago this month. I can't believe how long it's been. This particular spot has a lot of significance for me because the Office of Accessible Education is right next door on Salvatierra Walk. In my first year, because I couldn't walk very much, they gave me a golf cart to drive around campus to get all the way from Raines to the Clark Center, which is a long way if you've been here. And everyone always wanted to get rides on my golf cart. So I didn't really know if they really wanted to be friends with me or just wanted the free ride around campus. But it's really, really great to be back here. So the reason why we started working on graphs is because Vijay Pandey, my PhD advisor, and I identified a key gap, which is that molecules are not pictures, they're not text. Deep learning had been so successful in the mid-2010s, not because of some nebulous concept of AI, but because ComNets were so well suited to images. At that time, RNNs were really well suited to text. This is before transformers. And at that point, we really helped push the field forward of graph machine learning for molecules. And it started with 2D graphs, just representing the atoms and bonded structure of small molecules. And then we realized, though, that that didn't capture anything. As one of the previous speakers showed, really, molecules are 3D objects. So we had to expand to 3D graphs. But the thing is, the way drugs work, and Genesis is an AI-driven drug company, is drugs are like keys, and proteins are like locks. So the drug has to bind to a protein in 3D. So we developed PotentialNet, which is a 3D spatial graph to describe how small molecules interact with their protein targets. What we had to do even recently since starting Genesis that's been so challenging but very rewarding is to incorporate time into that picture. Because the way in which small molecules interact with proteins is not static, but in fact changes quite rapidly. Every few femtoseconds, in fact, there's slight changes that can really matter in the way a drug interacts with its receptor. So at Genesis, we're not just working with, it's sort of the opposite problem to large social or knowledge graphs where you have one ginormous graph that you have to do all these tricks to try to fit onto GPUs. Where you can actually fit huge batches of graphs on one GPU. The devil's in the details of how to set up that graph and how to learn on it and hidden layers of a neural net. It's been really satisfying and challenging as well. But if that's something you're interested in, happy to talk about it further at happy hour. Yeah.
Cool, thank you. Karthik?
Thanks for having me. And I must say, graphs entered my life in a very interesting manner. So I used to work for supply chain optimization. So before working on graphs, it was way back in 2009 and 10 at IBM. And mostly on operation research kind of problems. And I happened to have lunch with a bunch of folks, like Hema is here. She used to be at IBM in those days. And we used to be in the same aisle. We used to have lunch together with a bunch of machine learning folks, and they used to talk a lot about graphs. And graphs started fascinating me when Twitter came in, right? So a lot of people started talking about, there was also KDD Cup Challenge where Twitter data was available, and social network kind of excited me about graphs. And ever since 2010, I have been working on graphs. So in Amazon, we use graphs for a variety of things. By the way, as I speak about Amazon, I have to say, these are my views and do not represent Amazon in any way because you're recording and I don't know how long it's going to be persistent. So, yeah, forever.
JP Morgan is hiring.
Okay, so yeah, talking about graphs at Amazon, all transactional data are graphs in my opinion, right? So any database you have is a graph, so which means graphs are kind of universal. And we had so many talks talking about combining text with graphs, combining images with graphs, and graphs are applicable in different kinds of applications. For instance, if you're searching to know if a query an item is relevant, that's a bipartite graph, right? So the edges are labeled. And nodes have properties, like for instance, an item can have product types and associations with ontology, hierarchy, and whatnot. So graphs are helpful not only in improving relevance and quality of the results we show in search, but also improving the trust. Sometimes you buy items and then you may have to return it because you ended up buying a wrong item and you blame yourself or probably Amazon, whatever. So we want to avoid those situations and make sure customers are happy, right? So to do that, we use graphs to find buyers and sellers who collude and try to leave fake reviews and try to boost the rank of an item. And we do use graphs for all these different applications. And yeah, I think graphs are everywhere at Amazon.
Thanks. Neil?
Yeah, thank you. Thanks, both of you, and thanks for having me, Stanford and Vijay for leading the panel. So, yeah, I think, I have considerably less experience than some of the other folks on this panel, but I started working on graphs during my PhD, where I was mostly working on graph anomaly detection problems on online social network data. And transitioning from my PhD, I joined Snapchat about 5 years ago. And there, it's really interesting working at a social platform where still a vast majority of machine learning applications, are treated as kind of a standard deep neural network and tabular style models. We kind of know from the academic field and the academic perspective that, so many social problems are really fundamentally graph problems. But a lot of those this gap of tabular learning to graph learning is still kind of making the jump in quite a bit of industrial areas. And I'd like to think that every day someone looks at a problem that they're looking at and kind of has a eureka moment where they think that they're actually approaching this problem all wrong and everything actually should be a graph. This is certainly true at Snapchat. We have very, very big social graph data. Of course, at its core, one of the flagship products that Snap has is Snapchat, which is a very big social platform with hundreds of millions of users and many, many tens of billions or trillions of interactions between them. And so in a lot of cases, we use graphs for a variety of things, including trust and safety, like Karthik mentioned, as well as recommendation systems, which is probably a very big application area. But ultimately, I would say that the big kind of insight towards using graphs at Snap has kind of just been that most user-centric problems are relational at their core, and you can't make very good predictions about users if you don't consider information about what their friends and the people around them are doing. And so I would say that that's kind of the motivating insight behind a lot of different types of applications of graphs, whether traditional graph mining approaches or graph neural networks. At a social platform like Snap.
Does your team also work on recommendation engines?
We work a little bit on recommendation, but we're mainly kind of a siloed research team, and we kind of have applied projects that work.
Okay. My teenage daughter specifically asked me to ask you, are there any hacks for being a social influencer on Snapchat? This is actually, she asked me in the morning. So if you have some tips, please share them.
Yeah, I might be the wrong person to ask. Thank you.
Good, thanks. And last but not least, Yunya.
Sure. So I'm leading the ML team in Apple Knowledge. So we have probably one of the largest knowledge graph in the world. So of course, everything we do is related to graph. While I cannot name specific product, you can think of everything within Apple. There are opportunities that by better understanding the world, better understanding the user, the experience will be much more intelligent and be more pleasant. So in terms of problems we work on, I think everything you heard about today, we actually work on pretty much all of them, from question answering to reasoning and influence, graph completion, entity linking, and so on. So it's really like one thing we work on every single day. So it's a lot of exciting things they are working on. I'm very happy to be here.
It's awesome, thank you. So let's go on to the second question. How do you collaborate with universities, with faculty and students? This is such a new topic that I think you might have to rely on these universities for new talent. So maybe you can start.
Can I jump in first?
Sure, please.
Yeah, because this is a topic I'm really passionate about. Because like when we are in industry, right? Like how can we connect with the people in academia? So I think one of the most natural thing or most popular thing is interns. Bring students to industry so that the student can learn from inside and learn about the problem, about people, the team, the culture, and so on. So that's probably one of the most common way. The second is actually depending on the company, depending on the team, you can establish collaboration directly with university, either through very large program, like when I was in IBM Research, we have something called the AI Horizon Network, where we establish multi-million collaboration with universities or with individual faculty members through things like joint study agreement, where you can actually sign NDAs and share IP across company and university. The third is you can also host faculty members or visiting students, so they can come. They're still employee of the other, of the research institute, but they have access to a lot of assets within the company. Sometimes they're hired as contractor, so they are also regarded as the employee of the company as well. The fourth, I think, very important aspect is open source, right? Either open source code or open source the data. So personally, I feel, as an industry researcher, one of my obligation is to share what I learned within the industry with broader audience. I cannot blame the student or the faculty to work on problems that are not real, right? Because if I don't provide a venue for them to actually understand the real problem, how can I blame them? I think that's also a very important aspect. Fifth is actually participating in all kinds of community building events. For example, ACL has a mentorship event where you can actually share with the student, what you learned at your own career and help them grow and so on. Personally, like for example, some of you know, like I championed and organized industry track at the various NLP conference, and I feel that's also a very important way to create value within academic conference where they actually have a bridge to work directly, to learn about work from industry.
That's very impressive, actually. Just a few years ago, Apple was very closed, and now I can see this sudden change in position and stance. So very good work by you and your team. Anyone wants to take this question next?
Thanks, Karthik, and thanks for the answer. Yeah, I echo all these points. I think that, in general, industry is really well positioned to provide a certain kind of healthy degree of pragmatism to a lot of academic problems. And of course, like industry and academia have different roles they play in the research community. Of course, like Snap, Snap as a whole has quite a healthy intern program and numerous collaborations with external forces. Research, specifically the team that I'm on, we work very heavily with university collaborators throughout the year, as well as we have a quite healthy intern program. For context, our team is about, I think, 30 full-time members in research, and we usually have a class of something around 50 to 60 PhD interns every year. So we get to work with quite a few interns, quite a few interesting problems, and a good degree of mentorship there. I would say that, I think the internship programs and the university collaborations are absolutely essential to good research. There's kind of a healthy amount of pragmatism that comes from industry and liberal application of resources that are often required for making progress on some really large machine learning problems in practical context at scale. And academics, of course, provide the latest and greatest methods. A lot of students that are very deep in technical details and knowledge of up-and-coming methods that are sometimes a little bit removed from industry. And so I think it's really a match made in heaven. And for any students that are listening, Snap is hiring interns for next year, so please shoot me an email if you're interested.
And probably interns are the target users for Snap in some way, right? So no product manager needed. Directly start.
Do you check how many stars they have, how many followers they have?
We do. So any of you who send me an email, please make a Snapchat account. Send a few snaps before emailing.
Cool.
That increases your chance of internship, I guess.
Yes.
Okay, awesome. So At Amazon, I think I kind of second like everything Yunya and Neil said about internships and ways you can collaborate with industry, right? In addition to that, there are a few opportunities we have uniquely positioned at Amazon. If you're a faculty, you can do Amazon Scholar, right? If you're and Amazon Scholars are like part-time positions. You can do 20%, 50%, 100%, whatever your university allows you to do. And you can come in for like, some period, whatever period your university allows, and collaborate, and then leave, right? So this way you get access to like, the kind of platforms and tools and data and people and all of that. So that's definitely a unique opportunity. I know many of the scholars who join Amazon eventually became full-time, right? So I request people to talk to me if you're interested in any interesting opportunities at Amazon. This is across the board, which means not just search like Alexa. Across Amazon Scholar program is available. And we also hire interns throughout the year, like spring, summer, or fall. You can do 3 months or 6 months, depending on your availability and your visa immigration status. So yeah, once again, welcome you to apply to Amazon. Talk to me. Yeah, you can see me as a liaison for Amazon here.
Cool. I have a quick question. So with interns and all that, the IP is quite well established. It's all your ownership. But when you work with professors or something like that, or the labs directly, have you guys smoothened that part out?
Yeah, I think it's a really good question. So when I joined Amazon in 2018, the publication process, I would say, was kind of getting started, right? So, but now it's a very well-established process. I think we have been working with Uray for almost 2 years now, and we have several other collaborators who we work with, like Atlas Wang at UT Austin, and SVN Vishwanathan, who used to be at Purdue and then UCSC, who moved to Amazon eventually. All these people have published a lot with Amazon, right? And the publication process is so smooth. So, so in terms of IP, we have legal teams who take care of that. So you have to just give them a little bit of a notice in terms of publication. So if you have some interesting work which you want to make it public, we even open source data, open source code. Yeah, and recently we ran the KDD Cup competition for ESCA Challenge, which is like, open sourcing the search data set for queries and ASINs, like 2.5 million query ASIN labeled data set for information retrieval challenge. So I think a lot of things are happening in Amazon in terms of enabling research and pushing the academic boundaries.
That's great, thanks. Evan?
I definitely echo everything my co-panelists very eloquently said here, but just to add a little bit of color to it, even though we're recorded, I'll be as real as possible with how I'm speaking about it. Supervisors mostly see interns as it's a very lucky outcome if there's 0 value. Anything above negative value is like a great thing from an intern. But like, we've been so pleasantly surprised by it, and we did something that we thought was insane as an early stage startup last summer. We're kind of unique as a company in that we're 50-50 tech and biotech. So we're 37 people. We have a team of 13 full-time ML researchers and ML research engineers up in San Francisco. And we took 8 interns last summer, which everyone thought was a crazy idea given our stage. But it was wonderful. They were all students typically at MIT, CMU, Stanford, Cal Berkeley. And so they had, a 1-to-1 faculty to student ratio, if you will, if not a little bit more than that. And everyone produced something awesome and created a great culture. Like, it was such great energy to have all these young undergrad and PhD students in the lab or in the office bringing all these fresh ideas. And just to use a case study, we had one intern in particular who was really brilliant, had some great ideas, and wanted to continue the research thereafter. So after he went back to MIT, we hooked up with his research advisor and started up a collaboration between the two, which, to use as my co-panelist said, it kind of brings the best worlds. We have immense computational resources and access to real-world problems. Whereas oftentimes in academia, you see the access to the latest and greatest methods that sometimes are a little bit too far away from practice, but we can really bridge that gap here. And unlike my colleagues, I'm not on social media, so if you want to apply for internships all year round, email me at evan@genesistherapeutics.ai, very old school. I should just give a little bit of a different take on the question. which is to contrast the academic environment to, in our case, a fast-moving startup. One of the things I loved about my PhD was that ability to work on really greenfield areas without as much deadline pressure as you get in industry. The difference is in academia, the incentives are not always well aligned for collaboration. Oftentimes the most interesting research really comes at the intersection between different fields. In our case, it was really computer science, physics, chemistry, biology. It's the opposite in industry. As a small startup, we're all very well aligned in our incentives. So even though we have, the plurality of our team is on the engineering side, we have large chemistry, biology, and other groups, and we're all incentivized to collaborate together to create new inventions. And that's been a really refreshing thing in contrast to academia and all the troubles of trying to write papers in between labs. So if that sort of interdisciplinary effort and all the fruit that comes out of it sounds interesting to you, we should definitely talk, because it is quite a contrast between how things work at a place like Stanford.
Cool, that's very impressive. And I think Stanford has nailed that process very well. And I was reading, I was seeing this on a documentary once, where like how Silicon Valley became the valley, and I think Fred Terman was one of the first people who encouraged this movement between industry and academia. So yeah, very impressive. So let's move on to the next question. A quick show of hands. Any students left? Bachelor's, master's, PhD students? Okay, there are a few. So the next one is for them. So any ideas that you have for all these students for their theses or the next startup or something like that? What would you like them to work on to get an internship or start a new company? Anyone want to take it?
Maybe I can get started. So, for the last 2 years, we have been working closely on scaling GNNs and deploying GNNs to production. So, while a lot of interesting discussion happened today, I happened to join the meeting only in the afternoon, so I apologize if I missed stuff in the morning. But in terms of scaling GNNs, I think there are 3 avenues in which we can do a lot of interesting research. One is on the system side. So today, we scale GNNs using distributed training of models. So we basically partition the graph and have the graph across different GPU machines and train them, aggregate the loss, then backward prop the loss, and then update the weights, right? I mean, that's how you do the synchronization of the weights. And there are a lot of inefficiencies in this approach, right? So there is a lot of system research that needs to go in. Needless to say, we do have scalable systems today that works. That doesn't mean like we don't have the tech. We do have the tech. We can scale to trillions of nodes and hundreds of trillions of edges, and we have AWS DGL offering, which is Deep Graph Library, which does that. So I'm not saying like we don't have the tech. I'm saying like, we need to improve the efficiency with which we do use the memory and compute. The overhead is very high. So a lot of system students should encourage to look at this problem to see if we can increase the efficiency of our training process and inference process. So in terms of inference, can you deploy the GNN model to production today? Search applications where more than 10 milliseconds the customer is frustrated and leaves to another platform. That's another interesting question. Training and inference at scale with high throughput and low latency. So that's one interesting research question. For algorithms folks, how efficiently and quickly can you do a partitioning of the graph for distributed training? And do we even need distributed training, right? So can't we just sample the graph in a more meaningful way such that it fits in a single instance and we can finish the training and get away with it? Do we really need so many GPU machines and clusters to actually train? I mean, that's a very interesting question. In terms of ML folks, for students who are working on machine learning research and optimization, can we do elastic and asynchronous training of GNNs, right? So think of data as just pouring on you in volumes, and you have like a definitive set of resources, let's say finite set of resources, and you can maybe add a few machines here and there, but that's pretty much it, right? But you need to be able to train your models in an elastic manner such that you can keep adding machines, and when you run out of machines, you are able to remove the machines and your model is constantly being trained, right? So elastic and asynchronous training of GNNs, I think these are all interesting research areas to me. I believe a lot more to happen in the next 5 years in this space. and looking forward to it.
Cool, thank you. Neil or Yunyao? Or no?
Yeah, I have a lot of thoughts on this, and actually, Karthik, it's interesting to hear you have these three enumerated directions, and the two that you mentioned first are actually top of mind for me, and are very related to my answers. So definitely, I think the scaling up GNNs, there's the training and inference pieces, which Karthik mentioned. I think definitely very critical. And actually, I think it's more fair to ask like, what about GNN training, or what about GNNs isn't slow? Pretty much there's slowness kind of from the very beginning, and massive, large scale, even like data preparation, different strategies for kind of doing distributed computing and training GNNs in different ways, are kind of more pre-compute or pre-process heavy versus post-process heavy. And so, there are a variety of strategies on like what should the right way of even training a very large scale GNN model be. Should there be more pre-computation? Should there be kind of like a live, sharding and partitioning process, and so on. I guess on the inference side, this has been a focal area for a lot of recent work that that my team has done at Snap, and this I think is going to continue to be a very hot area. Real-time inference I think is very challenging with GNNs because of data dependency issues, and so naturally we kind of have this like blessing and a curse of data dependency that GNNs provide us, as opposed to kind of more tabular or traditional models where you lack this data dependency. And so, that academic performance, the improved performance on graph learning benchmarks when you use GNNs compared to tabular models, in industry you really see the cost that comes with in real time. And so, better strategies for actually deploying these models in real time. And in the second area, about like, the actual graph, right? I think another area that my team has been really interested in, and I think is a kind of continued open area for research, is kind of augmentation methods on graphs. So in general, there's kind of this perception on graph data that we kind of have a given graph data, we have some given node features and attributes or labels, and we want to solve a problem. But who said that was the right graph to solve the problem? Should we be sampling that graph differently? In the cases where there doesn't exist a graph, Brian Perosi from Google earlier today gave a great talk on how should we be building that graph. But in general, I'd argue that any task where a graph is given, we should first be asking, like, is this even a good graph for the task? That should really make you think, because you'd suspect that in many tasks that's true, but there are certainly tasks for which it's not, because your data is noisy, because there's adversarial information in the data, because you have limitations of which data can be collected. And of course, all of these implications for how you should be augmenting, like adding edges or nodes or information to your data, or dropping edges or nodes or information from your data, have impacts also on the scalability piece, which both I and Karthik have talked about now. So I think this kind of interplay between like what is the graph that we should be using, as well as like how should we be thinking about deploying systems on that graph in production settings, those are two really hot areas. And finally, I just want to kind of add a little piece, because this is supposed to be for students. And independent of whether or not you actually work on GNNs or this area, I think that my biggest advice to students is usually to definitely do an internship at a company or at a lab or someplace outside university culture at some point in your PhD. It's really kind of awe-inspiring how your perspective changes when you get exposed to problems that other people are working on, and you start imposing constraints in your own thinking about what kind of problems you should or should not be working on and be prioritizing. So I think that goes for pretty much all the kinds of problems in the world.
Okay, so I will add a couple of things really short. I think rather than give you the fish, I will teach you how to get the fish. I think the most important thing is to leverage what's out there, right? So we have an industry track out there. Read the papers, understand why your favorite, latest, complex graph neural network cannot be applied there. And think about how do you come up with something that can actually solve the problem, but at the same time have a lot of scientifically speaking, right, interesting element. The second part, of course, doing an internship. I think the biggest challenge I have seen when I was a graduate student or when I interacted with graduate students is why you work on this problem. So you tell me how, you tell me, but can you tell me why this is important? Why should I care about it? I think looking at the industry track, look at their problems and challenges can help you better understand and articulate the why.
Nice, that's a very nice. And I think it helps, definitely helps for you because you have such a strong brand. I think that probably helps hiring, all those kinds of activities a lot. Cool. So I'm just doing a check on time. Okay, it's 4:40. So how about we do one more question and then we can open it up to the audience. That sounds good. Cool. So I just snuck this question in very last minute. So I have no idea whether you're prepared for it or not. But let's do a quick rapid fire question. Cool. So I'm going to start with Evan.
So the rule is we just say one word? Like what's...
Yes, I'm going to ask you 3 questions, very quick, like Family Feud.
Okay.
And then answer it really quick. Okay. What's your favorite graph algorithm?
Potential net.
Parameters.
Personalized PageRank.
A star, because that's the first algorithm I learned.
Okay, cool. Next, going to start with you. Your favorite open source package?
Okay, so I'm going to tell you the latest one my previous team created called the label sleuth. So how do you create a model and label at the same time within a couple of hours?
Cool.
NumPy.
AWS DGL.
PyG. Yeah.
Cool. And the last question. Favorite Stanford professor, except Ure?
Professor Vijay S. Pandey, of course.
Chris Potts.
I'm going to say Ure anyway.
Dan Jarofsky.
Okay, cool. So I think we're done with our questions. So why don't we open it up to the panelists, to the audience? And just remember, these are like this amazing set of panelists. They probably charge $1,000 an hour for their advice. So make use of this and get your questions answered for free. Go for it. Yes, Rock. Oh, you need a mic? Okay.
So first I have disclosure. I worked with Ure for 10 years. And I went through this GNN revolution. You know, before, lots of things were very hard, especially heterogeneous graphs. And now suddenly, all the graphs with features, heterogeneous, we don't care. You know, you can have noise, missing links. GNNs will solve it all. So the question I have for the panels is kind of the GNN revolution, in your view, at the beginning or kind of at the end? You know, are we, if we have hockey stick, are we at the beginning of hockey stick or are we toward the end of the hockey stick for GNNs?
I think it's a great question. It kind of goes to one of the previous questions to the panel, which is sort of like what to work on. My view is if there was some central planning committee that knew what to work on or knew the answer to the question, like, you know, that person would be going to Stockholm like every year and figure that out. But the reality is it's impossible to predict where a field is going to move, in my opinion, which is why from the question of like what topic to work on, like I'll provide the fish in some way that I love for you to work on pre-training on graphs, which has come a long way. I think that's a way the field is going to move a lot. So I think we're not near the end of the revolution in that way. The other is architecture. There has been immense amount of effort in 2D architectures of graphs, and only recently has there been really interesting work in equivariant neural networks and some other areas. So those are 2 areas that I think will that should lead us to believe that the GNN field, which is certainly far more mature than it was in 2015, has many more years of really fruitful work ahead. I think it will just turn into a field that might be called something different, but still will be fundamentally be GNNs or message passing networks or whatever you want to call it.
Cool. Anyone else want to take this?
Yeah, I think we are always at the beginning of the hockey stick. So there's a long way to go for GNN because, as I said earlier, I mean, there are several research challenges where we need to move the needle forward to make it even possible for a lot of practical applications. So I don't think we are done yet.
Yeah. Sure. Yeah, I think we're. I mean, it's I think this is a biased group to answer this question, but we're definitely far from being done. I will say that, like, of course, there's a number of problems in the area, and I think that's kind of evidenced by the different kinds of GNN works there are these days on, like, architectures, modeling, scalability, expressivity. I think there's just so many different kind of little subfields within GNNs that have now kind of come up that will continue to thrive, and more will continue to exist. One of the big kind of recent areas that I've been excited about myself is a lot of applications towards link prediction and recommendation systems. I still feel like a lot of GNN work focuses very heavily on node level and graph level tasks. And to take some issue with the premise that Rock was saying, regarding like heterogeneous GNNs and them solving all the problems. I think there's some really interesting recent work that I've been looking into with some collaborators from Michigan State that suggests that in a lot of knowledge graph applications, for example, where heterogeneous GNNs see practice or use, these heterogeneous models can actually be beaten by well-trained and fine-tuned MLPs. I think there's really interesting kind of position papers that are coming out, I think, in the GNN space these days of like what can't GNNs do well, and where are we kind of making these false steps in the advancement of GNNs. And so I definitely think that there's quite a bit of work to actually be done in making some of these models work on these kinds of more complex problems. And I think that work will become even more evident as we start applying those problems in practical ways. For example, large-scale GNNs for knowledge graphs is still, I would say, way more advanced in the academic community than it is in the industrial community. And the academic community, of course, has different kind of experiences regarding benchmark data sets and publication pressure that may or may not skew the needle in some ways compared to actually finding out whether these approaches work for real problems.
Yeah, I just want to share one simple indicator. I think by the point if you cannot get a PhD from top university by doing the work on GNN, that probably indicated towards the end.
Thank you. So Yuri, do we have more time, or you want to close it? One more question? Okay, I have a hard question. So, I think, so someone in Silicon Valley made this amazing comment. When you fundraise, it's AI. When you hire, it's ML. When you implement, it's logistic regression. And when you debug, it's printf. So that stuck with me. So on that philosophy, can you sort of share some really candid anecdotes or advice for the students here? It's a hard one, so it's okay if you pass.
Yeah. Okay. I find it very amusing. I'll start with. I'd like to find out who said that. I think what I'll say is if you're really passionate about deep learning in general or GNNs in particular, you should seek out an opportunity, whether it's an academic position or industry position, that's directly aligned with actually using some advanced deep learning technique or field that you're interested in practice. Because a lot of what happens is, exactly as the quote demonstrates, is that for a long time, and even today in this risk-averse investing environment, you put AI on a slide, suddenly your valuation goes up by some percent, right? I think that will actually diminish as we enter into more like macroeconomically tumultuous times, because investors seek more risk-averse opportunities these times, and I think that will actually accentuate true value, right? And this kind of goes to the show me aspect of this, right? So in my field, machine learning has been used in drug discovery for decades. It's just been called something different. In the molecular dynamics community, it's just been fitting parameters on physics-based models with really fixed functional forms. In cheminformatics, it's just been basically logistic regression on fingerprints, right, with variations based on that. If that was so good, we wouldn't be talking about this, right? Drug discovery would be stalled, but obviously those more traditional techniques have severe limitations that deep learning in various iterations has that potential to surmount, right? So I think you want to look for the places where you can really create obvious qualitative value that traditional ML models cannot. And that's the way it'll be most incentive to be working in the most innovative possible workplace.
Thank you. Anyone else?
Yeah, I think my take on this question is if you join, say, let's say you do the internship at any of these Bay Area companies, right? Then you will have a strong baseline. You know what that baseline is? That's logistic regression, right? So I won't deny that because I have gone through that process, and I think I was listing a bunch of research questions. Some of the research questions are, how many layers do we need? Probably just one, maybe two at most, and I still doubt the two because like shallow embeddings and shallow models are like pretty effective and very easy to train and easy to distribute, right? And practical, very practical. So the question for the audience is like, how complex is actually complex? Like, should we simplify our models, right? Because I think the metrics between academia and industry are very different. I think in academia, the models are a lot more complex and evaluated on very public benchmark data sets, and a third decimal improvement is actually an improvement, is counted as an improvement. But if you deploy that model in production, if you don't move the needle for the company, right, then it doesn't count as a win, right? So that's why I think I kind of see the print of statement like everywhere, right? So on logistic regression, it's very hard to beat. So I think the question for academia is how complex is complex and what is the most reasonable value we can extract out of the complexity. And to add to my co-panelist, the point, which is there any insights we can learn from complex models we have developed that industry can adopt and advance, right? I mean, that's also an interesting thing to think about.
Thanks. Yunyao?
I think it's really important to think about why you are doing certain things instead of worry about how you do it, right? Because all these things we are learning at school, there are tools in your toolbox. But it cannot be just because you learned this most powerful tool and that's something you're going to apply for everything, right? So in fact, there are a lot of value to start with something simple so that you know what's the proper tool to apply. I think another thing also to think about is not just look at the final benchmark data, the final numbers, look at the details. This is something I observe, a lot of students is doing, like especially when you have benchmark data out there, you just look into, okay, I have 0.9, now I'm 1 percentage point better. So I strongly encourage you to look at the data, like what actually have changed, what's the change, what's causing the change. I think that can give you a lot of intuition and directions to do something different from other people.
Thank you. Need anything?
My read on this was actually very similar to my co-panelist here. I think that basically, the 4 different strata that you described, I think to me that actually sounded like a spectrum between pure research and engineering. I think I guess the question was really about takeaways for students, but I think this goes back to the you should intern kind of feedback that I had, because in reality I think as students you have it's very easy to gain misperceptions about how easy different parts of that stack are, anywhere from pure research to engineering, and anywhere anyone who works on one part of that stack always kind of deprioritizes or has like a warped perception of how important the other pieces are. And I think that for me personally, coming from kind of a research academic environment and joining Snap, or I could say this about joining probably any company, would be that there is a lot of intricate and detailed engineering work that needs to get done to make a lot of these things work in practice. And of course, this is all built. Even logistic regression, for example, is built upon many, many, many years of statistics and careful, theoretical and pure research work, even if it comes down to print tests at the end.
Awesome, thank you. So with that, I wanted to thank each and every one of you. Really fun panel, really very insightful. So off to some wine and beer. Yeah, cool. Thank you. Thank you.
I'm just going to conclude and say a few last words. Thank you, Narendra. Super. So I will just conclude the event and just thank everyone who attended, all the people in person, and everyone online as well. We had big audience online. When I was checking, it was around 1,500, I think was the highest, and then of people connected live, and then it kind of dwindled down as the time zones shifted in more unfavorable ways. Thank you for all the speakers and panelists. Really appreciate everyone giving amazing talks and very insightful presentations. And also, thank you to the Stanford Data Science Initiative and all the whole organizing team, especially Joseph, Malvana, Rok, and Ivailo. Really, without them and their help, this event would not be possible. So thank you again. To finish, there's drinks, there's food outside, so we can talk and digest what we learned. Thank you so much.